here with us on campus. After an incredible week of online sessions, we finally get to meet in person and continue our journey into the world of quantum computing. Welcome to the day 4 of the IISc Kiskit Fall Fest 2025. Today, we have some very interesting sessions lined up, starting with a talk on quantum technologies, directions and prospects, followed by simulation problems, and later we will have an exciting session introducing quantum machine learning. So let's get started and make this session interesting by interaction and learning. We really hope that the interactions turn out to be a two-way communication, and we will request audience to actively participate. To initiate proceedings, let me introduce our esteemed guest and professor. We are honored to have with us Professor Apurva D. Patel, who will be giving the first talk of the day on quantum technologies, directions and prospects. It is my privilege to introduce you, sir. Apurva D. Patel is an emeritus professor at the Center for High Energy Physics at the Indian Institute of Science, Bangalore, and is involved with the IISc Quantum Technology Initiative. He is also a visiting professor at the ICTS-TIFR, Bangalore. He completed his MSc in Physics in 1980 from the Indian Institute of Technology, Bombay, and PhD in Physics in 1984 from the California Institute of Technology, USA. He has extensively worked on lattice gauge theory, investigations on quantum chromodynamics. He is also notable for his work on quantum algorithms and the application of information theory concepts to understand the structure of genetic languages. He was exposed to the subject of quantum computation during his graduate student days at Caltech, and he has been teaching the students at IISc for more than 25 years. Now, I would like to invite Professor Apoorva sir to the stage to deliver his talk. Sir, it's an honor to have you with us today. The stage is all yours.
How to set up my laptop slides. Actually, on my port, that side. Settings. Display. I can start whenever you want. I can start? Okay. Good morning, everybody. I am going to talk about quantum technology, and in particular, what are the directions worth pursuing given the resources available in our own country. Note that there are only 5 slides, and this is the first one. But every statement which appears on the following 4 slides is important. You have to spend some time digesting it, and that is why it is enough for me to have 4 slides. I can talk about all kind of things if you want later on. So, let me start with this label, potentialities and limitations, which was the title of the course that introduced me to quantum computation more than 40 years ago. The full title was Potentialities and Limitation of Quantum Machines. It's interesting that the person who gave this course, Richard Feynman, was at the same time very adventurous and also very careful. So, he put both these labels, potential and limitation, in the title of the course itself, and he talked about both. You will no doubt hear a lot of things about the potentials. Maybe you have heard a lot of it in the past, and in the coming days also you will hear about it. My focus will be on limitations, and the reason for it that it is absolutely necessary to understand limitations if you want to find practical applications of quantum technology. So, the first fact is that the extent of quantum advantage is problem dependent. Even with the full power of quantum computation, some problems will become easy, but some problems will remain hard. There is no absolute statement that everything will get simplified with quantum technology, not true. And there is a very simple test to understand which problems are likely to get simplified. And for that, we have to go back to the history of why quantum theory was developed. And it was developed to explain physical phenomena that existing classical theories completely failed to explain. Not just give some approximate answer, completely failed. And it was done by introducing a new constant of nature, the Planck's constant, which did not exist in classical theory. If you consider the situation where Planck's constant is 0, you can have all the linear algebra you want, but there will be no quantum effects. So, it becomes a necessary condition to identify, does Planck's constant appear in the problem which I am trying to solve in some form or the other? If it does not, that it will be silly to expect that quantum theory will come and do something better. And this is a huge area. The full span of classical physics, starting from Newton's laws to fluid dynamics to Maxwell's electrodynamics. It's all classical. There are lots of problems inside there, but you don't need quantum theory to solve that. And the classical techniques which we have will work very well. Don't try to jump onto saying that, oh, quantum theory is going to come and improve this problem. It will be foolish to do that. And the question then is, where all places Planck's constant appear? It's a necessary condition. And there are several well identified situations. One of the most common one is the identification of conjugate variables like position and momentum. They are there in classical physics as well, but when you go to quantum theory, those conjugate pair of variables will have an uncertainty relation. Heisenberg's discovery, or it's a consequence of the fact that these conjugate pairs of variables will not commute. And the magnitude of that commutator or the magnitude of the uncertainty is given by the Planck's constant. So, that is one way to check, does this feature appear in the problem that I am trying to solve. Another example is the Planck's constant is the fundamental unit of angular momentum, or if you want, the quantization of a single photon energy. The constant h will explicitly come inside that. So, if you go to at that single photon level or single angular momentum quantum, yes, Planck's constant will appear over there. But you have situations with large number of quanta, nothing much is going to come out of quantum theory. Yet another place is little bit technical, it's a quantization of phase space, which is used to describe classical physics, and the Planck's constant is the minimal area in the phase space. It cannot be made smaller than the value of h. In classical physics, you just have a point is not allowed. And if that phase space appears again in some description that you are trying to tackle, one important situation is quantum statistics, which explicitly involves this phase space, whether it's Bose-Einstein version or the Fermi-Dirac one. It will involve Planck's constant, and yes, then there will be quantum effects. So, there are the examples, but you have to think a little bit. If I want quantum effect, I must identify that the problem I am to solve somewhere or the other has contribution from the Planck's constant. Next fact, that the quantum dynamics is highly fragile against external disturbances. And that means that it will work well in cooperative and protected situations, but not in hostile cases. This is important because to create these cooperative and protected settings requires lot of effort. You have a quantum system, but then you have to have good shielding, good control, perturbations from outside systems should not get in, but yet it has to be connected to control systems and measurement apparatus, which are actually outside systems. So, you have to set up things nicely, so these disturbances are minimal. And all this effort, all the peripheral structure that you need, it makes quantum technology expensive. This is not going to go away. Quantum technology will get cheaper, but it will never become cheaper than classical technology. The classical technology does not need this huge amount of protection. It's a fact of simple economics. Other thing is you have a quantum instrument and you want to put it in the field somewhere, arbitrary places. Well, you don't know what the environment is going to do. It's not a nice protected laboratory setting where everything is under control. Take it out on the field, it may not work. Quite common in many situations, and then you have to go back to classical stuff. No real option. The third thing is that classical technology is not idle. It is actually improving as well. These days, a lot of contributions are coming from neural network algorithms providing machine learning and artificial intelligence. That development is completely classical. So, if you say that I am going to get some advantage, the target is moving. You will have to talk about advantage compared to classical technology at that particular stage. After 5 years, well, the things you are comparing will be different. And there is some byproduct, that is competition helps. That you improve one of them, then the other side will say, oh, I can do this something more over here and improve that. And that's a good thing to have, that you have two contenders and they can feed off each other. So, what is the bottom line? That quantum technology will be attractive only in cases where the advantage offered by it is sufficiently large to offset its cost. The advantage has to be there. On top of that, it has to be sufficiently large. If it is not a large advantage, it's a question of economics. I can pay a little more in terms of cost, but I will have a stable classical instrument doing the same job. Okay. So, the consequence is that quantum technology will appear in practice as special purpose devices. It is not a general purpose solution to everything. It will be used as custom made subrouting for tackling certain tasks. For the rest of the stuff, you will use classical technology. It will be a hybrid situation in that particular sense, and that is the way the technology is developing. You are trying to identify specific areas where there is advantage. You will use a special purpose device based on quantum theory to tackle that part, keep the rest of the stuff classical, and see what you can get out of this whole setup. All right. Next slide. So, what do you expect in this particular setting? And I have listed topics with this traffic signal symbol in front. The first thing is green. It's already there. And these are development in high precision sensing and metrology. These are small sensors or measuring instrument connected to lot of control and peripherals, and you perform accurate measurements. They have already been demonstrated in laboratory framework, and some of them have already been used in specific settings. I will come to some examples little bit later. So, it is already going. Second thing is orange. It's on the step of happening, and these are developments in communications and simulations. Again, prototypes have been demonstrated in both these particular field, communications over network, certain features, and simulations. By that I mean simulations of physical quantum systems in various conditions. The other two things are red light, not ready, and probably it will take a while. We don't know how much, but it will take a while to happen. One of them is what is of interest to scientists, that you made lot of measurement with high precisions. Maybe you will stumble onto something new, something which you don't know. And that will be a feedback of high precision measurements onto theoretical framework. This is how science and technology have interacted all the time. You measure something to high accuracy, find something, then you try to develop a understanding of why it is coming out so and so. And most of the time what you find is kind of surprise. Well, it was not supposed to be that, but it showed up. And quantum theory itself is an example of that. But there is one particular problem in quantum theory which we haven't understood very well, and that is what happens when you measure a quantum system. You have the prescription, projection onto an eigenstate, but it's a discontinuous process. You don't have a dynamical equation for that. And maybe with all the high precision measurement, we will actually find out what is actually happening when you perform a measurement. That will be a what you call contribution to quantum theory itself. And computation is a long-term goal, it's the last on the list. It's going to take some time, maybe 10 years, before you get anything reasonable out of computation, and how far it will go, that also remains unknown. Again, I can say a little bit more later. So, this is a sort of roadmap of what to expect. And then what is the status? Status is that the theory is way ahead of practical implementation. Not in our own country just like that, worldwide, but the gap is larger in India. And the reason for that is that we have constraints on both infrastructure and manpower. We need sophisticated instruments, and we need skilled enough people who can use those instruments to do something non-trivial. And these hurdles have to be overcome. They are problems much more on the hardware design and engineering side than on software and theory. So, what should we do? That we don't have enough of infrastructure and manpower, so we need to concentrate whatever we have in one place. You distribute it all over the place and hope that something will happen somewhere. You are wasting your resources. So, we have to essentially build from scratch, but this is the strategy which has worked well in India. The two prominent examples in this category are the space technology and the nuclear technology. They were dedicated, concentrated efforts, dedicated with a group of scientists, kind of isolated from the rest of the world. They just went after the specific problems and achieved something. So that is what we need to keep in mind, but at the same time we should not kind of close ourselves off from whatever is happening in the rest of the world, because we can learn from the dead ends which appeared somewhere else, or we can even reverse engineer some of those things to save effort, and that can help in our developments. But ultimately there is no shortcut to doing indigenous development. It is true not only in the quantum physics, but any high technological area. If you want to become what you call self-sufficient, you have to build from scratch all the way up. You cannot rely on somebody else giving you some high level stuff. It does not happen in any area. There will be always questions of sanctions, security, blah blah blah, whatever it is, and you have to keep that in mind. All right. So, what should we prioritize? And here I have written, go after tough problems. Why? Because in the technological area, there are 2 points of view. One is a user's point of view, and other is a designer's point of view. User's point of view is just like the way we use our mobile phones. Press a few buttons, we get the answer which we want, and that's fine. Very few people understand how that answer came. For that, you have to open the box, see the circuit, how the questions or the algorithm was mapped onto the hardware steps, and that is the designer's job. How did you make that mobile phone? And it's not everybody's cup of tea. Okay? The pressing buttons is easy, everybody will learn. Even children figure out how to press this and get some interesting stuff. But designers is a very specialized job. You need to have enough knowledge about the algorithm on one side and the hardware on the other side. And it's a mapping, but you have to perform that, knowing all the properties of the materials which went in and the mathematics which came together with it, etc., etc. And one thing I can point out, that we are talking about all kind of quantum devices, but if you look at all the announcements, whether it is IBM or Google or Amazon or Microsoft or whatever it is, or other academic institute also, nobody mentions that we will replace our mobile phones and laptops by quantum devices. They are very useful computational tools, but why doesn't anybody say anything about it? And the answer, short answer is because it's not worth it. I pointed out at the very beginning, quantum technology will help as special purpose devices. These are not the areas where it is worthwhile to have quantum technology. The classical technology buried inside the mobile phones and laptops is perfectly sufficient to do the jobs which we want them to do, and of course, they are very stable. So, what should a designer do? And the designers have to build these are platforms which actually are now software libraries running on various workstations. We can do that even in India, and it's some generalization of CAD, the computer aided design tools. Every device, quantum or even classical, we are using it anyway, they would need this kind of simulators or design platforms to control errors and improve accuracy. There are parameters, you play around with them, adjust those parameters in some way or the other and find a good configuration, and then only you go for fabrication. Lot of design is just done on workstations. Because fabrication is expensive, you cannot repeat it very easily. The setting on the workstations you can change very quickly and find out what their consequences are. And the important point is that the fabrication will always have some kind of imperfections, and these tools tell you what will happen because of the imperfections, because you need to control them, and you play around with all the parameters to make these imperfections as small as to be tolerable. And certainly these kind of things are available with all the big companies. IBM will have it, Google will have it, Microsoft will have it, but they are the proprietary systems, they are their intellectual property. They will not put them out in public domain. If you want to do it yourself, well, you have to make your own version of it. What do you do after you make this design? That you have to make elementary components, which are, in case of quantum technology, qubits, single photon sources and detectors, but all that design effort will help you to get high fidelity, low decoherence rate, good control, etc., and they are the building blocks. They will be used in a variety of quantum devices, the same building blocks arranged in different manner. So, we do not have to worry about how we are going to put a large number of building blocks together. First step is to make good building blocks. And if you are able to do that, you have actually achieved quite a lot. If you have good building blocks, the first application which is easily available are these sensors and imaging devices, because they have small number of components. So, a few building blocks will be useful in making them, and the rest of the support system, peripheral electronics, etc., is classical, and they will allow you to measure all kind of things. On top of that, these are the systems where you can improve the precision or accuracy step by step. Whatever I can measure, well, I improve it by 10% in the next generation. That is fine. You do not have to look for a large jump in one shot. And so, every little step you can take in design can actually help, and the applications are very wide ranging. You can measure time, space, movement, electric field, magnetic field, gravitational fields. They all have their various applications. For example, an accurate measurement of time goes inside what are called the atomic clocks, and which are essential ingredient of the GPS system, global positioning system. Accuracy which is used there is in time, and it is measuring distance, because well, speed of light is constant. So, distance is just speed of light times the time interval. And how can it help? Well, Right now, if you look at various kind of Google Maps, the accuracy is of the order of a meter. Devices of higher precision using some quantum transitions have already been made, which can reduce that 1 meter to 1 centimeter, factor of 100, it is not a small gain. What will you do with a 1 centimeter resolution is a different story. Many times it may not be necessary. I mean, why do you want to measure it at tiny distance when you want to go from here to the next building? Not necessary, meter is fine. But then this military and defense applications, they said, okay, we will have higher resolution to pinpoint our targets. They have a different point of view. So, the applications will come from different directions. Some part will be beneficial to society and some part will be beneficial to people who are involved in war, and they will keep those parts secret. They will not want to reveal their what you call technical points. Space and movement, well, they allow you to perform navigation, how fast you want to travel from this point to that point, and again it can be useful in a what you call our practical navigation to some extent, but military people want to use them in their missiles, so they look at it at a different point of view. This electric field, magnetic field, etc., they are again high precision sensors. One of the beneficial part for the society here is medical diagnostics, because a lot of systems in high precision diagnostics these days involve detection of electric fields and magnetic fields to high accuracy. Example are the MRI, magnetic resonance imaging, or even ECG, electrocardiogram, or EEG. They are delicate measurements of some electric field and some magnetic field. Well, if you can improve the accuracy, you will be able to certainly do something better. And what can be done? Well, now the magnetic and electric devices are sitting in some specialized centers. You are able to make them small. You put them in ambulances, and they will go all over the place mobile. So, that is a huge advantage of being able to make high precision sensors. You are detecting the same field, but now the accuracy is improved, so you can make them portable. And that can have a huge benefit. Gravitational field again has ways to detect perturbations in density, so they can basically find what is underground without digging up. It can be some mineral, it can be even some tunnel, it can even be some what you call deposits of things like petroleum. You have enough accuracy to detect these perturbations, and the accuracy is measured by the depth, how deep you can go, and things which can go deep by 10 to 100 meters are becoming available. Okay. So, yes, there are these applications, and certainly they are special purpose devices, but yes, in several cases prototypes have been demonstrated, and now question is of putting it in practice. Together with this quantum sensors, another development is occurring in what are called quantum inspired algorithms. These are classical methods, but which we had not explored because we did not ask the right question. And the questions are coming from knowing quantum physics. And there are many interesting applications which have been thought of. Again, putting them in practice is a important question, but they are asking different questions. We are well versed with the digital structure, which behaves more or less like discrete particles. But quantum feature allows you to treat certain objects as waves. And what can you do with waves? We have used waves for communications for quite a lot of instruments, but we have not really thought of waves as a computational device. And if you think of waves as a computational device, well, there are a lot of things possible, and people have implemented some of those things, though not talking explicitly in terms of a quantum technology language, because it is not necessary, but you have high precision instrument based on wave property. What they allow you to do is tremendously improve the signal to noise ratio. One example is the way astronomers give us images of stars and galaxies and black holes. How do they do it? The algorithms actually involve interferometry, which is a wave dynamical feature. You have an array of telescopes detecting some particular source. It is important that the signal which is coming is a wave signal. You have multiple detections, you do interferometry with very high accuracy, and you are able to extract high resolution. It is essentially improvement of signal to noise. Can you do it in a smaller scale, like in a mobile phone? People have talked about it. Again, the broadcasting tower is sending some signal, but you have to put multiple detectors on the mobile phone, not just one receiver. And if you can do some interferometry with that, well, you will have a new device. It can help in bandwidth, essentially signal to noise ratio coming into the play, and maybe it will be practical in some sense. There are many examples of this wave type dynamics. Another familiar instance is our own what you call natural selection for detecting sound and light. Sound and light are waves. And we have 2 eyes and 2 ears. That double detection allows you to do something instead of having just 1 eye and 1 ear. And what is that? Well, there is a slight difference between the 2 signals. Our brain does something equivalent of interferometry, we do not know, but 2 eyes allows you to have a parallax, and so you can judge a distance. On 2 ears, it is in the time domain, but slight time difference is that it allows you to detect a direction of the source, where the sound is coming from. And that would now not been possible with one wave detector. And well, incidentally, our mouth and nose are particle detectors. One of them is enough. We do not need more than that. But you have to think a little bit about, and there are lots of this kind of quantum inspired kind of strategies. Well, if you can make use of them, you will have interesting things to come about. there are some technical features which are used in algorithms these days. There is something called classical shadows and tensor networks. They are classical observations, but they extract certain kind of properties of a quantum system which can be useful in a limited context, and they are also offering certain advantages. Okay. Another aspect which is not really quantum, but again you can call it quantum inspired if you want, and this is the development of what is called a quantum safe cryptography. It is a perfectly classical strategy, but based on the fact that there are certain problems which are hard to solve even for a quantum computer. They exist. We are turning the whole thing around. That you convert those hard problems into a cryptographic protocol, and then even somebody who has access to a quantum computer, a quantum hacker, can't break the code. So, that will be a non-trivial development, and actually lot of investment is being made in this direction. It is a very specialized area requiring sophisticated mathematics, but there are challenges and prizes of $1 million if you are able to succeed in any one of this kind of task. And they are actually necessary to tackle certain problems like authentication. That authentication people worry about is somebody will impersonate you, break your code and log in some place as you and do something nasty. And security right now we have are all these OTP and multiple device communication. So, you verify, cross verify that it is indeed the same person handling all those kind of things, and that is our way out. If you have a quantum safe cryptography, then you can make good progress on the authentication situation, and important part of that authentication process is actually quantum random number generators. So, the part which is quantum inside is that the dynamical process which generates these random numbers is quantum. Does not have to be a computer, it can be tunneling, shortness, photon quadrature, various kind of other quantum effects can also be used. But if the origin is quantum, then we do not know how to break it. So, that is the point of generating these random numbers and using them for authentication. Right now, the OTP is supposed to be random, but it is actually generated by some algorithm. If somebody figures out that algorithm, the OTP can be broken. You can have a better system than that. This is something which I already mentioned, okay, that this multi-path interferometry can help a lot in signal to noise ratio in communications. Astronomers have been doing this. The gravitational wave detector, in particular this LIGO observatories, which have been detecting collisions of black holes, they are using quantum features. Otherwise, detection with such high resolution just would not have been possible. So, that feature has gone inside, and the essential part is you need quantum signal coming in some form or the other, or if I am talking about waves, you need information about both the magnitude and the phase. Magnitude is the intensity and phase is the wave nature of the signal. If you have both of them available, you can combine magnitude and a phase as a complex number, and all the quantum machinery can be used to describe what you are doing. So, this is a development which is non-trivial, but it is important, and it is going to be part of the various kind of communications and observation systems. And one another part which I mentioned was simulations. So, what are we trying to do is we are simulating various kind of molecules and materials whose important properties are at the quantum level. If the material is very simple and you have a macroscopic crystal or a table like this, you don't really need quantum physics to understand that. But if you want to understand how the properties came from various atoms joining together in some particular way, some chemical reaction, some transitions, even in biological systems there are a lot of enzymes and catalytic processes, well, they are all happening at the atomic level. And if you want to understand them and then improve them, take advantage of it, you need quantum simulators. The simulators which will mimic that quantum processes into a hardware. The advantage is that the mimicry will have a lot of free parameters. The hardware will have some fixed couplings between different atoms, etc. So, here you tune the parameter to figure out some new possibilities, new designs, and that can help, and it can help all over the place, physics, chemistry, biology. You can even study novel material as well as what I call non-equilibrium reactions, because you actually observe evolution in time. And many of these things are not possible with the current instruments we have in all physics, chemistry or biology, and that will be a real breakthrough. And there are very simple materials which we do not understand in this first principle manner. Most common one happens to be water, which is well, they are all over the place, either in environment or chemistry or even over our own biology. The crucial property of water is dictated by what is known as a hydrogen bond, which is a tunneling of a proton between different oxygen molecules, and the tunneling is a quantum process. And we do not understand the full dynamics of what these hydrogen bond networks are doing, and that is why we do not have a first principle understanding of properties of water. Of course, you can measure its properties in a large ensemble, like what is its density or what is the conductivity or polarizability, etc. But properties at the individual molecule level can be very different, and they can do very non-trivial things. So, okay, that is kind of a situation of going after tough problems. And one last warning, because people ask me about security, that what will we do if we do not have quantum technology, but our adversaries have the quantum hardware. Can we still protect ourselves in some fashion or the other? And surprisingly, there is a way out of it. It comes from the fact that quantum information processing is highly fragile or unstable. So, it is much more vulnerable to attacks compared to the classical technology. And if you have an adversary using quantum technology, well, you do not have to figure out what exactly is going on. All you need is to cut it off. And surprisingly, that is easier, and on top of that, there is nothing the adversary can do about it. It is like, what does the government do when there are riots and chaos and various things going on? We are not trying to intercept every message going on between different mobile subscribers and what are the rumors, etc. We just switch off the internet. No communication. You don't have to care about what can be communicated. If there is no communication, well, the rumors cannot progress. And that is something which can be done about quantum situation as well. Don't like it, cut it off. And there is nothing anybody can do about it. So, that is in a completely different directions. But yeah, one last statement. What is it that we can do in India with our limited resources? First thing is, if you want to contribute to this subject, learn some quantum physics. Without that, you will not have basic understanding of where something can be done and where there is an advantage. And in practice, there is lot of thing to gain from devices which are kind of small enough, order 10 qubits are enough. Many of the sensors and detectors which I talked about fall in this particular category, and if you can control them very well, you can contribute a lot of new things to the technology, which can be indeed helpful to the society. Thank you. Of course, there is time and I can answer whatever questions you may have.
Good morning, I'm Narendra. So the question I have is, how can quantum technology, as you've stated previously that if an adversary has quantum technological advantage, the best way to cut off that advantage is to entirely switch off their mode of communication, or try to use the vulnerability that it's highly disruptible. But in the future decades to come, it's obviously that both sides in any conflict are going to utilize quantum technology, right? So what do you think the future of quantum technology in the field of defense is going to look like? I've heard of quantum radars, but what do you think? How effective would that be, and what other technology could come in the future decades to come?
Yeah, so there is nothing quantum about cutting off the communication. As I said, you cut off the internet or jam the signal or something like that. It's used in conventional warfare even now, because the signals are nothing but electromagnetic waves. If you figure out what is the channel or band in which they are being used, they can be cut off. And in war, those kind of things happen regularly. You just jam the signals. You are not worried about what is the signal in practice. And no physical phenomena can bypass this jamming attack. Only thing is to be known is what is to be jammed. If you can figure it out, there is nothing you can do, because ultimately it's a physical process, and some signal is getting transmitted from one place to another, and it can always be cut off if you know where it is. Radar can also be jammed. There is nothing peculiar about it, but using a radar at a large distance is not practical, not in the quantum domain, because you have to run it at a single photon level, otherwise there is no advantage, and then the intensity is so small that virtually it cannot go a large distance. What is possible is these are radar kind of signals at the tabletop devices, where they can be used because the distance of propagation is not large, and there the signals are useful again in medical diagnostics. You want to do imaging of certain kind of molecules or properties with a higher accuracy, precision, whatever you want to call it, resolution at the tabletop level in medical diagnostic environment. You can do it and it will have a benefit.
Good morning, Professor. In the context of India, where does India stand in terms of making qubits? Like, where is India focusing its resources? Like, how are we building qubits from superconducting qubits or from photons or trapped ions? Where does India stand in this?
Right now, there are competing hardware platforms for making many of these computational devices, whether it is superconducting, whether it is photonic, whether it is ion trap or neutral atom arrays. You don't know which one will be more useful in which situation. And likely scenario is that for a certain type of task, some particular platform will be more useful. And then again it will bifurcate that for simulations actually these neutral atom arrays are doing a very good job these days. A photonic platform will be useful where you want something to be done at room temperature, and it will have limitations because of the interactions are small between photons. You need some material in between to generate nonlinearity. That is not so easy, but if you have room temperature applications which you want to use it in a broader what you call field of area, spread it out in different locations, photons do a better job. Superconducting devices do a localized job which is much better, but then you have to work literally at a very low temperature system, which is expensive. So, you need all the dilution refrigerators and things like that, and that is possible in a very protected environment, but for certain kind of tasks it will be advantageous. So, there is no universal answer that I will use only one hardware platform all over the place. It is all going to be special purpose things and very much application oriented.
Good morning, sir. Sir, you just before mentioned about like defense technologies and everything. I just want to add up one question. Like you just said that signals can be jammed. Okay. So what if our country wants to target any other country? So they can also use the jam technicality. So how does quantum is going to focus over there? Means what's the role in the defense like?
There is essentially no difference between quantum or classical or whatever label you want to call it. War is a war. You want to break down whatever I have and I want to break down whatever you have. Whoever succeeds first probably has an advantage. And it doesn't matter whether I have a classical instrument or a quantum instrument, the adversary will attack them. And then a question is, can you protect whatever you have from those kind of attacks? And yes, if you have a strategy, or the strategy is to decipher what is being communicated, that is a different game. And the strategy where you break down the communication, it is a different game. And military actually uses both of them. Many times they want to what called eavesdrop the signal, that you extract the content of the message, but the people who are communicating don't know about it. And that hidden information can be used for some attack in future. And this was actually the strategy which was used by the British group against Germany in Second World War. They broke down the code which goes by the name Enigma, but they did not reveal that we broke down this Enigma code. They just kept on observing the message and taking the countermeasures. So there are no hard and fast rules. Okay, war is a war. Everything goes. Whatever you can think of, you can try to make the best use of it. And there is no what you call ultimate thing as well. Somebody might find out a new strategy in the future. Well, we don't know. It's a what you call cat and mouse kind of game. Break one thing, people will find something else, and break that, and then you find something else, and so on.
So in the interest of time, we have to move to the next talk. Dr. Apurva will be available for the questions during the tea break. So thank you for the questions. Thank you, sir.
Thank you so much, sir, for such an inspiring and thought-provoking session. Can we have again a big round of applause for sir? We are truly thankful for your presence, sir. As a mark of our respect and gratitude, we would now like to present you with a memento. May I call upon stage Debarti to present the memento. So moving ahead, we now have with us Professor CM Chandrashekhar from the Indian Institute of Science, Bangalore. Professor CM Chandrashekhar is a faculty member at the Indian Institute of Science, Bangalore. Before joining IISc, he served as a professor at the Institute of Mathematical Science, IMSc, Chennai. His research focuses on quantum information processing and quantum computation, with an emphasis on developing quantum algorithms for stimulating natural quantum phenomena and engineering entangled photon states for quantum information applications. Now I would like to invite Chandrashekhar sir to the stage to deliver his talk.
So, thank you very much for the introduction, and it's good to start where Professor Apurva Patel left. He was mentioning the importance of simulating systems, right? So, I will try to talk about simulating quantum systems. So there are various ways, and there are some specific ways which we can simulate it in a more organized manner. So that's the focus of my topic, simulating quantum systems using quantum walks. I'm going to say what quantum walks are and how you can simulate various quantum systems. So there were many examples which Professor Apurva Patel said, whether in physical system or in a chemical systems or biological systems. We'll take some examples and then show. So our group at IISc works on developing algorithm for simulating systems, and we also build photonic quantum systems like smaller number of qubits, and then we are working on simulating some of the physical systems using smaller number of qubits. But this talk will be focused more on the theoretical side of the algorithms and how we look at it. Okay, so just the way we begin with, the whole idea or the whole field of what we are calling about building quantum computers or quantum technology, whatever it is, a full operational in general, the grand problem for us is, can we ever build a fully operational quantum computers, right? In principle, we should be, because if nature is quantum mechanical, we may have to find some ways. It might take a decade, 2 decades, or whatever it is. But if we can build a fully operational quantum computers, we should be able to simulate most of the things in nature, right? Wherever, because if we are talking about atoms, the fundamental laws which are describing them are quantum physics. So there should be the building block, and you should be able to study or simulate what is happening in particle collision, or what is happening in molecular chemistry, or might be entanglement in electron systems, even some superconducting behaviors, black holes which are unreachable, like but the dynamics are all defined by physics which we know. So if we have an operational quantum computer, then we should be able to simulate them and understand to some extent, right? So, but that's the grand problem. So we are nowhere, close to such grand problems being addressed, but we are attempting. So there is a start of it. The start has happened only few years back with the ability of research community to control quantum systems, right? First and the foremost for me is, if I have to simulate something, I need to have another quantum system which I should start controlling. For almost, it has been 100 years now, the quantum theory from proper formulation, but it has been only few decades, like 2 to 3 decades, where people started controlling atoms and controlling photons so that you can build the systems around them. So we have been in a very early stage of being able to control systems, so might be in long run we will have, right? So what do we mean by quantum simulations? I think just this is the pictorial. It uses principles of quantum physics to develop tools to solve and understand problems where quantum effects are prominent. It can range from all fields, right? Wherever it is. As I said, the nature itself is built on basics of quantum physics. So if there is some quantum system, which means that there is some evolution which is happening, it may not remain the same. I can always write some state as initially, after some time something would have happened. So there is some dynamics of it, right? So that is what is happening in nature. But then to simulate them, I need to map. I need to consider some other quantum system where I can prepare some initial state which is approximately close to what might be the state of the system or a nature which I want to simulate. And there will be some dynamics which nature is doing. I need to mimic those dynamics to the good approximation, and then I will get a final state. So this could be a complicated, inaccessible system. When we are talking about high energy, something is traveling at a very high speed and you can't stop them and you can't access them. But something has started and something has ended. So if I have some other system, if I can mimic those states, then I can prepare, simulate, measure, and understand what is happening. It's almost like watching things in a very slow motion and understanding what is happening in a system, and that's where simulation helps us a lot. So we can, in fact, we may not be able to build exactly U. You may start building some U's, and no U is giving you this final F. At some point, you will strike to a proper U. Then you would say, okay, that is what nature is doing. Like you might have to start approximating this U bar, and then you will figure out what U is. So that's what the whole idea of quantum simulation is. And the major objective as a field of it is that first is, why can't classical computers do, right? Classical computers, even today, we go to computers write some program and it say it's simulating, I'm trying to simulate something, so it can't do. There are reasons for it. One is, one I said, to harness controllable evolution in open systems to simulate other inaccessible complex systems. So there are systems which are not accessible, they are complex. So I have some controllable system I will do. Another one is to turn an exponentially scalable resource needed to simulate quantum systems. The classical computers are not favorable, like you can't use classical computers if they are exponentially scalable. Like what does that mean? Is that there's a simple table which I think people who are working in the field know, prepared it long back, and that holds good. So if I'm taking just an electron or an atom, right? So there's a picture is there, but I'll just give you an example. I have an atom, 2 energy levels. If I have to simulate those atoms, I can prepare some 2-qubit state, right? So classically, I would need 2 classical bits, 0 and 1, to just mimic that 2 state. Now if I take 2 atoms which have just only the valence electrons having 2 possibility of being in ground and excited state, then I would need 4 possible classical bits to mimic, to simulate the interaction between 2 atoms. When we say interaction between 2 atoms means one electron could be in ground state here and other one could be in excited, or it can be all possible configuration. Interaction could do that. So that will be 4. The moment I have 3 of such kind of atoms interacting, my classical bits needed would be 2 to the power of 3, 8. And the quantum state, so superposition will come to that. But the moment I start looking at many atoms together, even if I have like 10, 30 or 50, for example, if I take 50 atoms and they say there's a complex molecule has been formed, and the electrons from one, or the valence electrons from one can hop between everything, and then there can be some state, I would approximately need about 10 to the power of 16 bits of classical system to see that all possible configuration. Now that is almost to the limit of the best of the supercomputers today which I have there, right? So if you are trying to look at, this is a crude picture of it, but the numbers speak a lot. So if I am trying to take a quantum system which can be in superposition and they can always be written in a tensor product state, then a good 50 qubit quantum system, a very clean, that's what I said, like efficient quantum system, if I have, then it can create that 10 to the power of 16 possible states, just a 50 qubit quantum systems. So that's what when we meant a resourcefully scalable system, classical computers can't exactly simulate them all. Like how do people do today? Like people in quantum chemistry, people who work on drug designing, they all have to deal with these chemical complexes on a daily basis. And if you can't study the whole of those complexes in one go, as a one single picture, they break them down into small problems or like in a small subsets. Parallelly, they try to simulate them and then they stitch them together and get some. So while doing this, there has been a lot of approximation which was going on, because quantum systems are all connected. There is always correlations between this system and this system. The moment you cut, you are losing some information. The moment you are making smaller pieces, then the exact solution is different from what you are getting. But since we don't have a more efficient way than that to do, people still use parallel programmings and then use a lot of big simulation techniques to come up with some approximate ways to simulate this kind of system. So that's what we mean that you need to have a resourcefully implementable systems, right? So this is what it says, the way the numbers says how quantum systems can help in simulating. So even if I have a small number of systems, right, even if I have like 4 or 5, I think the last point which Professor Apurva Patel mentioned, that 0 to 10 qubit system, even if you have small number of systems, if you can control them efficiently, then you can at least exactly mimic. You don't have to do any approximation. What is happening might be in hydrogen oxygen interactions, or might be in other small like 2, 3 atomic configurations or something. So that gives you a clear understanding of what nature is doing and the way you are simulating. Might be some corrections can also happen with the way we do it with quantum systems. So now there are again, the field itself has 2 approaches. So we call one is a digital quantum simulation, right? So when say digital quantum simulation, which means that there is some Hamiltonian for the dynamics. I think you all might have an idea of what Hamiltonian would mean. It describes the dynamics of a system, total of potential and kinetic energy. If I know the Hamiltonian, then I can understand many things about a system. So you might have some Hamiltonian of complex system, you might have an axis for that. Then you need to break that Hamiltonian into smaller components such that you can make a small combinations of unitary operators, and then those unitary operators has to be converted into computational gates, and then that would be the way you take these gates, implement it on a quantum computer, and that's one of the ways we call as a digital quantum simulation, which means that it can be any complex Hamiltonian. First thing is that how do I convert into an efficient unitary operator, and then how do I break them into small set of gate operations, because that's probably is what you all are familiar with. You can go to some available softwares, implement gates, there is some initial state and you get a final output. But how do I come up with gates? I need to first think of an Hamiltonian, break them down to unit operators, build a gates, and then look at it. So that's what's called as a standard digital simulation approach. There is another approach which is called analog quantum simulation. This is slightly not based on unitary evolutions or gate operations, but what it does, it takes an alternative approach where sometimes nature itself is trying to give you some systems which are identical to another one, right? So there is cold atom examples which Professor Apurva Patel also mentioned at the end, where these are, you can have atoms in very lattice structure and you can control them. So there are Hamiltonians, many Hamiltonians can be simulated there. So nature might have some Hamiltonian. If you can simulate roughly the Hamiltonian by controlling the trapping potentials in cold atoms, then you will be able to simulate something in nature using some other system. But they may not be gate based, but they also will not be universal. When we talk about universal, means anything, if it is given as a unitary operators, I can break them down into gate operations and then implement. So you don't even have to worry about whether it will do or not, as long as when you say universal system, it should be able to simulate anything which are unitary, ideal case. But analog simulators may not be able to simulate everything, but it will be able to simulate Hamiltonians which are similar and certain similar structure, and they are still of very good use. And this has been, both these approaches have been very widely followed, and people have been solving a lot of problems, understanding them, using them to understand various systems in condensed matter to high energy, and take them as a small set of problems to computers, implement them, and even validate the operationality of the computers, quantum computers also, right? So from that, I'll focus mainly on the digital simulation here. I will not have any example on the analog simulation. So what I said now in terms of digital simulation, this is a kind of pictorial way. It can be any complex system we pick from nature. First is we need to develop some algorithmic or operational approach for that. I should break down that, whatever approximation or whatever form it is. First I need to come up with some algorithmic approach, and then from that you would have an unitary operations, from that you will build a quantum circuit, then take a circuit to an hardware and then implement, right? This is the standard procedures we have to follow to simulate quantum systems, digital systems. So now I'll take, to need to come up with some algorithms. So there should be, I can't have for one system, should I develop an algorithm? For if I have 10,000 systems, should I develop 10,000 algorithms? But there might be some generic class of algorithm which we can control in various ways or make certain modifications and simulate at least a large class of system, right? That's what I'm going to say about. There is one of such algorithm which we call as a quantum walk. It is a good algorithmic resource. It can simulate few classes of, or probably a large class of quantum systems, and I'll just describe that. It's not something which is very new. People have been using a classical version of quantum walks for centuries, right? So the simple example is that you toss a coin, you get head or tail. Depending on head or tail, you move to left or right, right? So now it might look like it's a very simple problem. So what is so special about it? And it still tries to give something. You can start making things more complicated there, right? I can toss a coin with different probabilities. When I'm tossing a coin, there might be another walker which comes in between. Then you create what should be the relationship between them. Then the dynamics becomes complicated. That can be mapped to some physical systems. It can be some biological dynamics or some Brownian motion dynamics or some diffusion dynamics. or it can be even in astronomical systems, there are planetary, not planetary motions, there can be some collisional dynamics or some formations which statistical physics is all about many subparticles moving around, interacting. So people have been using it as a fantastic tool for like hundreds of years. Even today, people use the most complicated forms of classical random walk as an efficient tool for simulating and developing algorithms to study systems. The quantum version of that is I toss a coin, I get head or tail, I move to the left or right, but quantum mechanics allows us to be in superposition. I think that you are all familiar, right? So it can allows us to be in superposition, which means the particle, whichever I am trying to think about, you toss a coin, it can go in superposition at both the places. Unless you make a measurement, it doesn't collapse. So which means that it can end up having some finite probability of being at every place at all the time. So that is a big picture of what it means by quantum walk. So you have a classical version, and the moment you're converting it into a quantum version, it means that you are now bringing in some quantum feature, which we call, it also takes interference in it, right? Because there is some amplitude which is contributing to the left and right, from here also to the left and right, and there will be some interference which is happening here. So the dynamics has superposition, it has interference. The two feature which we call as the basic quantum mechanical principles are getting captured here, which would also include entanglement here, right? It automatically comes because you have path, position in which is going, and the particle, it also creates entanglement between. So all the three features of or principles which we think as a resource for quantum technology or quantum information are used in this simple dynamic. So using this, so we can, this is an example which is one of my favorites of like 1943, where Professor Chandrashekar wrote stochastic problems of physics and astronomy. This is a simple one-dimensional problem of random walk. As I said, it just begins with tossing a coin and you describe random walk, and he takes it from modeling diffusion to how you are addressing a lot of problems in astronomy. Right, and that remained one of the classic reference. It still remains one of the classic reference for classical random walks and the power of it in simulation. So we do envision a similar kind of, the broad applications of quantum dynamics in such time. Okay, so I will try to give a mathematical formalism when we say, I said you have superposition, you evolve in superposition, but I still have to write them in a mathematical form. So which means that there are two particle and then there's a position, because you need to evolve. I toss so coin would have spin up and spin down, or you can treat it as 0 and 1, it's just a notational difference. I have a particle which moves, and then the position, which is the lattice. So, but since I can have a superposition, I can always write a particle in superposition state. Now coin is not just head and tail here, because when we switch from classical to quantum, we are now dealing with unitary operators. We are dealing with vector spaces, right? So it can be in superposition. So which means that I have to take some unitary matrix which evolves it. If I take spin up and then apply this unitary matrix, I will have a superposition of spin up and spin down. That's what it says. Then I define a shift operator. The language is the same. The formalism when you're trying to write an operator different. Like spin up will go from j to j minus 1. Spin down will go from j to j plus 1, which means that head is moving to the left, tail is moving to the right. But because it is in superposition, and this evolution will take them in superposition. So that's all. You just have to repeat them, step by step. And the moment you do this, you will end up having a probability distribution which is very different from the classical system, right? If I am doing a classical random walk, what it means that there is always a probability of you coming back to where you began, because you might have gone to the left, next time you might come back, you will end up having the high probability of being around the origin itself and low probability of being anywhere away from. But the moment you are changing this into a quantum dynamics, there is a constructive interference which happens away from the origin, and you would end up having a wide probability spread. And this itself was, this was not even thought of as simulation part of it at that time. Though physicists developed the idea of quantum walk, it was computer scientists who picked up as a very useful tool for search algorithms, like quantum walk based search algorithms, because it is evolving in a space very fast, at quadratically faster in Persian space, and you can use it to search something which you want in a Persian space, because it can spread, right? The classical can't spread, and they have huge simulation probability, options also. That's something which we'll try to. So now what happens here is, I said you can make your work dynamics complicated. You can start introducing more parameters, and what do I need to simulate if I have to understand a motion of something or a quantum particle in one dimension or something. I need to be able to simulate all possible properties. It's not that always spread in Persian space with quadratic speed. Can it localize? Can I control my property distributions? Only if you can control all these evolution operators, then you have some tool to configure your dynamics which might mimic some other physical system, right? So that's the first thing. So now what is the tool we have? If I have here, I have a coin operator. I didn't write as, you can simply write this as an Hadamard operator, which we all might have studied, you all might have looked at it 1, 1, 1 minus 1, 1 by root 2. It's always an equal superposition. But I can choose theta and have different superposition possibility, which means that with some lesser probability it moves to left, higher probability it moves to right, and all these things can be done. Now that degree of freedom, I can begin with some different initial state. I can use coin unitary operators can come in different parameters, right? I can choose a generic unitary operator with 3 parameters. Then I can actually control my dynamics. It can be very small, it can spread faster, I can have an asymmetry in my distribution. So that kind of tries to help us that you can have some control of your dynamics, which means it might help us to simulate some dynamics on one dimension, and this can actually be extended to 2 dimension. That I'm not going to talk about it anywhere here. So this is one version where you have a coin. If you don't even if you don't have a coin, because when I say coin, which means that it is representing a spin system, right? Spin up and spin down. There it might also be some physical system which doesn't have spin, right? It might just have to evolve in superposition without any spin. For that also there is another version which we call as a continuous time quantum walk, where you can have any random graph, any connectivity. So now graph would have vertices and edges. Now you can always write an adjacency matrix. I don't know, you might have heard about adjacency matrix. What it means that there's a graph structure, some vertices are connected, some are not connected. So now just looking at the points which are connected, you will put a value 1. For the ones which are not connected, it's all 0. You can write an adjacency matrix, like 1 if edges I and D are connected, 0 if they are not connected. Now that matrix actually is telling us how is my graph structure. Now if I am using that matrix to have some evolution, then it should talk about if I keep some particle in the graph, it should tell what are the possible routes for that particle to take, because the connectivity is what is help us to what should be the dynamics there, right? So in that way, I can always label them into computational basis of each path, and adjacency matrix, from that I can construct an Hamiltonian. So there is an identity, there is a diagonal matrix, which is one at all diagonal, and then minus an adjacency matrix, which would say how, what is diagonal? Diagonal means all connected, right? One to one connected kind. So when you have not all connected, like particular pairs are all connected in one dimensional lattice. So when they are connected, then adjacency would say which are not connected, and that difference would say what would be the path for it, and that can help us to have some Hamiltonian simulated. Then e to the power of IH, that Hamiltonian is unitary operator, and that is also one of the methods to simulate. So now you can have a dynamics of a particle which has spin up and spin down, 2 levels, or it may not have any spin. You can still evolve or define an evolution of that. So you can, even here you can control by adding weights to the edges, right? So the edges you can add some weight that would say what probability it might take that path and what it may not take, and that way it also will help you to simulate that's called as continuous time quantum walk, because your Hamiltonian is always fixed. It's only to the e to the power of IHT would describe the dynamics, right? So now I can also introduce disorder into this, because this is all spreading. There are some physical systems where nothing will happen. It might just remain there, but still there will be some small dynamics which is happening. So you can always introduce coin operation. You don't have to worry about, if you are not familiar with the mathematical expressions here, that's okay. But what it's trying to say is that at every position space or at every time I can use different coins, right? Because I have that freedom. Because when I'm trying to think of simulating, the system is under my control. So which means that at T1 I can choose different coin, at T2 I can choose different coin, at T3 I can choose different coin, which means that at every time I'm giving different probability for it to shift, and I can also define at each position I can give a different probability switch. Now this can also help us to say it might be some complex systems where at each lattice I might have a different element or different particle which have behaved differently, and that might shift in very different. So I can think of physical problems related to that. A spatial disorder also can be introduced to the system, or I can even use a combination of them. So what this does is that, this is just to say how you can have disorder, but what it does is that if you see, the standard version would give me a spread, but the moment I have started introducing disorder, it might be like 20% of the time you have random coins used, and the other time you are using a uniform coin, or have an 100% disorder. You will have a very strong localization, and you might have weak localization. It means that it may not be strongly localized, but it would still be like a classical behavior. But the dynamics interferences happen. The dynamics is still quantum dynamics here. So it's not a classical picture. It's not just a probabilities is going there. It was amplitude which had interference, and you still get some kind of behavior like this. Now these systems, it might just look like, what did we do? We didn't do much. We just had random coins there, and then I got some distribution. But they directly help us to understand some very well-known phenomena in physical systems. There is some phenomena called Anderson localization, and he got Nobel Prize for that. They talk about single electron localization in disorder. So you have an electron, and electron would be in some spread, but if there is small disorder, a very small disorder into the system, then also it ends up localizing. And that kind of is, when people were trying to study electron as a tool for electricity, and building devices like, it can be like your PN junctions or any semiconductor devices, the movement or the motion of electrons, understanding them was very, very important. And what is happening here is still a quantum dynamics, and there is a constructive interference at the origin because of disorder. And now that is what Anderson's localization talks about, and for which he got Nobel Prize long back for discovering, coming up with a theory to explain why people are observing localization there. So it simply says that you can now have such kind of algorithm, and you can simulate some systems, even like weak localization. There are physical systems where we see weak localization. Now we can actually map them to this dynamics, and you can say, now if I want to simulate weak localization, I can go to quantum computers and use this algorithm as a tool, and now I can vary various parameters and simulate them, right? So these are how it spreads, and then look at it. So this is only two examples. One of the other, one can actually calculate and then prove even from the algorithm's perspective that why it is localizing your group velocity. It's because there is always a dynamics of single particle. There is always an oscillation in that given region. There is interference, but it does not spread behind. So the group velocity will be 0, but not at that small localization. So that can be shown with some simple math. This is going to space. But there is some other, one of the other important problem for it. I'm not going to look at it. I can take a simple coin operation of some particular form. So these two gives me an identical output. I have I here, but here instead of having an initial state, I have I in opposite. So it's just like what is saying my initial state and coin operator, right? But this simulates something more interesting, other interesting thing. I can always do, these are all like my +2 mathematics, right? There is no complicated mathematics. It's just the notations we are writing it as Dirac notations. This is just a simultaneous equation. At any given point, position x, what was the state at its previous time, and then you try to estimate, because if I'm looking at this particular position, I'm getting a contribution of amplitude from the neighboring positions at the previous time, right? This is contributing to me, and this is contributing to me at time t is equal to +1. That's all. I'm just writing the state at one particular point x at time t +1 based on what was the state at the previous time in their neighboring lattices, because that's what contributes. This is just a, now if I simply write this equation, and then, okay, so it just went fast, and I try to solve this, like, there is difference operators, difference operator to differential equations, I can always solve them. I can convert them into differential equation. If I convert them, I end up getting a second order time and second order position differential equation of some particular form. Now this is only for one solution for one of them, psi 0 or psi 1, I can get this kind of solution. Now what it is trying to say is that if I have, it's just Klein-Gordon equation is a spin of spin 1 expression for in a relativistic quantum mechanics. So other than that, it also tells us this can simulate a second order time and second order position differential equation of this form. If I come across some dynamics where they say, okay, this quantum system dynamics looks like this, then I think, oh, I can go back to quantum walks with some particular configurations of coordinate shift operator, and I can simulate this differential equation and solve them, right? So that's how we try to look at simulation problems, what kind of look at it. And because it can solve some kind of or it can mimic some kind of relativistic equation, there was another problem which is very, very interesting, because most of many physical systems which we control in materials are all like described by Dirac equations, which is a spin-off particles. And this is a Dirac equation, relativistic Dirac equation, which as an Hamiltonian of the form, which is given here, c is your speed of light, m is mass, and this alpha and beta are matrices which define. So, I mean, it's most important for us, if you are not from physics background, it really doesn't matter. What is important for you is this is first order time and first order position differential equation, which has some mass and velocity term. But this was interested for physicists, like who study high energy physics. At long back, before the era of quantum information theory or quantum computing, people had looked at some problem called as Dirac cellular automata, where, because even then, when classical computers were developed, first thing which they have to do is, okay, will this computer help me to simulate some physical problems? So Dirac equations fundamental problem, can we simulate? So to simulate any problem, what should we do? Any continuous equation, you need to discretize them. And then only you can write algorithm and code, right? So they tried to discretize it, and this was a kind of discretization of the Dirac equation, which is there, right? So which means that I can have some unitary evolution where you have a 2 cross 2 matrix. I mean, it's not just 2 cross 2, you can alpha and beta also could be matrix, but in a simple form, it has some matrix where t minus is going from x to x minus 1, t plus is going from x to x plus 1. So you have t minus and t plus, and you have some components which are not having any movement to the left or right, right? So this was the pre-quantum information era, pre-algorithm era. But now, if I see the same thing from a quantum walk language, the coin and shift operator which I showed in my previous slides has this form, right? You have, the difference is that there is diagonal elements, even off diagonal elements having the shift operators. But in the real Dirac equations, the off diagonal elements don't have the shift operator, right? So it means that moving to the left or right. So now this is the fundamental. So if I have to simulate Dirac equation using quantum walk, all that I should do is that now I should figure out a way to modify my coin and shift operator, whatever it might be, is that this t plus and t minus won't be there. I just somehow get rid of t plus and t minus in the off diagonal terms, and then I'll be able to simulate Dirac equation, because these are betas and alphas would be like sine and cos theta, and that is going to mimic. Then it would also mean like my alphas and betas are associated with my like sine theta, cos theta. I have taken mass terms out here, but they are all like associated here, which means that using theta, which is my coin operator term, I will be able to have some information of mass there, velocity of speed of light there, everything incorporated into it. Now that's the problem which looks, but you need to see how I can map or reduce this to get this. If I can do, then I'm doing Dirac equation simulation. If I can do this, then many quantum systems which are described by Dirac equation can be simulated using this algorithm. So if I look at a pictorial way, why is this difference coming? Right, we can analyze them. First, we know there is a difference. Now I need to figure out why this difference is coming. If I figure out, then I can find a solution for it, right? So now if I see, I said to the left, I toss a coin, it's like superposition, right? I'll go to the left or right, and then again I toss, I'll go to the left or right. So if you see here, at every alternate time, the alternative positions are 0 occupancy, right? That's what is happening in the standard quantum walk simulation, which we saw with it. So that is what is giving us a probability distribution like this. But what is happening with Dirac equation is, if I'm breaking it into cellular automata model, along with going to the left and right, there is also a finite probability of our amplitudes getting just remaining at the same position. It is not evolving. And that actually we can attribute to the mass effect there, because the particle has some mass. Because of mass, there is some amplitude of it being there and some amplitude of it going there. Now, that would give me a probability distribution which is very different. Envelope might look the same, but there is some fine oscillations here which are differing here. These oscillations we actually attribute now to something called as Jitterbug oscillation in the dynamics, which is like the change between the two spin has certain pattern and there's some expression defining it, and that can actually be mapped to this small envelopes which you see. So which means that this dynamics is capturing something more than what didn't exist. So if I can manipulate this to get exactly what it is, then I have successfully simulated them. We can do that in a bit easier way. Of course, it took some years for people to come up with a solution. So I need to have an amplitude of it being at the same position. So instead of just evolving to the left and right, first time I toss a coin, then I say with certain amplitude I stay back and with certain amplitude I shift. Second time I toss a coin, but I will do the reverse of the dynamics. Then after this is a split step, right? One step would compose of 2 small steps. Then I will have some non-zero probability at all the 3 position space. If I just repeat them hundreds of times, then I would end up, I just like coin and shift operator, because this is moving to the left and moving to the right. Identity would mean that it will remain at the same space. If I just combine them together and then write an expression, I will end up getting exactly what the Dirac cellular automata model had given. Like off diagonal elements will not have any shifting, diagonal elements will have shifting, and I can choose specific theta values. I can choose the theta values which would give me, which would overlap with what the cellular automata do, but it would also tell me that what parameters are, how I am mapping my mass and then C are not under my control, that is with the physical system. But I can use theta, which is under my control, to represent different masses and different speed, and I can change change theta and then simulate the real parameters which are not accessible in such kind of system, right. So now this kind of says that you have in a simple one dimension you can actually mimic a Dirac equation, and there are a lot of papers which had been written after that, try to study how you can look at in higher dimensions, how you can simulate some field theory problems with it over time. Now that's one of, but another example is the neutrino oscillations here. That's another. See, now when I say I can simulate Dirac equation, then there are so many systems in nature which are all Dirac equation driven. I now have to figure out how do I bring them into picture and then start looking at it. So again, there are details of the physical systems there. We may not have to go into too much depth into it. These are a well established phenomena which are explained in field theory, quantum field theory. There are neutrinos, there is oscillations between them. There are always 3 flavors, there are 3 flavors, mu electron, mu and then tau, so mu e and so they correspond to charges of leptons, and there is always some oscillations between the flavor which happens. And that changes there. The standard model which were developed, they predicted that neutrinos are massless and they are very weakly interacting particles, but experimental observations disagreed with this. That's why people have started thinking of modifications to standard model, and people are exploring various other aspects for it. There are some corrections. What the experiment says is that there is some mass associated with the neutrinos. So they are massive and the leptons mix during the dynamics. So now people are trying to look at so now can we use a simulation systems? Of course, it's not that simulations has predicted something significantly different right now, but it's an invitation for us now to say we can try to simulate them and see if we can understand something better than what it is known. So if we write down the evolution, again, this is just the slide which may not be very relevant, but I will go to the next, the quark slide. But this is just a slide which describes the way the textbook's definition of neutrino flavor simulation happens. You have different flavors, you can write them as a superposition of mass eigenstates, and there will always be unitary operator just trying to mix from one flavor to the other, and then the flavor oscillation happens. And now those unitary operators can be broken down into the mixing of the flavors, and you can always have the cos theta, so the terms there. But these, what is important here is you might have all this eigenstate. These are the mass eigenstate of Dirac Hamiltonians. So that's the only key point which we have to take, which means that there is a spin which is spanned by 3 flavors, eigenstates, which are represented by Dirac Hamiltonian. I will only now take, from this slide, what I would take is that now there are 3 flavors. All these 3 can be represented by Dirac equation. I should come up with dynamics such that there is a mixing of this flavor and I have to get some probability output, right. So that is a take home message from me from this understanding of the little math we have of the neutrino oscillations from this slide. So and the dynamics there, right. So what it would do is that I have this mixing, which means that when the evolutions are happening, there will be some initial state 0. After certain evolution, I will end up having some state, and I can make a measurement of them, the propagation, when I have a propagation. At the end, what I should get is the probability of a transition from one flavor to another flavor at any given time, right, because the dynamics is happening. Once the dynamics is happening, at every time I can actually now think what is the probability of flavor change from one to other, and that's what is happening. For us, the important is this is what we should get, and then in as is mentioned in the previous slide, okay, so we begin with the mass eigenstate and then some initial state, and then come up with, okay, okay. So the simple approach for that again would be like, because I have 3 flavors, I have 3 Dirac particles if I had to begin with or something, then I would have 6 possible configurations to write them, right. I can take 6 levels for representing, right. It may not be 3 qubits here completely, but I can say there is 6 level of representation because each one would have 2 flavors. I can label them with the 6 basis state. Now I can break them into a spanning of 1 and 2, 3 and 4 and 5 and 6. I can describe a coin operator which is the sum of addition modulo the form, or like this, sorry, the sum of the 3 flavors separately, and then I can define a coin and shift operator on each one of them independently, right. Then at every time I have to come up with the dynamics. The coin would be of this form. So we just start to think of what is the mapping. I can take state 0, 0, 0 and call it as 1, 0, 0. Now I am taking a 3 qubit mapping. I will take a 3 qubit system, and then I can take 0, 0, 1 and make 2, and I have represent. So now what is the number of bases I am having for 3 qubit system? I will have 8 possible configurations, but here I am only taking 6. 2 of them I can make a dummy, right. I do not need them, I am not going to use, but I will just choose 6 bases of a 3 qubit system that should try to represent the 6 possible probabilities of what I am going to get from the 3 flavors with time. And I have to define a shift operator. There is a coin operator which is telling me going from 1 to 2, 2 to 3, that is represented with this form, and the shift operator. So this is what I said, you can make them 0, you do not need them. Then you have a psi 1 and psi 2, psi 3, which is a superposition of these 2 flavors. So it means that superposition of these 2, superposition of these 2 and superposition of these 2 are the initial state, or like the possible state basis states for each of this flavor, right. So what we did is, instead of we take the 6 possible probabilities which are going to get, map them into 3 qubit system, and then define a coin and a shift operator for that, then try to simulate their dynamics, that is all. I just have to do a coin and shift operator continuously with time, and at every time calculate the probabilities, right. This is we get by using a quantum walk. After a large number of steps, you start from one flavor, other flavor would be 0, and they will get an amplitude, and this is the short span of time, but this is what is there in the experimental or like the people who are looking at the real experiments, which turns to about like large length with high energy dynamics. This is like hundreds of kilometers of experiments to get this data, but you can simulate exactly the same probability outputs by using a quantum walk dynamics. Now these are all like done in classical system itself. We don't have to go to a quantum computers to try to understand, but it's trying to give us an algorithmic approach. If we can simulate them here, then we know that the dynamics is mimicking it exactly. Then that will help us to pick a dynamics which are complicated and you can't, but it's still defined by the similar systems, which you can't do it in classical system. Then that will give us more confidence to take it to a quantum computer and look at it, right? This is another example of how you can pick and look at it. Now, if I had to look at this dynamic, we are only talking about dynamics, then we need to think of translating, because in the beginning I had put a slide. First you need to pick a physical system and then you come up with an algorithm. We did that step. After I do that, then I should come up with a circuit for it. Only then I can implement it on a physical system. I'll just try to take one step. If I have to build a circuit, then what should I do? My coin and shift operator, whatever I took, should all now fit into my set of basic universal gate operations which we are talking about, right? The single and 2 qubit gate operations. I need to do some mapping here. We'll do that mapping. But these are the operators which whatever I've taken there, coin, shift, coin and shift operator, they should all be implemented using this, right? So first thing we should do is that now if I am taking a walker to walk in a position space, if it has some like 15 position space, I need to say what is the minimum number of qubits required to represent them. I can take a qubit basis, like if I take a 4 qubit system, then I can represent some of the configuration, each basis states of 1 qubit with some particular position space. You can choose different mapping. This one of the mapping which we can choose. Now which would mean that if changing my quantum state from this to this, which means the state is evolving from -6 position to -7 position. If it's going from 6 to this, then so it means that if I'm doing a quantum walk operation from here, it will be a superposition of this state and this state at the next step. So that's what it means. First is, now I choose my qubit. The mapping, I can choose any mapping, we can just ignore this part. Now I need to think of a coin and shift operator. What did it say here? All that it said is I should bring a superposition of 2 states on a given position and then move to the left or right, right? So I can come up with, of course, how we come up with slightly bit involved, but the moment we look at this mapping, all that is needed is the change of the basis states, switching of the basis state, because my particle is evolving. I can always introduce a coin operator like your any like any single qubit operation on the particle which is evolving. That can be 1 qubit. This is the position basis. Now I need the 5th qubit. This is my particle which is walking and this is my position basis. So this will be in tensor product of this. All my coin operations can be just done on this particle, this one single qubit I am going to take, and then it is only the shift in position. Now shift in position space can be manipulated using the controlled NOT or controlled control NOT gates or controlled gate. So this gets complicated, but if I have different schemes of walk, because we said we can have coin and shift operator, I can have combination of single and 2 qubit gates. So there are various different methods to have first step, second steps and all of those things. So you can come up with many configurations, but then what happens when the next level is I have to talk about going to an hardware. If I take these complicated circuits and speak to any experiment, even in our own lab when we are doing experiments, if I look at these circuits, I said no, we can't implement, because you need a lot of resources to do that. You need to come up with some simple ways. Of course, there are some simple configurations. Of course, we can come up with simple circuits to mimic them explicitly. And looking at the ion quantum computer system, so we could come up with some circuits to implement few steps. This is only involving 5 qubit system, but the real hardware used 8 qubits as an ancillas. So few steps were implemented. So if you see, even to implement these few steps of Dirac simulation, you need about 70 single qubit and about 30 2 qubit gate operations, right? So that's the resources needed. But in existing systems, you can implement up to some level, but it is well, so you have the experiments giving you, and this is the theoretical, like computer simulations, classical computer simulation, but is a quantum computer simulations, it gives an exactly similar approach. So this is one part of the story, but then you can see more complex, like Dirac equations are also described in curved space time, right? Now you can actually even capture curvatures all in your coin and shift operators. But then the circuit becomes a lot more complicated and the current computers are not ready to handle them. Right? Theoretically, it's a bit more easier to come up with and come, and then the moment you look at the hardware development does not happen in the same line. So that's, but what it's in principle saying is that you can come up with various configurations of the dynamics, and then you can build circuits around them. You can implement them at the small scale as a test of it, right? So how much time I have? Almost 5 minutes. Okay, so I'll try to. I think I'll just quickly run. I'm not going to detail, but this also helps to not just looking at simulating systems. There are some, we all do this Google search, right? We give search and then there's a ranking. I mean, I'd say which page comes first, which page comes second. There is a page rank, Larry Page algorithm. But then the quantum version of that can also be described using quantum walk. Because what does quantum walk do? It again goes along all the nodes and identify. Now, I can have some nodes which has a lot of amplitudes coming in here, and then some might have less. Classically, what happens is that, so if you have some complicated, here these are all like binary tree, there is no much interference there. But if I have some complicated structure like this, there might be some nodes where you have many inputs coming in, but that might actually lead to a destructive interference there. The amplitude might be less in spite of many modes coming in. Somewhere else it might be there. So if I am taking, this is just an example of, it may not be very clear, there is a classical and quantum dynamics on a similar network. There, quantum gives slightly different priority over the classical. There are some examples, we could look at it. It's because the interference which happens in quantum system is not captured in the classical system. That gives a different ranking. So if I am trying to simulate or trying to identify some chemical complexes or some dynamics where there is some interference which is happening and what points have priority over another one, classical systems can't do. So now this was looked for as a very simple problem, like nothing to do with any physical system simulation. But interesting thing was this algorithm, where again every node you are defining a coin operator and shift with some complexities, of course, but the simple term is coin and shift at every node. That actually helps us to even simulate the dynamics on some hydrocarbons or anything. Like there is some electrons, when you have all these hydrocarbons, there are benzene rings in different configurations, electrons hop from one ring to another, and there are certain nodes which we call as highly reactive centers and others are not. Right? Now those reactive centers, all that we have to do is that go to standard first chapter aromatic hydrocarbons textbooks and then see what are the weights or the bonding which they are trying to define, map them into weights and then implement an algorithm. Then it identifies certain nodes, gives a ranking for certain nodes, which means that the nodes which have higher ranking are the highly reactive centers and which are not. So it is a direct mapping which you could see by using such kind of quantum dynamics in the system, right? So for all this, it was just implementing or transferring the algorithm to this chemical structures and then mapping them, and everything matches with what has been there in the standard textbook thing. So it kind of says that you are in a right track to understand, simulate dynamics which happen in quantum system using a quantum principle in your evolution. Okay, so there is, I'm going to skip most of them. In similar way, there is open systems. I will look at it, but there are people have tried to look at open systems which means that you will have some unitary evolution, some noise associated with it, and that can also be introduced in your algorithmic form. And you can say this is the quantum and the classical combination together, merge them and then again simulate them and split them. But this is one of the, it's a very debated problem. Even today there has been hundreds of papers which people talk about photosynthesis and chemical complexes. In 2010 they came up with the quantum walks, gives you a very effective simulation of it. And why these are important is that, when we are thinking about solar cells or when we are thinking about designing materials, first is we need to understand some things which nature is doing more perfectly than our engineered systems, right? Nature does photosynthesis very well, efficiently. And there are algae which are in sea, which are deep inside, and they just get 1, 2, few photons in a day, and then they efficiently convert them. Their conversion ratios is around, or conversion efficiency is more than 80–90%. We have not built any cells which are more than 20–25%. It could also be because we don't understand dynamics well. If you can understand first, then I can mimic them. And in that attempt, so they picked up one chemical complexes which is FMO, and then they tried to see there is light falls in, there is a dynamics which happens, there is a quantum wave dynamics which is happening there. There is also environmental effect, right? So that gives a directionality and goes to reaction center. So this can be mapped into some nodes and then see how they can go, and then they can look at it. So they did come up with some mapping of algorithm to simulate them, and that is still been contended by a lot of biochemical researchers who say might be there's something more missing, and still been papers written on them. It's because the problems remain open, and I'm not saying that there is a solution or there is exact model and this is solved, but one can actually consider, people have, and we also try to consider such kind of problems, define the dynamics with whatever limited information which you have, forget all these dynamics are there, and then try to come up with the quantum circuits for them, right? So it means that even if I know the model well, if I know what should be the dynamics which is happening, all that I would need is roughly a 3-qubit system. I don't need more than that, but I still don't know what operations efficiently I have to do. But whatever little we know, even to mimic the dynamics on a 3-qubit system, I need a very complicated quantum circuits, the gates operations. There are two problems here. Again, still, can I optimize this circuit to the best so that I can mimic? Optimization is another problem. And then is whatever model we have is better. Can we, after we do that, can we go back and then correct the model, improvise them? So in that way, the science also evolves, and we can also try to come up with the most appropriate solution with time. I think I will try to stick to time, and thank you very much. So questions?
So there's a question, how do the coin angle theta and the initial coin state parameters delta and eta affect interference and localization in the discrete time quantum walk with evolution u is equal to s, then c theta tensor product with p?
P.
Yes, I think it is.
Oh, IP, identity and the Persian space or something. Okay. So what so the thetas for localization, you need to have different theta at each position. So then what happens is that the interference, which is end up being constructive towards the origin. So that's what it is. Means like when there is 3 parameters there, they're talking about theta and then delta and then eta. So now delta and eta only affects to vary the amplitudes of the peaks. It does not help you to control the spread in the Persian space. Theta is the one which is affecting your spread in the Persian space. So the delta and then eta, delta minus eta is what defines these probabilities. You can actually make it asymmetric. Theta defines the spread in the Persian space. So now if I start making only theta random, you can have any delta eta, it doesn't matter. The moment I start making theta random, my spread starts becoming closer to your origin, and you end up having localization. I think that's probably the. Okay, so thank you very much, and.
Thank you so much, sir, for sharing your valuable insights with us. Can we have a big round of applause for sir? We are truly thankful for your presence, sir. As a mark of our respect and gratitude, now we want to present a gift to you, sir. Please accept it from our side. Now we will be having a short break. After that, we will continue. Okay.
The next talk will start from 11:30 after the tea break.
Now moving ahead, we have with us Professor Chiranjib Bhattacharyya from the Department of Computer Science and Automation at the Indian Institute of Science. His research interests are in foundation of machine learning, optimization and their application in industrial problems. He has authored numerous papers in leading journals and conferences in machine learning. Some of his results have won Best Paper awards. He joined the Department of CSA IISc in 2002 as an assistant professor. Prior to joining the department, he was postdoctoral fellow at UC Berkeley. He holds BE and ME degrees both in electrical engineering from Jadavpur University and the Indian Institute of Science respectively, and completed his PhD from the Department of Computer Science and Automation, Indian Institute of Science. He is also a fellow of Indian Academy of Engineering. So today's session will be a three-part talk exploring different directions in quantum machine learning, which is an exciting and rapidly growing field. The three parts are as follows. Number 1, quantum machine learning, a survey of ideas. Speaker will be Professor Chiranjib Bhattacharyya, Department of CSA, IISc. Number 2, short frugal quantum machine learning, and the speaker will be Abhay Shastri, postdoctoral fellow, CSA. Number 3, DOEM, learning density operators of quantum latent variable models, and speaker will be Adit Vishnu, PhD student, CSA. This three-part session will begin with an overview of the rapidly emerging field of quantum machine learning, followed by 2 presentations highlighting specific research areas, one on supervised learning and another on unsupervised learning. We are truly honored to have all of you here. I now invite Chiranjib sir on stage.
Thank you very much. Somebody can somewhere some connector. Ah, oh great. Huh? Mic? Hello? Yeah, good. Right. Play slideshow. Okay. So good morning to all of you. Mine. Okay. Thanks for the introduction. Delighted to be here. So we thought, why come alone? We'll also took some of my colleagues, co-authors, students, and postdocs. So three of us would discuss this interesting area of quantum machine learning. So it's a nascent field, and we are very much learning and in introductory stage of learning. So so this you can think about it as a broad survey of ideas, and given there's 90 minutes, a lot to cover. So what I have now gone for width than depth. So what, like you can gain to take away that what are the key papers, what are the key highlights, that kind of thing. This to help you motivate going forward, right? And we'll also present, so we'll present, what I will do is I'll present existing work, some of the highlights. And then Aditya and Abhay will present some of our own research works which we have been engaged on. Okay, so with this thing, of course, thanks to our collaborators, all of them are involved in one way or the other, and Professor Apurva Patel has been a pillar of support for me in learning quantum. So why are we doing this? Obviously obligatory slide, this is the year of quantum, right? So there's a lot of promise on quantum, all right, and that is, so this is a very, very important era we are entering, that what can quantum computing do? Maybe this is not the right audience for this, but anyway, this is just to show you that every day if you look at technical news, you hear this kind of releases, right? 1000 qubit quantum chips, there's quantum advantage, and so on and so forth. So that being said, now I work in the area of AI, machine learning, the foundations of it. And now this is the news I track. So for example, last July, last week of July, for example, it was just amazing that models, these so-called large language models, can win gold medals at Math Olympiad. So why is this happening? It's an exciting thing to be an AI in the field of AI, right? Now, and of course, that's just in Math Olympiad, but it is going in all fields. For example, drug development is another very important area. This is just for an example, but AI will enter all aspects of our life, as you see, as you have seen ChatGPT and things like that, both scientific and our standard life. So now. But at this point, I don't see any connection between the two. Quantum computing is emerging on its own way, everywhere is important. Generative AI, we are seeing it, right? But there's no connection. This is sometimes I think there must be connection. That's what these are questions I ask and debate. And my research is governed by that, question. So obviously, these are questions everybody to ponder, and I don't have good answers for this. So one thing to say generative AI and quantum is, but what are the promising directions where we can do meaningful research and will have industrial impact, right? So now industrial impact is one thing, but then it should help better our lives. So what are those problem areas where we should target this research effort? Things like this, right? For example, but more importantly, can you just not the application of it? Can you characterize those problems in some way? What characteristics a problem should have? Where I can potentially see some very useful things which I otherwise couldn't have done, because and you could have done it because only there's quantum, right? So we'll also present to you some ideas as you can go along. So some of them are not very clear, that can it be done tomorrow? You know, as most of you know who are who have a little bit of understanding of quantum and things think that they feel a very speculative field, right? It says that, oh, if there's a machine will be built and I will do great things. So it's very important also now, but now, especially in the last 5 years, if something like, as you see the press releases I saw, all coming from companies. That means it's no longer an academic exercise. Now that means it is going to impact industrially. In fact, industrially cannot wait for like after 10 years something will happen. That means it's here and now. But then are these ideas here and now? So that's the question we are having, and when I'll share some ideas with you, not that I have great answers, and hopefully some of you will, in the future elaborate on that. So now, there was a slide I showed about generative AI, right? This is something very close to my heart. And what I found after reading many things, right? As of now, I would love to know a single generative AI model which is suitable for quantum computing hardware, which can do meaningful things. It is one thing to say I want qubit, 2 qubit, I do things, which is fine. But can I do some meaningful things with a standard in a quantum computing hard setup, right? It is also not very clear that now, as you can see, generative AI, you say, right, there are very powerful models, diffusion model, all that, those of you know. Now today you can go to ChatGPT and say, create an image and things like that, create a video, it will do that. Behind that, there are very powerful models running. Now can this compete against that? I am not at all sure. And maybe it's not because it doesn't have the potential, but maybe we haven't understood it. I haven't understood it, right? And but the main challenge I see is that essentially most of it is based on, so when you say machine learning, there's a quantum computing hardware. So what is the intersection? Intersection is you put up parameterized quantum circuits, PQC. And my own understanding, that is the problem. Because the PQC as of now, my computing support is very weak. And we will show you what are the problems people are facing with. And maybe that may be one of the bottlenecks. But anyway, that's not the point. Point is that, can I now, does the bottleneck invent new things? Or if the bottleneck can solve the problem? That's a research agenda it is, right? So I'm mentioning these points is because I would like to showcase some of these highlights which touch upon these points. May not be very exhaustive, but this is the underlying things, right? So maybe I'll just not belabor this point, which I already said. So basically, it is aimed at non-experts in ML, right? But they are somehow interested in understanding quantum computing and how can I work in the field of ML, right? So that's the broadly QML. But QML doesn't have a definition as of today, right? So as I said, I would not be exhaustive. I would like to, I said again, I would like to give you a broad canvas of things people are doing. And of course, it will be selective, and I'll try to be as like as precise as possible for the references. But I'm sure many references I'll miss. You can ask me later for references if you will. Anyway, so now to talk about ML, as I said, non-experts to ML. So what I thought I'll do, divide the talk into the following. We'll very quickly go over some standard ML primitives, machine learning primitives. Just to set up the, let's say, you should not take this as a class in that, but it's more like to build vocabulary, which follows next, right? Then you will use those primitives to see what people have developed in the context of quantum, right? And then we will present, Abhay and Adit will present 2 of our research efforts in some of these, and hopefully those things will become clearer as we go forward, right? So that will be the agenda. And then it's 11:35, okay. And I have to cover all this between now and lunch. It's a very bad thing. So don't want to stand between lunch, right? We'll see. Okay. So what we'll do is we'll cover. So basically, as machine learning has a many different paradigms. But most most widely used paradigms are two: supervised learning and unsupervised learning. Many of you know this. So what I'll do is you can use this. So we will quickly go over this and use it again. I'm saying as more like a key definition ideas. Right? It's not a course in itself or something like that. Right? So I'm going to cover some of these things, and this is one thing which you're doing, which goes to our research as well. Now, so the power of generative AI comes from what are called latent variable models. We'll explain it at some point. Now, to learn the latent variable models, it is not easy. Okay, is not only intractable, but there are many intractable problems. But you can quickly find some good approximations and things like that, where I can quote unquote, okay, I don't know how to solve it exactly, but can I solve it approximately? Can I run code on it, even if I can't give you guarantees? So towards that end, a very important algorithm called expectation maximization algorithm, EM algorithm. This is one of the key algorithms in machine learning. So any Gen AI model using EM algorithm, you can interpret it as an instance of an EM algorithm. So what we thought is we'll take this EM algorithm and can you reimagine in the context of quantum machine learning, right? And then Adit will talk more. What I will do is I will discuss this EM algorithm in the context of latent variable models, and we'll also introduce something called Boltzmann machines, an idea which came from physics. Okay, so that being said, now change of slides. Okay, so we start with view full screen mode, hopefully that. Yeah. This is notes I was making, right? So basically we would like to cover these 5 things. So first is the perceptron algorithm. So this is an algorithm of 1950s. So those days there were no social media like today, no Twitter, no breaking news, all that, right? But in 1950s, there are a few scientists in the MIT, and there are others, of course. They came up conceived of a machine using a very rudimentary definition of a neuron, and they called it perceptron. So perceptron means it can perceive things. That was the hope, and it was all over the news at that point. And of course, many of the success we owe today is because of them. But anyway, that's not the point. This is talking not about discussing the perceptron network and all kinds of other things. But now the question is, for the first time demonstration was made that can I learn from data? Of course, we always fit models to data. That's not the point. But can I learn from data to solve a perceptual problem? Can I see? Can I classify images? There's no physics to it, right? The first demonstration. So we'll talk about this algorithm per se, but the algorithm has many other ramifications, especially in optimization. And then like at least 30-40 years later, something support vector machine emerged. Like at least in the last, in the 90s, it was a huge rage, and even early 2000s. We'll introduce something called kernel functions. And then these are ridge regression is, those of you know statistics, it is an algorithm for fitting models using the least square sense. Okay, why ridge and all that? That will take me some time. I have not just take it as a name, and we'll just review the definition of it. And we'll now whatever written here, we'll now to have a kernel reinterpretation of this. So that will be the agenda for the next 15-20 minutes. Okay, so now the idea is so supervised learning, right? Supervised learning means what? That is, I give you a data. What is data? An image, a voice sample, something like that. So now you can think like this: whatever you do, you give me a sort of vector. That's one way to think about it. You give me an image, but it's fine. But by the end of the day, there's a vector, which is called features and all that. And you also give me supervised. What is supervised about it? Now you also tell me, oh, this image is about a cat. This image is about a donkey. This image is a monkey, and things like that. Now you give me show me enough images like this, cats and dogs and all that. Now can you build a machine which will take an image and tell me what is that label. That's the problem. All of you know that. Right? So, into that end, let us say that xi's are my images and yi's are the labels. Cats, dogs, monkeys, things like that. Right? Now, I have to create for you a function which takes in xi, an image. X is an image and it will give me the label, the cat, dog and things like that. So, that is called a classification problem, right. Now, the simplest thing you can think about is, can I create a linear function on x, linear function on x. Here I do not know w and b. Now, the job is to, you give me a data set, you go into the field and collected many such pictures, it's a capital N number of images, 1 million images you have covered. Now, from this can you figure out w and b, right. Now you see, if you figured it out, w and b some way, so what should the machine do now? The machine should do is, now if I take this machine and take it to some unseen images, it should give me the correct answer. Now you see the fields it interacts with now. First, I have to go and collect these images, that's fine, that's more like on the field, something like. Then I will present them in some way. So which field is this? Signal processing. Gives you my vectors. Just to understand the things as it goes on, right? Now once you have that, then I need an algorithm to figure out w and b. And you say that I know from hindsight that you as humans learn, you just show me one image, I won't be able to tell you, but you have to show me 10, 15 images, many images for that matter, right? So the algorithmic challenges are, more images you show, I should get smarter. That means I must have the computing ability to learn from it, or finding w and b's and things like that, right? So that it heavily borrows from various fields. Before I mention the field, the other thing is that the core idea is that I'm even given WB, I should be able to measure how good is it. So all this borrows heavily from the field of statistics. Statistics and optimization thus remains one of the cornerstones of this field, right? But now let us say that we don't worry so much about how good is it in the field. At this point, I am quite happy learning W and B in a meaningful way. So, it's the first meaningful way then, that can it fit the training set? Let's call the training set. That's the first meaningful thing. Now, that may or may not be always a good thing. But anyway, that's a different discussion. So, here's a quick algorithm. So, the algorithm should be such, that there is a W and they should exactly match this thing, right? That's what we discussed. Now, let's assume there is a W which realizes this. See, if there's no W, there's no point fighting it, right? Let's assume there's some W which achieves that. Let's call it W star. Okay? The fact is, but you don't know W star, right? That's the challenge, right? So now convince yourself that if this happens, right? The sign of that number, this is a number, right? The number should be equal to yi's value. Let's assume the labels are 1 or -1. There are only cats and dogs. Cats is 1, dogs is -1. Okay? Then if that equation holds, this will hold, right? Now, obviously, this is strictly greater than 0. That means, there is some number gamma. You can that's obvious. So basically, now I say that, so we call such data set linearly separable. Linearly separable means a linear function can help you identify them exactly, right? Now, that means such a number exists, right? Okay? Okay. So now, so now here's a nice algorithm. What does the algorithm do? Let us say, I have to learn W and B, I have to figure out. And let's put B to be 0. In this equation, I put B to be 0 for exposition's sake. So B is 0. Find out W. Put all the W's to 0. Starting point. Okay. Let's say it's iterative algorithm. Let's say at the iteration k, I have a guess of Wk. What is going to happen now? Now, in some of them, it may be good, and some of them it may be bad. So what you do is you run this WK classifier and find out an example on which it's bad. What does bad mean? They don't match. They're 1 or -1, right? Okay. In that case, this has happened. In that case, this has happened. This is greater than 0, right? Discussion was if it is right, then there is no such L for this is less than 0, right? Now, once you so that means on this LH thing you made a mistake. moment to find a mistake, we just add this thing, just add the mistake. Simple algorithm, easy to implement, right? Okay, great. But is it any good? Now here is a very powerful result. Powerful, but very simple to prove. We will not do the proof, but right. So for example, we can show that if the data set is linearly separable, what does that mean? There is some W star which would exactly do that, right? Then this algorithm will stop after at most R square by gamma square mistakes. That means it will really find one of the classifiers on which it will give you a classifier which is cats and dogs are properly classified. 2 lines of code. Advantage, that is, thing like this is also used for big data, right? N is very large. All I have to do is I just have the ability to look into the data and see is it right or wrong, correct? So this is famous called the positron algorithm, and see now if you want statistical guarantees, that also exists in terms of leave one outer, but as I said, we will not discuss this more. This I just put forward for you to study more, right? But now, so let us say, so how many oracle calls you think it will make if there is a data set like in one pass? I have to find out the mistakes, no? In one pass, how many oracle calls it will make? Oracle means how many times so it's a big database, right? How many times I'm probing the database? In the worst case, it can be n times, no? To find the example, I'm finding one example, right? In the worst possible case, I have to look for all the examples, no? So in the worst case complexity is like n R square by gamma square, right? So please remember this result. Okay. So how am I doing in time? 11:50. Okay. So maybe 1, no? See, I'm really optimizing. Okay. So yeah. So now once you have this gamma, it says you can show that R square by gamma square, you got the term, no? And what do you want that term to be? You want the algorithm to finish very quickly, right? Right. Also, there's one more thing. Though I flashed it, other thing is that this gamma also has a role to play in terms of statistical guarantee, right? But the long story short, larger the gamma, better it is. Okay, and this is sometimes called large margin classification. Okay, yeah, long story short, this gave birth to the thing that okay, why are you now not using? Can you now figure out that classifier which is the best gamma? How is gamma defined? Gamma defined in terms of W star, no. Now there is also a relationship, there is only one, not one W, there are many Ws. So among those Ws, which is the best gamma? Can I now find this? Now that's possible. But then I have to know a little bit of optimization. So you have to solve a problem like this. This is called optimization problem. Let's not bother what it is. But let's say this can be solved easily. Not easily, today's day and age is there. Okay? And now the optimum value of W can be written something like this. So W star written as alpha is some scalars, yi, xi's. Alpha is the numbers. Remember the update you saw? It was something like yi, xi, no? So these are like scalars, all y, xi, right? These are the same form, right? This is not by accident. There are things like that, right? So end of the day, one can finally solve problems like that, and that's your classifier, right? Okay. Okay. Now, so to solve that problem, you have to use something, as I said, in optimization. This is called quadratic program. But these problems can be reformulated in many ways. One of the very interesting reformulations was what is called the least squares reformulation, where what you do is, you solve a problem like this, inspired by something like this, right? So what is least squares about it? Least squares means you have to find set of parameters which minimizes a squared objective. Least squares, right? And that goes down an idea, Gauss, Newton, many of this. And that's the first thing they did. At that point, they did optimization, but that's the thing they solved many problems, right? So now least squares problem like this would turn out to something like, this. I've written it out. So basically, so now those of you know a little bit of fitting least squares. This is like what is called as normal equation. Right, normal equation, these things will look like this. So a matrix, they have to solve this. Basically, the optimization, the computing problem becomes finding, B alpha and all that by solving this set of equations, right? A linear set of equations. Let's just invert this matrix and you get it. Okay. So what is the computation challenge here? If you wish to know, so what is the big deal? Big deal is that if n is large, how do you solve these things? Okay. Now this one way of looking at it. Now, what is the difference between the previous one and this one? Many statistical differences, but mainly this will also give you a classifier, right? But the computing tools I require are very different. These are least squares fit. I don't need optimization, all those fancy quadratic program and things like that. It has its own benefits. Fine. So these are some of the things now. So important, interestingly, these can be solved. So if D is the dimension of this thing, and it is the number of examples, time complexity of solving a problem like this can be written as something like d cube plus d square n log 1 by epsilon. Epsilon is the accuracy which you want to solve the problem. Fine. I think this is to be noted. Why? Now the field is speculative, no? Moment I say something in quantum, they said that, can you do better than this? That's why these things are important. That's the field as of today, right? But actually, one should go one step more and say that I run code and I say, can I see? That is a real engineering thing, but as a first step towards that, okay, this is what you are saying is a theoretical construct. Now I do quantum this, that, can you beat it? So that is the thing, that's why these things are important. And I think this is one point you want to note here, right? Okay, so maybe I'm just running out of time, so I'll not say kernels, maybe I'll leave that to Abhay. So maybe I'll just go over this regression a little bit. Again, so this becomes, so basically now, so regression problems are often, can I fit a linear function on observations, right? So I know if I measure pressure, temperature, humidity, and that has got something to do with some other variable, let us say well-being, your blood pressure. So and assume it's a linear function, right? So that can be modeled as something like this, right? Now that approximately can model something like this, that can you find W so that minimizes this. This is exactly the least squares formulation, okay? Now many of you know, this is like a best fit model, if X is the matrix whose columns are whose rows are the columns of, whose rows are the data points, let's say each of the vectors, right? This W star will write something like this, using the same update which you showed previously, Now what is the problem with this? The problem is this, that this matrix can become ill-conditioned. It may not be invertible. Okay? One simple algebraic problem, code will not run. Okay? Now to that, so then what is the fix for that? Fix is that what you do is you just add something like a small constant into norm W square. It's an algebraic fix, but it's also a statistical interpretation. This is famously called the rigid regression problem. But this is only one side of it. This is just the computing side of it. But there is a statistical meaning behind this as well, but let's leave it there. So this is, as I said, this would be our definition of what is called as rigid regression. Okay? But all of them, what is the idea now? All of them can be solved by the same least squares module, right? Whose complexity is d cubed and all that stuff. Okay? Right? And that's where we take it up from. So kernel, sorry I didn't cover this, just a lack of time. So kernel methods can be applied to this problem. By what I mean is that you had your x's, right? W transpose x, right? Now I can use, and what is the tool for solving? Maybe a least square solver, maybe an optimization solver. Now kernel does some magic here. With no rise in computing cost, I can solve the same problem in a very different space, nonlinear space, W transpose x, right? So I can also solve it with phi of W transpose phi of x. I can do that. My optimization problem still remains least squares, quadratic program still remains quadratic program, and things like that, right? So that is the idea behind this. I'm sorry I couldn't spend more time on this, but anyway, this immediately allows me to do nonlinear things, right? Okay, now 12 o'clock. Okay, I was planning to give Abhay by 12:10. So then, okay. So here, so now let's quickly move to unsupervised learning, right? Unsupervised learning, what is happening? What is the difference now? As you can see, supervised learning means where supervision came from Wise. I don't have Wise. I just dump on you collection of images. I haven't told you it's cats and dogs. Now what can I learn from? It's just like somebody gives you a lot of books and says go study and be wise. Right? So now that's a very ill-posed problem, and there are many disciplines, directions and all that, right? So one of the ways people have thought about it is assume that these data points are coming from a distribution which you don't know. And this is exactly the generative process. There's a generative, there's a nature which is generating things for you. You don't know that process, right? Now the game now, if I want to think like this, then I see. Oh, this is a distribution coming from this. So now can I figure the parameters of the distribution? And how do I know the right distribution? I don't know, I guess. Oh, it's come from a Gaussian, very simple. Moment I make that connect, then what is the next thing I should do? Figure out the parameters of the Gaussian. Okay, that is basically the idea, right? And now latent variable models are a little bit more interesting. It says the following. There is a probability law between on two variables. One is you observe, another you don't observe. X and Z. You see only X's. But there is a hidden variable Z which you have no access to, but you know it exists. Fine? This is called latent variable model. What is latent about? Latent means hidden. Z is hidden. Okay? Now, in such a case, what should I see? I see only X, right? Observation. So then, by basic laws of probability, this kind of thing will happen. So my definition, my data, like the model is this. Model assigns the probability between X and Z. Okay. Now you see, now what should I do now? So given a data set D, learning problem is to find theta from D. For this is likelihood you know. So most of you know maximum likelihood estimation. Right? That means I have to maximize this function. But this function comes in a weird way like this. So, so this intractable in many cases, in most cases, but even if intractable is one thing, but I can't even do, but if I just, eyes closed, just try to do maximum likelihood, in many cases I'll fail spectacularly. There's no way I can write a computing algorithm for this. Okay? So EM algorithm fills this void very nicely. So to just illustrate this point, let us say I have a mixture model. What is a mixture model now? Mixture model definition is, we said distribution, right? Now one of the things is, like take 1D distribution, right? Take all kinds of points. So what can happen? You histogram them. It is very general what should happen. You'll see many bumps. So what is the next thing I should do? Suppose I know how to handle Gaussians. So what should I do now? Fit Gaussians, mixtures of them. That's the mixture distribution, right? So now let's assume these Fi's are like Gaussian distribution. And this is so now the mixture distribution definition is that you take a convex combination. This alpha is like 0 and 1 and sum to 1, right? Now the new density is something like this. Histogram, just mixing this, right? This is not the same as adding the random variables. This is different from adding random variables. It is adding the densities, right? That kind of thing, right? So now this, so now if you want to write all of that down, a Gaussian distribution is given by the Fi's are something like mu's and the c's, right? And so yeah, so let's see the thing which you already have. Now see, is it a latent variable model? It is. So what I can think about is that assume there are k Gaussian bumps. Okay, but given a sample, I do not know which of the bumps it came from, right? So that Z value I do not know. Okay, observation. Now you can rethink that alpha I, Fi as something like this. There's a random variable Z whose PMF is alpha i's, right? And the condition probability Z equal to I is given by this, and that's the way, right? So now I can think like this. This is nothing. This is my latent variable model. This is a very simple way to make connections to that. Okay. Now there are many sophisticated models. For example, till date, now it has been overhauled, speech processing. Right? In 1970s, where the ideas came from, at Bell Labs, they invented what is called as a hidden Markov model. That is also an instance of a latent variable model. And the EM algorithm was invented to solve that problem. Now take a hidden Markov model, this likelihood there's no way you can even compute anything. And for that you need EM algorithm, right? This is just to give you broader context. Okay, so maybe So, I will stop all of that and just to say just the interest of time. So, basically this is the likelihood of the model, no? And now what EM algorithm, what it does is, suppose you have a guess of theta. Theta is the parameters. Let's assume that what is the guess? Guess is theta 0. What you do is now, so you don't see z, right? I see only x. Now using x, can you guess z? Suppose any x and z is easy to compute. That's the idea. So can you now given x, can I guess z? So what does guessing mean? Okay. So can you now compute the conditional expectation of z given x, assuming the model parameter was theta, and this is the likelihood which you have, right, for a theta function. Now this can you maximize? This is very different from maximizing log of px. You see, log px is now gone. Log px is here, right? Now L of theta is something like this plus this term plus a Kullback-Leibler divergence, right? Now if you see, if you put theta to theta 0, you put theta to theta 0 here, what is going to happen? Now this term, now KL, there's a slide there, but just the interest of time, I skipped it. So if you put theta to theta 0, this term will go to 0. Let's take that. Then what is going to happen now? Theta to theta, this is L theta 0, right? And now this term is also positive. So that means L of theta must be lower bounded by, L of theta is lower bounded by these two things, right? Okay. L of theta is lower bounded by this. This also has a name. This is famously called as elbow in today. Take now any Gen AI paper, they will say what is the elbow? Elbow. This is what it started. Now what will depend on the kind of model, expectation, variation, all this, right? Now the elbow also, now if you do all of this nicely, if theta equal to theta 0, I also go back L theta 0, right? So now this tells me this interesting thing, that if we wish to maximize just the first term, just this first term, just maximize the first term, as I said, which may be easier to do in many cases, So, so that's the theta nu I compute, right? Now this has this nice interesting property. There's the formulas for that. I can show this. So what did I do now? This property, if this all plays out, that means the likelihood increases at every step. That's what you want to achieve to set out to do, right? Now for mixture of, now if you want to play this algorithm for mixture of Gaussians, I think I have a complexity estimate. That means at each step I have to give you alphas, mu's and the c's, right? C is the covariance and all that. Now while those rules are complicated formulas, but finally end of the day, this all I have to, I just all have to compute these things. Complexity, k and d square. N is the number of examples, d is the dimension of this, right? And this is all I have to do. This is every iteration. Now you run 10 iterations, hopefully likelihood increase and that. This is a setup, right? Okay, at this point, 12:06. Now quantum will have to happen in 4 minutes. Otherwise, Abhay will get angry. I made him do slides. Okay, so let us see. Maybe, okay. So this is what I do, survey of quantum analogs for each of these. So let me play slideshow. Yeah. So this thing all of you know, Gruber's algorithm. Right? I'm assuming and now I'm assuming that you are experts in quantum. Right? So Gruber's algorithm, you are expert. So what does Gruber's algorithm do? Setup. Right? Now one of the applications of Gruber's algorithm started is there is a database, there are n items. And one of them, so there are n oranges and one of them is bad. Right? So what do you do? Each of you test. You test each of them, which was the bad one, right? That's Gruber solves the problem. So the worst case, you have to test n oranges, standard database. Right? Now where do I find the bad orange? There is a test and see, good, bad, right? That's the oracle. Oracle comes and tests. Okay? And now, so here comes the n oracle calls. Oracle calls, how many times the tester comes and tests, right? Now, what is the quantum version of this? That's the Gruber. The key assumption is, I assume that all states are in a superposition state. So here is this quantum physics entering. So this is an instance of what is quantum parallelism. That quantum machinery will allow me to store these data points parallelly. Right? This is an abstract concept, but anyway. And this of course, as you know, this required a class to discuss all this, right? Now in the operator, now this operator, that's oracle, right? It marks if x is marked, orange is bad, it will say minus x, whatever, right? And that is the thing, right? Now, the interesting thing what Grover showed is that you can find that bad orange, quote unquote, under conditions with very high probability using root n calls. That's the result you know, right? Now, can you connect to something which we just discussed? Database, 1 point, which one? Perceptron. Okay. So, what I have to do is what? I have to figure out the example which was misclassified by the kth iteration, right? Same problem, right? So, this paper you can read, very interesting paper, and this is one of the things. So, basically the main challenge is that this root n, no? N is the number of, we wrote down this n r square by n by gamma square, right? So, now the n becomes root n now. That is, I can do it in big data settings, get a root n advantage, correct? But in ML, what the problem is that we want to hold ourselves to working code. I don't think it is still computable, but you guys will know better. But this is one of the examples that you see that very primitive constructs now can be speeded up like this using Grover's algorithm, right? This is one instance of it. Okay, now quickly, there's another algorithm, and this I have talked to many people, and I see this algorithm is not noted as much as Grover. This I think is one of the fundamental, this constructs, it's like in the same space. It's called the HHL algorithm, right? So, essentially it is a linear system of equations. Can I solve them efficiently? Why that's important? Take any field of engineering you take, the crux is that Ax equal to b. If you can solve it, many things are possible. You already saw a few instances of what you saw earlier, right? So, that is why this is a fundamental work, and they showed that you can speed things up, right, under some quantum settings. So, it requires many things, including this there's a simulation angle and all kinds of things. So, let us not get there, but important thing is that you are given an n cross n matrix and a b, find x, right. Now, the challenge is that so basically you have to now make sure that it is realizable in a quantum setup. So, you prepare it in some state. So, let us say A, so it is a Hermitian matrix. What will happen now? Now, I know the spectral theorem that A equal to lambda I ui transpose, ui the eigenvectors, right. Now, if I can prepare the state in a nice way, that is in one way to, the way I like to understand it is that suppose you have, you can manipulate the eigenvectors in some way. For example, you can represent B in terms of the eigenvectors, B equal to bi ui's, okay. Then using that, see, suppose I know ui's, right. I not only know A, I also know ui's, right, and I know lambda i's. Then what will happen? My x star, which solves this, something like bi lambda I by ui, right. This is the crux of the algorithm, right, and of course many things has to happen. So, the HHL algorithm, what it says is that it can realize an approximation to x star with some error epsilon. In complexity, this k is the condition number of A with sparsity s and log n by epsilon, right, where n is the size, right. S is the sparsity in A. If this matrix is sparse, you can do all that. So, it often happens, but it comes a lot of conditions. The conditions, I won't give you x tilde. Maybe in many cases, you need a function of x tilde, especially a quadratic form of x tilde. And only then this is useful. So, one is solving, another is extracting. Quantum has all kinds of things, right. So, anyway, so this is, so let us assume for now that maybe I have solved this problem x equal to b, right. Now, this has huge ramifications. For example, if you want to compare against standard things, right. For example, this the Ax equal to b inversion is n cube, right, and if A is sparse, like n s into kappa, right. Now, first application of these is this quantum least squares. So, it does exactly the same thing, just copies this algorithm, and it now becomes what? Log n. What is n? In this case, what should be the n be? Number of examples, right. What was n there? In the only least squares, is d square n. So, n to log n. That is the charm. Okay, you know, so that was n, and this become log n, and that is basically the charm of this. Anyway, so I think I have overshot my time at this point. So maybe I'll not show you all these other things, but let me flag this very interesting piece of PhD thesis if you are looking for things to read. You know, so especially Anupam Prakash's thesis. This is my result of EM algorithm as well. So Anupam, in his thesis, you can, especially this chapter, very nicely written things. It borrows, it has another idea called QRAM, which is again an abstract idea about storing data. And there he shows that if QRAM is essentially, it requires quantum access to data. QRAM is some architecture for that. It's again imaginary. Well, it's not there, but it's just an idea. And what it does is that, you know, the ridge regression problem, you know, which is, which at this n cube and all that stuff, right? You know, so instead of nd, it becomes mu squared delta, where mu is the condition number of the matrix, right? And this can be almost constant time given this, right? So this would be the some of the let's say improvements possible, right? That's why it's a very good paper to read, good thesis to read. Okay, so now what do we do now? Okay, this is a warning anyway. There's not time for this. I am going to now say these things, right? And to set up the stage for Abhay and Adit. So we are doing many things. One of the things we are interested in is parameterized quantum circuit without gradients, and this Shantanu is doing something. Now we will hear two of these talks, right? Can you learn reliably with kernel functions? And this last one is learning with density operators, which Adit will tell us a little bit more. Is now this is probably the first step you may see that how generative AI can be realistically implemented using quantum inspired models. And this is our attempt at that, right? Okay, so without further ado, then let me invite Abhay to take it up for this learn reliably through kernel functions, right? Okay, sure. I take this. Come.
So this remote works. Yeah. So thanks for that. I will talk about this ensuring robustness in quantum kernel classifiers. So Professor Chiru was covering, he had a few slides on kernels, which was he didn't have enough time to cover this. We will come to what a kernel is, but essentially the idea in supervised learning, there is a viewpoint that supervised quantum machine learning is essentially a kernel method. So you basically embed your data into a quantum feature space, and then you learn a function in that space. So that's essentially the idea. And where does the quantum come in? It is in evaluating the kernel, but the optimization problem is solved on a classical machine. This is what is known as a hybrid setup. So yeah, Professor Chiru was covering this. So this SVM, the standard SVM, right? So you have these blue dots and these green dots, and they're linearly separable. What you want to do is you want to find the optimal margin hyperplane here. So you will put this in the middle of these two classes of data. And it's basically a quadratic optimization problem that you need to solve. However, this only works for like classes which are linearly separable. So you need to be able to write this line here. Kernel methods offers a very powerful extension. So you can draw highly nonlinear boundaries using this this basically idea that you embed this data into a higher dimensional space. So you can imagine there are these red points inside this circle and blue points outside the circle. And you can imagine it being embedded on the surface of some conic section like this. And then you can imagine that now you will be able to, in 3 dimensions, draw cut a plane, a hyperplane, which separates these classes. So that's essentially the idea. And you can embed these into even infinite dimensional spaces. So, and for all of these algorithms to work, you need efficient computation of the kernel. So, what in quantum extension, what happens? So you're essentially, so the kernel function is basically the inner product between 2 such embeddings in the feature space. It has to satisfy a couple of properties, which is that it must be positive definite and symmetrical. So which by construction, this will be both of those. So if you think of the embedding as a quantum state given by this density matrix, rho of x. So everybody is familiar with the density matrix, right? So you take a data point and you think of it as, you embed that into some Hilbert space of qubits. And then this is known as a Hilbert-Schmidt inner product, and that defines a valid kernel. So here the feature map is explicit. We are writing it in this way, and this will obviously be, it will satisfy the Mercer's conditions. And the thing is, you can compute this inner product efficiently. There are quantum circuits to do that. So the 2 circuits are, one is like the canonical swap test, which is a very popular circuit. You can construct it using 3 C0 gates. You can swap 2 quantum states by doing that. And these are the kind of kernels that you can realize using in the quantum space. So what is the big attraction here? Well, some embeddings are thought to be hard to simulate classically. So that is where the attraction is coming from. So for example, in this paper, it was shown that a quantum kernel can represent it can learn a function which is based on the discrete log, but classically you cannot do that. So they constructed a sort of synthetic data set based on this discrete log function, which is known to be, or believed to be hard to do classically. So our research has focused on this question. Quantum computers are highly noisy. Now let's try to deal with that first. We will see that, so if you have noise in the kernels, your classification will also be not reliable. So on some days, you run the classifier, it will say cat, and on the next day it might say dog for the same data point. So that is a very, you have to be careful about that. And there are 2 types of noises which enter the, in any quantum measurement. There is a quantum measurement noise, which is fundamental. You can't do anything about it. You are inferring all values from measurement statistics. And there is a device noise, which can be mitigated or corrected. And there is a lot of work to. So these are the 2 circuits, which we'll not go into that too much. So now the idea is this. So you have to, so we saw that kernels are inner products. Basically, you have to calculate this transition probability. And you have to estimate it using measurement statistics. So now what will you do? Like maybe you want to, so this is one circuit which evaluates it. So you want to measure this and infer the kernel value. But you can't do it just once. If you do it once, you will get an answer 0 or 1. So maybe you will run it 1,000 times. Maybe 250 times I will get 1, and 750 times I get 0. Then I will infer that the value is 0.25. But there will be some error. So next 1,000 times you run it, you might get a different value. But as n goes to infinity, you will get the correct value. So now, how many measurements should we use? So this is a question that is not in the literature. If you see, they are using various numbers. This, for example, is from the IBM group, so they have access to the quantum computer there. So it's like 50,000, and the defaults that they offer is like, it used to be 1024, now it's 4,000. So for each kernel, you do it those many times to infer the value. And there is no understanding of what this number n ought to be. So this, for example, is an 8-qubit simulation, which is trying to do classification. And this is this axis is the accuracy of the classifier, and this is the number of measurements. And you can see that there is accuracies themselves are not very good. 50% is basically just a coin toss. So that's as good as random. But what is more concerning is that there is a huge range of values that the accuracy is taking. So depending on the particular instantiation, sometimes you might get a good classifier around 65%. Sometimes it's like below 55%, for example. So this is a huge problem, and it has not been given due attention in the literature. And so this is a clear sign that it is unreliable classification. So one day it might say dog, one day it will say cat. So, so here, yeah, it is showing the same thing simulated here. And when this notation Fn means that the classifier is run using n measurement shots per kernel evaluation. And if you do it, this is the ideal case when you have a noiseless kernel. You want to get there. And one has to introduce this figure of merit, an important figure of merit, to quantify the reliability of classification. Just the accuracy or average accuracy being reported, that doesn't give you much information, because you can see that the range of accuracies is very wide here. Right? So sometimes this n is called as the sampling complexity. It's a number of times you have to sample for each kernel evaluation. And you can write a simple Chernoff bound and find that if you want to evaluate the kernel to precision epsilon, you will get 1 divided by epsilon square kind of dependence. Same thing you can repeat for all pairs in a data set of size n. And this is a very important thing that was noted in this paper in NeurIPS 2021. So if precision needed is exponential, quantum advantages disappear. So there is let's not talk about quantum advantage. You will lose your whole game in, with n going to infinity, basically. So, okay, let's now, the questions we want to answer is, let's introduce a good figure of merit to characterize the reliability of the classifier. Can we obtain better scalings for n? And can we reduce n without sacrificing the reliability of the classifier? So, so now what is reliability? This Fn is a stochastic classifier because I'm using n measurements to evaluate each kernel value. F star represents the ideal quantum classifier, which you can think of as n has gone to infinity. So F star represents that. So what is the probability with which these two agree? So both are going to say cat or both will say dog. So we show that reliable classification requires log m by gamma squared. Now gamma is the margin of the classifier. That's very important. It's not the precision epsilon. So we are not interested in precise kernel evaluation. We are interested in reliable classification. So this gamma, this is good news because gamma is of, or if you choose your kernels well, gamma can be of order 1, whereas epsilon is vanishingly small. So, so we'll talk about this very briefly, the chance constraint optimization and how to construct robust classifiers. And then, yeah, I think Adit needs more time than me, so I will try to speed this up. So you can see that precise kernel estimation, yeah, see, you can see that this, if you want to do it up to precision epsilon, you will get 1 over epsilon squared. And then this is coming from a sub-Gaussian bound because these kernels are actually, since you can think of them as coin tosses, right? Sometimes 0, sometimes 1. That's how you measure the kernel values. So it's a Bernoulli distribution, and there are like sub-Gaussian bounds you can write for them. And here is our result here, which is more interesting because gamma squared is appearing here. And we are trying to bound the error of the stochastic classifier with the performance of the ideal classifier with the margin gamma. So what we intuitively what you can see is the points closer to the margin. So this is the decision boundary. So points closer to the decision boundary require more measurements, but points further away you can do with less measurements. And the main idea in optimizing when there is uncertainty in a problem is one of the main ideas is that you can do the optimization with high probability. And this leads to something known as chance constraint programming. Here, so I won't have time to go into this. The message is this. This is a program where instead of your usual quadratic optimization problem, you have the constraints change because you're taking into account the uncertainty. You get second order, you get what is known as a second order cone program. And there are efficient algorithms to do that. Anyway, you're doing optimization on a classical machine. So you'll pay some, maybe some, it might not be as simple as a quadratic program. So you may spend more classical resources, but you get huge savings in the quantum resource. You can reduce n by a lot. So that is one of the messages here. Yeah, you can analyze the effect of other noises as well, but here is the main message. If you use this chance constraint approach and construct short, frugal, and robust, SHOFAR stands for short, frugal, and robust, and you get like very large savings in n, say up to 90% in many cases. And we recently ran this simulation on like a 25 qubit simulation on the fashion-MNIST data set. And you can see like similar type of behavior here. So the robust SVC performs much better, both on accuracy as well as robustness, where as a function of the number of measurements per kernel estimation. So you can see there's a huge gap between the nominal SVC, if you directly try to do the quadratic program, or compared to our robust SVC. So thank you very much. Thank you. So I'll hand it over to Adit.
Am I audible? Okay, let's get rolling. Yes, all good. Thanks, Abhay. So let's get rolling. Fair warning before this talk. So we will be largely talking about how you can use density operators as a machine learning tool. So there is no quantum device in this talk. It's about how you can use quantum formalisms to do machine learning. Now, how you can get this running in a quantum computer is still out there, right? But if you were here for the quantum simulation talk, if you want to deal with an actual quantum system, so if you want to simulate a physical quantum system, currently you are generally stuck at very small numbers. So if you want to simulate a 12, 13 qubit density operator, you have 2 raised to 13 times 2 raised to 13 matrices, and these are quite large, and you're out of the game very quickly, right? But recently, there's been some effort to use these density operators for machine learning tasks. Recently, as in the last decade, right? So this is joint work with Abhay, Dhruva, and Chiru. And so today, if you want the state-of-the-art generative models, if you just ask for a tranquil sunlit mountain landscape, it'll give you something like this. This is the quality that you're fighting for. So if you want quantum machine learning, in whatever way you define it, to start impacting today's machine learning, you need it to hit qualities of the scale, right? And as of today, quantum generative models cannot generate numbers, faces, let alone very fancy images like this, right? So modern generative AI can generate new instances of images, text, videos, and they generally use something, a formalism known as latent variable models. And this was talked about in the previous segment, so I will skip some of the details. And they're usually powered by deep neural networks, right? So as far as today is concerned, there are no generative AI models that are suitable for quantum computing that can give comparable results. And it is not clear if such models exist. And if they're developed also, we don't know if there's going to be an advantage. It's open ground there. And even if you go today and Google for quantum, what your favorite generative model, you will find papers. But if you now go and look at what they actually do, it'll have some unitary transformation somewhere, and the claim that, oh, this unitary transformation is a quantum effect. But what does it actually do so that, does it beat your generative model? Now, that has two problems. One is it has to scale up to images of this scale, of this size. So you would like to impact models that are, if you want an image, even a 28 cross 28 image, which is the simplest image data set that is usually used here, which is MNIST, you need 700 odd bits or qubits, right? The other setup is, okay, now suppose you can generate it, does the quality get better? You do all of this, is there a use? Is there some advantage? Advantage being used rather loosely. I know quantum advantage is something that gets flagged around a lot. Okay, so the first generative AI models that we know of were inspired from statistical physics. And this is part of the reason why Hinton got a Nobel in physics. And if you go look at the Nobel citation, you will see this thing called a Boltzmann machine. And the Boltzmann machine is actually a model that is inspired by something called the Ising model. So if you're coming from, if you've taken a StatMech course, how many of you have taken some kind of StatMech course in the audience before? Not a lot. How many of you have taken a machine learning course before? Okay, so excellent. I have a machine learning audience. So if you know the Boltzmann machine from a machine learning course, excellent. But if you're coming from a StatMech background, there's something called a Ising model. And the Ising model basically is for a discrete system. So you have a binary state of m bits or n bits, and then you have an energy function and you have the Gibbs state. So what you do in the classical machine learning setup is that you take an Ising model, you say that m bits I have observed and n bits I have not observed. So the samples you draw are only from the first m bits, and so in this case the diagram that I have, you have 4 visible bits and 3 hidden bits. Now you have some energy function that has interactions, And now you have the probability of some state S is the probability with respect to the Gibbs state, right? And all your machine learning folks already know this. So now how, if you want to update this, if you want to train a model on observations that you found on the visible states, what you can do is that you have to either derive, you do gradient descent or gradient ascent, you take the log likelihood, you get an expression like this. So you have Si Sj clamped, where Si and Sj are either V1 through V4 or H1 through H3, and Sj is similarly. So there is this clamped free stuff. So please look up, this is necessary reading. So, but this is the idea, right? But Boltzmann machines have been bolstered further. So there's something called an RBM, where a restricted, so you say that, oh, my interactions in the previous slide, so this model interacts through all, there are Wij interactions for all bits here, right? So, but now I can say that, oh, I can have a bipartite graph here, where the Vi's interact with Hj's, but the Vi's don't interact with each other and the Hi's don't interact with each other. So if you have this, you can now start running something called a contrastive divergence algorithm, where now you can run a Boltzmann machine or train a Boltzmann machine for significantly larger data sets. Because otherwise the problem is that you will have to sum through. So I've only written a directly proportional. So to make this an equality, you have to have a normalizing constant. And to find the normalizing constant, you have to sum through all possible states. And that here is 2 raised to m plus n. And you're out of the game very quickly. So again, if I want to say mnist, even if you have no hidden units, you have to now go through 2 raised to 780 something, right? 28 cross 28. And that's not happening. We all know that. Right? So you can train it on a contrastive divergence algorithm. So now RBMs are quite good. You can, when it launched in the early 2000s or late 90s, they were so powerful, and like they're the earliest large-scale generative models that we know of. Now there are several other models. So you have something called the deep Boltzmann machine. So what you have essentially is that you have the visible layer. It's a n-partite graph now. It's not a bipartite graph anymore. You have H1, H2 and H3, and you train across all of these models now. So you basically have depth. So you can think of this as now, if you're, since you guys have been taking machine learning courses in the 2020s, you're more familiar with, oh, add a few more layers to the neural network, right? And this is the primary idea there. And this can generate better images often. And the deep Boltzmann machine was introduced in 2009, a few years before the AlexNet paper. Okay, now, but there are more exciting things. Boltzmann machines, now you can have something called Gaussian-Bernoulli RBMs. So what happens is that now you have an RBM, and the hidden layer is still discrete. But I can now say, oh, an RBM has a bipartite graph, and what happens is that if you fix the hidden layer, you can now start, what happens is that you can now start working with the visible layer on this conditional probability, and this is much easier to calculate. Now in a Gaussian-Bernoulli RBM, what happens is that conditional probability, given the hidden layer, is a Gaussian distribution and not something on a discrete distribution, on a discrete probability space. So now you can start modeling more complex data sets, right? And this is still active, even though they are not the state-of-the-art methods. Papers around Gaussian-Bernoulli RBMs still come out. So if you Google for it, you will find that even after 2020, there are a reasonable number of papers. So this is where RBMs are, right? Even the most elementary model that is used in ML, it's been well studied for decades, and this is the state of an RBM, or a Boltzmann machine in general, right? So now how do you have quantum Boltzmann machines? It is one of the most active areas in quantum machine learning. You will find so many papers. The first quantum Boltzmann machine paper, which came out in 2018, has, I believe, around 500 citations to 500 to more than 500 citations. So it's quite an active field in that sense. So you have an Ising model. You have analogs of the Ising model in the quantum setting. So one example is the transverse Ising model. And you can now do the same thing where you model it using you start modeling data using a quantum Boltzmann machine. So that is the setup. Now the problem with a quantum Boltzmann machine is that you now need 2 raised to m plus n cross 2 raised to m plus n density operators, right? If there are m visible bits and n hidden bits. If you want to use hidden bits, you have only a total of 12 bits between your visible and hidden units. What kind of data sets can you model using these? Not many, like no practical data set that we learn in a machine learning course fits in 12 visible and hidden qubits, right? Now, a real world data set, like I said, requires 700 plus bits, right? So, this is where we are. There are no comparable variants for a DBM or a Gaussian RBM, and you cannot really train on large data sets. And that's where the interesting things, interesting phenomena happen in ML. Okay, so the challenge is this, right? Can quantum DBMs at least do everything a DBM can do? So can we come up with a quantum DBM? The second question is, are the quantum variants any better? Okay, this is for people who are not particularly coming from a physics background, but I believe there are several talks that have been talking about density operators, so I won't go into it much. So any quantum system is described by a density operator, and they are essentially positive semi-definite trace one operators on some Hilbert space, right? And your data points now become elements of this Hilbert space. Now, if you want to train really large density operator models on a quantum system, this is not happening anytime soon because quantum computers, the hardware is not coming up yet. So the standard approach is, can I do something on a classical computer and see what happens? Okay, so again, the expected value of a if you have a density operator, you can calculate expected values of an operator, all well known. More importantly, using the spectral theorem, you can now start talking about quantities like the KL divergence. So essentially what you're asking is, if I give you two density operators, how different are they? And this comes from an area called quantum information theory, and you have several ways of quantifying this. This particularly is not a metric in the mathematical sense, but this is your standard tool. And this is the analog to something called the KL divergence, Kullback-Leibler divergence in classical information theory and machine learning. You would have seen this in several places, right? So you can do this. Now the omega k relative entropy, which is the analog, is defined as such. And this log n and log rho, okay, I give you a matrix and I ask you to calculate the log. What does it mean? So what you have to essentially do is that you have to now take the spectral decomposition of this operator, take the log of the densities, the log of the eigenvalues, and then bring it back. So that is what log here means. But moving on, you also have a notion of marginalizing an operator to a subspace. So this is called the partial trace operation. So if you have a density operator over HA cross HB, you can think of this as a joint probability distribution of sorts. Classically, you will integrate it out or sum it out. The equivalent setup here is something called a partial trace. And how do you encode data? Like I said, now you would want some element of your Hilbert space to be data points. So if you have m bits, your Hilbert space now all of a sudden has 2 raised to m dimensions, and each data point in the classical setting is now orthonormal basis vector in the Hilbert space. That is the setup. And now naturally, like I said, you can now take the probability of one of these data points S to be the trace row with the operator for that specific eigenvector. Okay. These are polymatrices. So polymatrices are now the way quantum Boltzmann machines or the transverse field Ising model is defined. So I will not go into why they are relevant in quantum mechanics. Please go read up. But they appear quite frequently. Now you can think of the expected value of a polymatrix. So now if you take n is equal to 2, you can compute specific, you can scale these polymatrices up to n bits by tensoring them with appropriate identity matrices. And just to give you an example, so for n is equal to 2, your polymatrices look like these, right? And what is a quantum Boltzmann machine? You have a specific Hamiltonian that give you biases for polymatrices, and interaction terms between these polymatrices. And the density operator itself is just e raised to h, which is the Gibbs state by the normalization term. And for us, what we are specifically interested in is rho v, right? So you have to partial trace over the hidden units. Probability of S, as mentioned, all great. Now, incidentally, if you now remove this red part, which is in this Hamiltonian, this is entirely classical, it's a diagonal matrix, and you will get back your Boltzmann machine. And m plus n, m visible units, n hidden units. Okay, so you have the joint distribution, you have the marginalization, everything is good. And like I said, gamma is, if you set gamma I to 0, you get your classical Boltzmann machine, but in a density operator, right? And you have a lot of zeros, but it's still a very large matrix. Okay, this is the setup for a density operator latent variable model, right? So you have visible units, you have hidden units, and you have rho defined over the entire space, and you have to partial trace it out. Now, what is your log likelihood? Suppose you have some target space, suppose you have been given data, you would like to say that, oh, I would like to maximize trace of eta v log rho v. Now, why is this the log likelihood? In classical machine learning, you will notice that if you increase the log likelihood, you are also reducing the KL divergence between the ground state distribution, which are given through samples, and the model. Now, if you go back to the definition of the omega k relative entropy, this is one term there with a minus. So, if you maximize this, you are minimizing the distance between the data set that you've been given and the model, right? The challenge here generally is that this cannot be broken into simpler terms, because eta v will still have these ij entries. Okay. Now, you want to train on these. I have a long list of problems. So existing algorithms. So if you take your classical EM algorithm, you can't. It uses Jensen's inequality, for example. The proof, right? How do you prove it for density operators? It breaks down. There are Jensen theoretic analogs in operator theory, but you need to be able to use them in a nice way. So that is a problem. Like I said, size of matrices is also a problem. And the biggest problem here is that density operators are non-commutative. So if you have e raised to a plus b, you're used to writing, oh, e raised to a times e raised to b. Now this is not true anymore. You're stuck. And worse is that the EM algorithm, which was covered before, uses the conditional probability as a step. And you don't have conditional density operators in general in the physical setting. You need to do some measurement of some sort, and that if you want a conditional density operator, right, you need to do some measurement, and then you say, oh, the system goes somewhere. The problem there is that once the moment you measure, you're losing out on all the quantum, the system collapses. So you don't want that to leave either in your model. And in the ML setting, if you're familiar, one of the big reasons why you have the EM algorithm is that your log likelihood finally has a log of sums, and this has no closed form expressions in general. And here the problem is that trace of eta v log rho v, as I just mentioned, rho v is actually a partial trace of a larger model. So I have also a similar phenomenon here, which is that, oh, I have a log of a partial trace, and I do not know how to take the derivative there, or any other expressions for that matter. Okay, so the classical solution, as mentioned before, is the EM algorithm. How am I doing? I have roughly 7.5 minutes. Okay, I will skip this because you have a general model, observable, latent variable, and parameters. Sure, Boltzmann machines are an LVM. Now, the solution here is an iterative algorithm called the EM algorithm, and you have two steps. You have to maximize this step, and you calculate an expectation in this step, and then you maximize the next step. So, and this is the evidence lower bound. So please go read up the EM algorithm. So sure. Okay. Like I said, you want to derive an EM algorithm for density operators. The hope is that some of these problems are reminiscent of the problems that we face in the classical setting. For example, the trace of log and all of that. But the problems are also more complicated than the classical EM setting because you don't have these standard inequalities as cleanly anymore. Okay. Can we have an EM algorithm for density operators? So the EM algorithm, incidentally, the E step, which is where you generally use the conditional probability, can be thought of as an information projection problem where you have data and project the conditional of the model to the data. So using this, you can now also have an information projection notion here. And you say, oh, I have, the first thing you need is an elbow. You have to derive an evidence lower bound. And then once, 2 steps, right? The expectation maximization algorithm, as we mentioned, has 2 steps. The first step is you have to derive a inequality which you can maximize using these 2 steps. So where do you get the evidence lower bound from? So the idea here is that you have something called the monotonicity of relative entropy, which says that if you partial trace two density operators, so you have a joint density operator, and if you partial trace it, the relative entropy between the omega k relative entropy between the systems will only decrease. This is a very famous result in quantum mechanics, and this we can use this instead of the Jensen's inequality or the standard trick that we use, which is the chain rule of KL divergence in classical probability. So once you use MRE, fine, you want to now maximize this setup. So I will now say I will fix rho. Can I find eta such that this inequality is maximized? That is the first part. So it's a 2-step optimization process. The EM algorithm in general is a 2-step optimization process. I will fix rho. I will try to find eta. Trace L eta is the data. Eta v is the data that was already given, and I have rho. I will try to find. I'll fix rho. Fixing rho fixes trace L of rho as well, and then trace L of eta is given by the data, right? What I will do is now I will find an eta that maximizes the whole thing, and once I do that, I can now fix eta, and trace L eta is already fixed, and now I can find a way to maximize theta, like change the parameters of theta. That is the idea behind the EM algorithm. So there is something called the Pets recovery map in quantum information theory about how you can recover systems that quantum operators that have already gone through some CPTP map. And he gave an if and only if condition for when you can actually tighten this inequality. And that comes from something called the Pets recovery map, which is often called the base rule. So I'm not going into the details of this. Classically, if all of your operators are now diagonal, it will give you the base rule, right? And turns out the information projection problem in the quantum setting that we want to solve under certain sufficiency conditions is solved by the Pets recovery map. So classically, the information projection is solved by the base rule. Under certain conditions here, you can now solve it using the Pets recovery map here. Okay. So the quantum elbow is basically just this. So you have your monotonicity of relative entropy. You move it around so that the log likelihood that you want is lower bounded by this expression, the quantum elbow. So you can just move this around to get the MRE. It's your standard trick in classical machine learning as well. And once you have that, you can now have 2 steps. So you want to find eta using the information projection, and you want to find the parameters of rho, which is theta, using some gradient descent technique usually, right? Okay, so far so good. You have quantum Boltzmann machines now. I have not connected them yet. Turns out you can solve or train a QBM using density operator expectation maximization. The problem is still here, is that you have not reached scale, because I still cannot initialize matrices that are 2 raised to more than 2 raised to 13 cross 2 raised to 13 or 2 raised to 16 cross 2 raised to 16. This problem still exists. I had left one tiny bit in the beginning as foreshadowing. What was the trick that was used for Boltzmann machines? You need to run some kind of contrastive divergence, right? So turns out if you can now set it up as a as a quantum RBM, where these Wijs don't interact with each other, you can now have quantum DBMs. And once you have quantum DBMs, you can estimate the gradient that is given by the EM algorithm in the M step, and you can train models. Okay, I have 1 minute. How good are these density operator models on real world data then, right? So what have we done so far? QBMs exist. We've made them an RBM or a quantum DBM. And now you have the classical EM algorithm. We've derived an analog called for density operators. It's the density operator expectation maximization algorithm, as we're calling it. Now you want to scale it up to real world data. You will say that, oh, the gradient can be estimated using contrastive divergence techniques. Okay, fine. So this is the setup, right? So you have QBMs, quantum DBMs now with quantum bias terms, and this contrastive divergence step for the EM algorithm. Okay, this scales as well as the DBM. So any data set that a DBM can train on, because of this contrastive divergence step, I can now train significantly larger models. Any model you give me saying, oh, a Boltzmann machine can learn it, I can now train a quantum DBM on it, right? So here is images sampled from a quantum DBM and images sampled from a DBM. It's a little difficult to compare. So the standard metric in this setting is something called the Frechet information distance, where you give a neural network an inception model, the test set, and data that is generated by your model, and the neural network will spit out how good your generated images are. Turns out, the samples generated by a quantum model is significantly up to roughly 40 to 60% better than the images generated using DBM. More, is this just over parameterization? That's a good question to ask, right? Okay, DBMs have this extra gamma item. So we now trained DBMs that have significantly more parameters than the QIDBM we are training, and the DBMs don't really improve beyond a point, but our QIDBM is still doing 60 to 40%. So there is something here with the interaction terms that help models. Okay. We also we ablated over several different architectures, so to speak, which gives you different number of parameters. And you can see that the quantum models always outperform the classical models. And this is all done on a GPU with the CD update. So you don't need a quantum simulator. You don't need any fancy machinery. If you have access to Google Colab or something like that, you can now run all of these models. You can run the code for this and generate these models. Can you now extend quantum RBMs to Gaussian RBMs maybe? Turns out you can. I will skip the definition, but I'll give you numbers because that's the more exciting part. So the samples on the right are generated by a Gaussian RBM where the hidden units are now quantum. So once you have that, you will see that there is still a relative decrease in the FIDs. And we are pretty excited about it. Because as far as I know, and please correct me if I'm wrong, I do not know about a quantum generative model which uses a density operator setting, which is what is quantum about it, that can even train on these kind of data sets. And now, okay, we've trained it on these data sets. And if you go back to where ML started, generative modeling started, we do better than those models. So we are not yet competing with modern generative models, but this is still a nascent field and it will take time. But the fact that we can, on very standard classical hardware, using quantum formalisms, outperform old really classical ML models, I feel is exciting. And that's our work so far. The paper is up on arXiv, so you can take a screenshot, or you can take a photo for this thing. I do not want to stand between you and lunch. Questions now or after lunch? during lunch, you can find us. So questions for all of us. So you are not taking questions. Yeah, do I want to make my last stand here today? Yeah.
So good afternoon
Yeah.
and great work. It's really exciting. But then I would want to ask, like you had told that your models were outperforming the classical models. So how confident are you that if you extend this research, it might actually be useful even in Gen AI?
So this is generative AI. Like this is still okay.
The
This is
really
not
scalable, real-world messy data kind of thing.
This is still a real world. So what kind of data are you talking about? So if you want to talk about standard data sets that are
Not standard data sets, like how we train on real-world data, like you're taking live from other sources. It's very messy.
taking, sorry?
You're taking from the real world, just think, and it's not processed in how standard data sets are given.
So anything that, so I'm pretty confident that any model, any data set that you can give me that a DBM can train on, however you process it, right? I can train it on this model. How it will perform, we've done our ablations on standard data sets because that's what the field requires first. But if you have a data set in mind that you're saying that, oh, these models can train on it. So if you say, oh, a Gaussian-Bernoulli RBM can train on it, or if you can tell me that a DBM can train on it, or an RBM can train on it, we can do the same thing. And we believe it will do better. All indications are that it will do better, but there's no way to say for sure.
So you're confident it can hold in industry settings too?
So industry settings today is very different though. So these classical models are not what are used today in your phones or in most of your applications actually. So you will need formalism. This is a step in the right direction, we believe, to ask how these models should be even defined, right? So even model definition, so if you ask me what a quantum diffusion model is, what is the setup? Or if you ask me what a quantum GAN is, if you set it up the right way is the only case when you need two things, you need scale and performance. You might be able to get performance easily, but you need to be able to also be able to get scale. So it's a open problem I am not aware of any model that I know, a quantum analog of a standard classical model or a standalone quantum model that can give you both scale and performance. This for me is the reason I'm excited about this work is that yes, it's a classical model in that sense, in the sense that it's not modern that way. Right? It's not a model that that came out for the first time in 2023 that is now being revamped into the quantum setting. It's an old model, but the fact that we understand these models better, so we can now go and check what is the thing that actually makes it work. So now you're free to take a quantum DBM or a quantum model and then actually go and check, okay, what is giving you the advantage? And that hopefully will give you a better sense of, okay, now I want to generalize diffusion into the setting. What do I do? What is it that gives me an advantage? What is it that doesn't? It's an open world out there actually. So, and that is the exciting part about this area at least.
Okay.
So hi, my name is Mitali, and my question is specifically for Abhay. You mentioned that in your research you used a hybrid model. You went for the kernel on quantum machine and the optimization as a classical approach. My question is, why did you not try the optimization also as a quantum approach? Is it something that's not possible, or what's the case?
So in that case, I'm actually not sure how we would go about doing it on a quantum machine. I think maybe the HHL algorithm can be used if you can embed that data in a quantum way. Like your optimization problem, if you can do it in a quantum way, Because it solves Ax equal to B, you should be able to do like least squares sort of optimization. But this has been the standard approach in the literature, and we've just sort of done things in that setting. Yeah, so that's a good question. So you should look into extensions through the HHL algorithm, which Professor Chiru covered. Yeah, so maybe you can search along those directions and you'll get answers.
And another question that I had was because the quantum noise was such a big issue for us. So were there any quantum error correction methods that you tried, maybe using multiple qubits or something like that?
So this is a quantum error. It's in some sense a quantum error correction method. That is, we are demanding a robust classifier at the end of it. But our approach is to go through the optimization problem and do things on the classical machine, because we know we can trust classical machines. They're not, quantum machines are not trustworthy right now.
At this stage, I agree.
Yeah.
So that kind of brings me to my third and a more open-ended question to maybe all three of you. We did see in the research that we are trying to approach the classical methods using a quantum way, but we still don't see any quantum advantage here. So what exactly do you think is the future currently? Do you think it's something on the hardware side or maybe something on the algorithm side?
Yeah, that's a very good question. I think I'll let Professor Chiru.
Lunch cancelled. Bring it to her. No, yeah, good question. Frankly, I don't know. I'm sorry we rushed the presentations. Things which I couldn't cover, there's something called QRAM, this idea of Setloid. Now, it is not, as of now, not realized, but it's speculative. But if you have QRAM, you get great gains in terms of many linear algebraic primitives. If you make progress on that, the computation side of ML will also improve. And there are some examples which I wanted to show, and I showed a few. Okay? So now if that is realized, then maybe we have something to say, number one. Number two is, I think if somebody can make a breakthrough on this PQC business, because that's the only way circuits have been used, right? And if it can react, now the problem is it does not react well to data. In the sense, I can't train them well. If that problem can somehow be circumvented, we may, because now the chips are coming up, right? And I think what you asked Abhay about this, that, oh, why didn't you try QEC and all that? Yes, but our step is different. Somebody has given you the hardware. What can I do with it? That's the question we're asking, right? And that's why Maria Schultz's connection to get around that, let's say the PQC through kernel methods, I think is an alternative to maybe a better models which can react more to data, right? But of course, that also has one problem. That's why Abhay's work is mainly on that. Okay? And see, and the last point, Adit's part, you can see there that traditionally I take a standard ML algorithm, whatever primitive, and now force it into quantum hardware. That's one thing. But I think there's two-way street also. For example, we did not know how to do machine learning with operators. First of all, I don't even have the methods to do it, number one. Number two, even if you have it, what good is it? So Adit's work is in that direction, right? So I think this will create, I am not very clear about actual industrial realization in the next 2-3 years, but definitely will create huge kind of high quality science, and hopefully in 2-3 years, some of you will now do wonders. Now, if you want more gritted discussion, lunch.
It's not going to cancel.
Not going to cancel. So we'll leave it that.
Sir, I'll approach to you externally about this. I have more to say about this.
Thank you. Sure.
Yes. Thank you so much.
Right.
Thank you so much, Chiranjib sir, Ajay Shastri, and Adit Vishnu for sharing your valuable insights with us. The way you all connected the foundation of machine learning with real applications make it very interesting. We're truly thankful for your presence, sir. As a mark of our respect and gratitude, we would now like to present a gift to Chiranjib sir Abhay Shastri, and Adit Vishnu.
All of us get gifts, no?
Yes, sir.
Only then, all of us.
Give a huge round of applause for sir. Now I thank everyone in attendance for making these sessions engaging and full of learning. I hope every one of us has taken something from the session. So before we conclude, a gentle reminder to all the participants, please don't leave for lunch yet. We will be having a group photograph in front of the main building right after the session. Thank you so much.
Good afternoon, everyone. I cordially welcome all of you present to the second half of the IISc x Qiskit Fall Fest 25. The next set of talks would be given by our experts who are coming from IBM Research, who have years of experience in computer science, especially in quantum computing. So a huge round of applause for our experts. The first of these enlightening talks would be on a deep dive of the Qiskit SDK. The Qiskit SDK strives to be the GCC and LIBC for quantum computing. And in this talk, the architecture of the core Qiskit SDK would be discussed by going into some of the modules in detail. The talk would be delivered by Dr. Dhinakaran Vinayagamurthy, who is the manager of the Qiskit team in India at IBM Quantum and an adjunct professor in the Department of DSAI at IIT Madras. He holds a PhD in computer science with specialization in quantum information from the University of Waterloo, a master's in computer science from the University of Toronto, and a bachelor's in computer science and engineering from the College of Engineering, Gundi. His research in quantum computing, cryptography, and blockchain has resulted in about 20 peer-reviewed publications and 16 patents with around 1,400 citations now. He has received a Best Paper Finalist Award at ACM CCS, IBM internal awards like Outstanding Technical Accomplishments and Technical Collaboration Achievement, and one IBM ISA Growth Award respectively for his research. So with a great round of applause, please welcome Dr. Dhinakaran Vinayagamurthy. Please come, sir.
Should I connect? No, I mean, laptop? Do I have this? I think I have this. Very good. Yeah. Okay. Press the button.
So I need this for live streaming, or I can just talk from this. If I'm walking, I can use this. Otherwise, I'll just use. Yeah. Can those in live stream? Is it good? Okay. Does it take time?
Laptop no detector, sir.
It always detects. I don't know. Kalyan, you want to try whether your laptop detects? If it detects, then you have to listen to me and not prepare your talk.
Okay, sure, no problem.
No, but I don't think that will be the case.
Do I have to do anything here?
No. First you have to
No signal, it is saying. Should we send it to some laptop, mail or something? Should we email it to some laptop or some other ID?
No, but this
it
was
working
works.
fine, but can we share it on some other laptop? It's not written.
But usually it works.
Usually it works.
Yeah.
Is
I mean,
there any wireless thing like?
yeah, is there a... But usually it connects, there is no issue. Maybe it's HDMI 2. Can you connect?
No signal दिखा रहा है.
I mean, if I switch, the formats will all be messed up. Let's see. I have to convert to PDF.
ठीक है HDMI 1 है. चल रहा है HDMI 1 है.
Is there an online way of connecting?
Online.
Live streaming is what link is Zoom or YouTube? I guess.
YouTube. Yes.
Oh, I see. Morning it was fine.
Okay. Morning it was working.
For everyone.
Yeah.
Should we try a different HDMI or VGA, sorry. quantum or not, we have to figure out these things. Anyway. Good. Okay, good. Right, we can start. Okay, good afternoon everyone. Welcome back to the post-lunch session. So, I think we are almost like towards the second half of this Fall Fest, right? You guys have already heard a lot of basics around quantum computing and also perspective of how this technology is going to evolve in the near future. So, with all that background, I thought in this talk, we will go one level deeper into how Qiskit works. When I say Qiskit, I mean the core Qiskit SDK. I thought I'll take some time to give you a deep dive into how that works. And I think while I go into that, I will also quickly have this context, quick summary of the context before I go into the details, right? So, right, so the main goal that we are all working towards is to bring useful quantum computing to the world. So what do I mean by bringing useful quantum computing? Or how do we execute it? We do it in two parts. Okay, first is developing the core quantum platform itself, right? So the hardware, software, and we'll have to develop the core platform because you would have seen already that quantum computers are different foundationally. Like they're different from the computers that we use today. Starting from the most basic unit of information, depends on how we store and process basic information. Like quantum computers have to be rebuilt from that foundational point, and hence a primary goal for us is to develop a performant quantum platform that scales beyond the classical computers we have today. The second pillar of our goal is to work with enterprises, research labs, universities and governments to discover new quantum algorithms that can leverage the power of the quantum platform that's built, right? Okay, so what do I, like when I say quantum platform, so where are we with this? So this is sort of a heavy slide, but I always like to, depending on the context, I will at least give a summary of this, and sometimes if you guys have not seen it, I even like to go a bit into this before I go into the technical part, right? Was this roadmap covered at some point in one of the previous talks? Janani covered it? Okay, good. So just to give you an overview, right? I mean, quantum computers were first made available on cloud in 2016. And every year we had this a goal setting exercise of committing to what we want to achieve in the following 5 years. So from 2016 we have always had this 5-year roadmap looking forward, and it gets updated every year or two. So this slide, the left half of this slide contains a summary of what all we had promised and achieved in the evolution of the quantum platform in the last decade, and then the right half contains where we look forward, right? And then if you see, it contains evolution of hardware, it contains evolution of the middleware and the software, okay? Hardware, it started with a 1-qubit thing. I think it's sort of not in here. 2016 when it first came up, we had a 1-qubit computer available on cloud and a 5-qubit simulator. And then it sort of evolved to right now about 156 qubits is the, at least in terms of number of qubits, that's the biggest hardware that we have today. And the when it was a very small qubit system, the way to program it was easy, right? We can just directly work with it. So it was direct control, like a UI, which I think it's still available, Quantum Composer. It's all online, you can go plug in gates, qubits, and then play with it. So since it was a small qubit system, it was, let's say, primarily used for teaching purposes for quantum computing. It was for everyone to get exposure to it, because otherwise only those who were in a lab building a quantum computer, which was maybe a handful of research labs across the world, had any quantum computer. So this was the first experience for almost everyone in the world to get used to it. So it gave a fine low-level interface to quantum computers. But as we evolve, there are much more interesting things that we could do with it. So a lot of abstractions that are being built that amplifies the advantages of the quantum computers that we have, and then also abstracts out the sort of the let's say some of the disadvantages or some of the properties that we'll have to work around to get useful computations run on quantum computers. Okay, so that's why like levels of abstractions were built, so that it was easier and easier for those to access. And then the goal in the near future is to reach a stage where it's very similar to how we write programs today, where almost all the intricacies with respect to quantum computers are abstracted out, and the computation libraries just needs you to have a high-level understanding of the capabilities quantum computers have, and then you can write your domain-specific or applications program on top of it. Having said that, if you have a deeper understanding of quantum computers, you can certainly plug in, go to a lower level and then fine-tune and then do better than the generic optimized setting that we have in terms of middleware. So yes, this is sort of the summary of this particular slide, given that you've already seen it. So the major milestones that we are working towards in the next 4 years are that in this year we will have a demonstration of a quantum-centric supercomputing algorithm. So what I mean is that we'll have a physical, we already have a physical connected system established between one of the best quantum computers we have today and then one of the best supercomputers that exist in the world. So we are working towards the most powerful demonstration that exists in terms of a hybrid quantum classical algorithm that leverages the advantages of both of these to the best possible manner, and in simulating a scientific computation algorithm better than just leveraging the classical supercomputers alone. So that's one of the things we are working towards, and there are already some initial results in there. Maybe that's covered in some other talk, right? And actually, the algorithm that Kalyan will cover next is one of the leading candidates here. And then next year, the goal is to demonstrate this quote-unquote quantum advantage. Maybe it's probably half a talk in itself to sort of illustrate the definition of quantum advantage, because there are many similar terms that you hear from different companies in quantum computing, and in fact from IBM itself there are very similarly worded terms that you hear. But the goal here is essentially to demonstrate that there is a verifiable way that we can demonstrate that an algorithm that also leverages quantum computers outperforms the best classical algorithm that exists, right? And there is in fact a paper that we wrote on it that goes into the details of it. And then this all builds to a scalable end-to-end error-corrected quantum computer that we are like building up towards in the next 3 years. Okay. Okay. So now, when I say quantum platform, this is one level of abstraction, like one level of one type of an overview that you can think of. Okay. Quantum platform, like I said, had to be rebuilt from scratch compared to like how any computers existed today. So essentially, a quantum platform end-to-end contains hardware, middleware, and software. What do we mean by what are all composed of hardware? The quantum chip, which contains the core qubits, and then also, let's say, the closely tied, the quantum processor contains the control electronics that let's say stores information in the qubit, performs different gates in the qubit, and so on, right? Measurements and all the necessary operations that you want to do on the qubit are done by the control electronics present in the quantum processor that interact with the qubit, the chip in a scalable manner. And then on top of that, you will start seeing components analogous to what you have in our current computer architecture today, which is, let's say, sort of analogous to firmware, okay, that, that scalably passes along, that does some kind of a low-level compilation and also scalably interacts with the processor, right? And then you also have components that, quantum computers are not going to be physically available in different places that we tend to use, like our laptops or even our PCs. They will almost be in a data center in the near future, or maybe much longer, based on what it needs to maintain that reliably. So we will have these serverless components that expose quantum computer through cloud. So there are these levels of software that or middleware that expose, that enables a easy usage of quantum computer. And like I sort of alluded to in the earlier slides, a quantum computer is not expected to be used alone. Okay, so this is not going to solve every problem that we want to solve. And we expect quantum computers to be very good at solving some subclasses of problems that are useful. And we will continue to use traditional computing architectures that we use today, like the traditional CPUs, GPUs, or FPGAs, or AI accelerated units, and so on. So those will also exist, and there will be some classes of problems where quantum computers will significantly do better than running it on the classical software. So we will need one level of middleware that efficiently and scalably orchestrates between the quantum computer and the traditional computing architectures. Okay, so these are all one level of middleware, and going up, there are also things like the traditional operating system and compilers that we need to build, right? And they all have to be rebuilt to make the best use of the quantum resources. So one type of compiler is actually present in the core Qiskit SDK that I will go into a level of detail in throughout most of this talk. And then there are also the traditional operating system. Okay, what's the operating system? It's mostly efficient resource management of the processor, memory, storage, and so on. That's how our current operating systems are, and very similarly, we will have to build an operating system here for a quantum computer. And so going up a level, we will also, let's say in terms of software, right, one is certainly the compiler and let's say the programming languages and the sort of the standard quantum information libraries that you need to build here for programmers to use. In addition, we also want some of the optimized versions of core quantum algorithms being composed together, because it's a very evolving field. So when a research comes up, there are all these add-ons that have the most optimized implementation of some of the state-of-art modules that can be reused across different algorithms, or that can be combined in different ways for different applications. So you can think of these as one type of application enablers. And at the top level is the traditional, let's say, applications catalog or functions catalog that has optimized workflows that sometimes uses different parts of the stack in an optimized manner for specific applications. That's the tradition. That's, let's say, the typical application function. There are also other variants of optimized workflows that will be that are typically used and needed across different quantum algorithms. So this is one preview of how you can think of a quantum platform that we are building, going from hardware at the lowest level to the application software at the top. Okay. Any questions before I go further? Okay. Yeah.
Software tools, right? So, what's a percentage or what kind of expertise we would need for this layer?
So there is a way you can already run this without any real understanding of the hardware. But of course, the better understanding of above the qubits and processors, you barely need any understanding. You don't need anything at all. But sometimes there are something about the noise characteristics or something about the hardware connectivity. Okay, so there is some information about the hardware that is useful if you want to optimize better than what we have today. But there are some automated tools that are already there that you can leverage to abstract out some of these.
Because when you say data center, we are not going to touch the hardware.
Yeah.
So we are going to do it anything remotely only, right? So it's more of learning.
Yeah, that way you don't need any connection to, you don't need any understanding of the hardware from that point of view that you're asking. You can program from your laptop and connect to the hardware, and there are already tools available to do it. And I'm pretty sure during the Fall Fest, they will have some runs that some exercises that will make you run through the real hardware also.
So what's the commercial or free tier equivalent available for us to try out? Anything available in that layer?
There is about 10 minutes of hardware access per user per month that's free. And on top of that, if you want details, I think there is a website that goes into pricing of different models that are available.
Sure, thank you, sir.
What's the AIU, by the way? Their high performance classical compute.
Oh, it's okay. This is just a representation for AI units, but you can think of it like any specialized AI optimized hardware.
Okay.
That's just a generalization of that.
What did you say again?
Just a generalization of a typical AI optimized hardwares.
Okay. And could you explain how Qiskit is being integrated with HPC with like high performance computation?
I see. So that is not really something I have as part of this talk, but if you go into some of these plugins that are available in the Qiskit platform, right? So typically HPC architectures, almost most of the HPC users in the world. Right. Okay. That is how Qiskit exposes it. But I think if you come from the top level down, there are all these tools that enable you to have an easy integration to HPC systems. And if you look at the core Qiskit, that also exposes a C API. So rather than typically people use a Python interface to code into Qiskit, but there is also a C interface here so that you can easily run it along. Combine it with the traditional HPC programs. Because
what is it called? The interface, the C interface.
There's a C extension. Right?
I have no idea what that is, so I'm just asking the name. C API.
Yeah.
Okay. All right, fine.
It's just one way for you to write Qiskit program in C.
Oh no, that's the name of it is C API.
Right.
Okay, fine. Thank you.
But essentially, like these are the other tools, like the Quantum Resource Management Interface, Slurm. Slurm is a very popular tool in the HPC community that they use. So how to integrate Slurm into this, and Qiskit serverless is also adapted to ensure that it's easily integratable with HPC architectures and so on. Yeah.
Okay, thank you.
Good afternoon. How does the Qiskit code assistant help in quantum programming?
Okay, I think you should use it to see.
Yeah.
It's supposed to abstract out all these. Like there are different. One of the most promising features, the main features we have right now is if you write a natural language text, it will automatically convert it into Qiskit code. There are also some more things that are coming up, but essentially that's the thing that you have today is natural language to code.
Yeah, understood. Thank you.
Okay. Yep. All right. So these are the three main abstractions of, three main levels. This may be a different way of formulating this slide, but just in terms of Qiskit and the higher level libraries. The core is the Quantum Information Science Kit, Qiskit, that contains the core compiler and the Quantum Information Science modules. And then on top of it, we have modules for integrating with HPC computers and for ease of programming with them. And then on top of that, I talked about optimized like algorithms or like modules from certain research papers that are made easily available to use in your like quantum program. So that's add-ons and function templates. Okay, so we try to improve Qiskit along 3 dimensions. First is, of course, the speed of compilation. Okay, we want to ensure that this is the most performant SDK and the compiler that exists for quantum computing. We also want to be the best quality one. By that I mean the output that's produced. I mean, what is a compiler? It converts a high-level user program into an optimized intermediate representation or something, a low-level set of instructions that a hardware can understand, right? So what we mean by quality is that we want Qiskit to have the most optimized equivalent computation or intermediate representation output after passing through our process, right? So that's the metric we aim towards. And the third thing is also extensibility. So we want Qiskit to be easily extendable for any application workflow or the other tools, other quantum tools you want to build. Okay, so this will contain the core compiler and the core modules. And anyway, that's just the like it was mentioned in the introduction. If you think about the traditional computing architectures, there is GCC. It was initially written for C, but I think it's a bit more than for the C program itself. GCC has become the standard set of compiler tools which are extended for by most compilers that you have today. And then libc is like the standard library for C, and there are similarly standard libraries for Python, Java. Like all the languages have their own standard libraries which have algorithms that are typically used by almost everyone who writes something using that language, writes a program using that language. So similarly, we want Qiskit to have the most optimized implementation of all the commonly used algorithms. So hence, if we have that and if the interfaces are proper, so we want to strive towards that for it to be the most extendable or the best, easiest project for others to build quantum programs and tools on top. And anyway, like right now, there are surveys which say that it's used by around 70% of the quantum programmers in the world for many years running. And this is also, if you had seen one of the slides, this is the core of the tool that had been used by like almost like most people working on quantum computing and all those collaborating with us to write quantum applications on our quantum computers. Okay, so for the rest of this talk, we will focus on some of the core modules of Qiskit. When I say Qiskit, I mean the core Qiskit SDK. And what is core Qiskit SDK? It's whatever that's present in this GitHub library, github.com/Qiskit, in that organization, this Qiskit. So this is what we mean as the core Qiskit SDK. And right, as a single slide summary, what is Qiskit? It's an open source software development kit for quantum computing. It's open source with an Apache 2 license. And this is the link that I showed in the previous slide where it resides. It started in around 2017, a year after the launch of our IBM Quantum Experience, through which we could access quantum computers through cloud. It had provided a Python-based interface to program for quantum computers. And very recently, like I said, it also had a C extension. In addition to being open source, we also try to actively work on making it quantum platform and agnostic or vendor agnostic. So we want it not just to be performant and easily working for our superconducting based quantum computing architectures. We also want to make it agnostic to any superconducting based quantum architecture or any other quantum architectures as well, like be it ion traps or neutral atoms or anything else, right? All right, so the core of it includes an interface of programming, a quantum computer, a quantum circuit compiler, and then certain interfaces for running circuits on hardware. So these are sort of the some of the main components of it. Earlier, the core Qiskit was written in Python itself. It's not just exposed Python API for programming. The core of it was also written in Python. But very recently, we have started transforming the core of Qiskit to Rust for performance and reliability reasons. And we continue to expose a Python API, and recently also started exposing a C API for those who want to write programs on top. Okay. So this is one summary of the different modules that are present in the core Qiskit SDK. You can see it sort of roughly across 4 categories. These 4 categories relate to what we call as 4 stages in the Qiskit patterns. So that's just an abstraction, we thought it's easy to think about for anyone wanting to program in a quantum computer. Okay, so when you write a quantum program, the first stage of it is trying to map the problem statement that you have into a quantum circuit or a quantum program. Okay, that's the first step. The second step is to optimize that quantum circuit that you wrote. The third step is to execute that quantum program, okay, or the optimized quantum circuit. And then the fourth stage is for post-processing, okay. So the fourth stage is to sort of post-process using classical resources, whatever the results that you obtained from running a quantum circuit on the quantum hardware. So if you look at it, the mapping, optimizing, and the post-processing are all done on a classical computer, and this core part of executing is where we use the quantum hardware, right? So this is all sort of preparing towards running on the quantum hardware and then post-processing. So if you roughly categorize the modules of Qiskit across these stages, so we have sort of the circuit library, like there is also DAC circuit module, which is the way we represent a quantum circuit for processing through Qiskit. And then there are also these quantum information modules that will cut across these. And then the optimization is where the core compiler or the transpiler comes in, which contains various pass managers and so on. And then CASM and QPY are the 2 intermediate representations we will output an optimized circuit. So you can roughly think of the input as a circuit or a DAC circuit. And after we run through the compilers, we produce an optimized intermediate representation, which is either CASM or QPY. There are 2 formats that we use. And then sort of these connects to the primitives is where the SDK helps in running it on the quantum hardware itself. This optimized IR is then further compiled to the low-level sort of pulses that are sent to the hardware to execute the gates that we want to execute. And then there are these results and the visualization modules that will help us in visualizing the results, and actually some of these prior modules also help in post-processing the results. Okay, so these are some of the main modules of the Qiskit SDK, and there are many sort of closely related components. So for example, the C extension of the core Qiskit, there is something called a Qiskit runtime that exposes in easy access through cloud. So sort of the client of that runtime is for Qiskit is also here. And then there is a library called BenchPress that handles all the benchmarking of Qiskit and different layers and tries to come. All the performance results that I mentioned in the previous slides were through running bench press. And there is also a compiler for fault tolerant, there's a fault tolerant compiler that's being built that will make it easy for us to write programs on a fault tolerant quantum computer coming up. And then Qiskit Air is the classical simulator module that you can either run it for some simple classical simulations, or more importantly, as an initial stage to debug your quantum circuit before you send it on a real hardware. Okay, so this is one other, one more level of details into this. Like I said before, there are still these four sort of demarcations, of 4 stages: map, optimize, execute, and post-process. So this quantum circuit library, if you look at it one more level of detail, it contains sort of the standard gates, and then it has some different control flow modules, and have a way to specify different classical qubits, parameters, and to introduce timing delays. So whatever different things that you want to write in your quantum program, or as for a core quantum circuit, that is in this quantum circuit library. There are also different ways of synthesizing different other representations of a quantum program, and that are some part of synthesis. And then there are some of these, okay, maybe I'll come to quantum info later. So once you have this quantum circuit, DAG is one way of representing the quantum circuit and gets into pass manager. So this particular module is where I will spend around 20-30 minutes of my talk around. So, but this is where we convert the high-level quantum circuit into an optimized form. And yes, primitives, like I mentioned in the previous slide, it helps us execute this on a quantum hardware, and you do post-processing. And this target is a way where we represent the characteristics of the backend hardware or any other backends on which we intend to execute this program on. Okay, so this is also important because there are certain characteristics of the hardware, and anyway we want, like, Qiskit is extendable to like any type of quantum platform, right? So it's important for us to specify the kind of target backend we want to execute, so that the circuits are optimized for the characteristics of the backend that we want to execute. Okay, so it's important. Target is the place where we specify the characteristics of the underlying hardware. Okay, there are also different kinds of visualization modules to help us visualize the results or to help us debug, and then different serialization, like I mentioned, like DAG. Actually, like eventually, the intermediate IR that we'll try to like output is CASM or a QPI format. Okay. So roughly how did Qiskit evolve? You know, in the earlier days we had, I think, around 45 or 46 minor releases of Qiskit, where we, from 2017 till I think 2023, right? Or in fact, okay, yeah, before 2024. We have had these minor releases, yeah, okay, till 46 and 46.3. So there were so many minor releases. And then one of the major milestones for Qiskit was the release of Qiskit 1.0 that standardized the APIs, and it had a reliable sort of API lifecycle, so that to maintain backward compatibility and for us to sort of have a expectation on, okay, how long we expect to support an older version of Qiskit, and when is it needed to transform to a newer version, and so on. So the standardization of API happened here. And it's actually critical, more critical than you realize, and it's very hard to achieve than we realize, because quantum hardware evolves at such a rapid pace to, you know, like go from one 5-qubit system to the 150-qubit system, and even going forward, it sort of evolves at a very rapid pace that the modules above it also has to evolve rapidly to keep up with the hardware changes and to extract the best out of the hardware, the current generation of hardware we have. So breaking changes to the API are sometimes mandatory, almost necessary, because it's almost impossible for us to think in the future beyond a certain extent. So at least we want to standardize how we make breaking changes and then evolve this Qiskit. And after 1.x, I mean after 1.0, there were two main goals that we worked towards. One is performance, and second is support for HPC integration. So one of the core of the performance goals was conversion of some of the core modules of Qiskit into Rust. At some point, I think we wish to convert almost all the useful modules in Qiskit to Rust, and all the new modules also will be developed in Rust. As if you don't know, Rust is a programming language that has been very popular over the last decade or so for writing programs with memory safety and performance and reliability. Okay, so converting Python to Rust very often gave 2x, 3x performance quite easily, if not much more, very often. And of course, it also had a lot of reliability. So due to that reason, it was very popular in the cryptography community because secure implementation of a theoretical algorithm was critical. And there are many sort of reasons for which we thought it's also critical for the core of Qiskit SDK to be in Rust. So including performance, of course. So that was one of the major things that happened, towards working towards Qiskit 2.0. And the C API development of it was also the second biggest thing for Qiskit 2.0. Okay, so that is where we are in. We are, I think, in 2.2 Qiskit version, working towards 2.3, and in the future, when we work towards the future, the next versions, we will have, let's say, support for fault tolerance and other things coming up. Okay, so maybe I'll just quickly run through this. But earlier, if you write, this is not sort of the exact sort of way that this slide has to be talked about, but if you look at it from a different angle, the way that you could use Qiskit before was you had Qiskit circuit, and there was, or you can also write a CASM, the intermediate representation program, in Qiskit, and you can use a Python extension to run it. Okay, but right now what we have is the core of most of Qiskit in Rust, and then you can either have it's used by both the Python extension and the C extension. So you can write Python-based scripts here, or you can write a C program here. And there are also certain ways you can interlink between those two. Okay, and since we have a Qiskit C API that also, due to the different tools that had been developed over the last couple of decades, so it is also easy to extend this C API for other programming languages. So there are already extensions available for C++, Rust, Julia, and so on. So if you want, for whatever reason, I don't know, if because of your favorite languages, C++, Rust, or something else, or for whatever reasons that you want to integrate quantum programs into a different application, and that other application already exists in, I don't know, Julia or C++, okay? There are also extensions to Qiskit available for that. The interface is available for that. Because we have the core, we have the core C API, it becomes easy for us to extend to other programming languages. Okay. So now I will get to the second sort of half of the talk, or depending on the time we have. So this part, what I call as the core transpilation or compilation module that we have, right? So I will go into one more level of detail on what we do during this compilation at this point. Okay, so you will write a high-level program, and then you probably don't really see what happens underneath, right? So this rest of this talk will give you a preview into how do we convert this high-level program into an optimized intermediate representation. Okay. And yeah, I think, like I said, we will sort of use compile and transpile interchangeably. We had used the term transpiler, and maybe compiler is one of common terms. I'll just use it interchangeably. So any quick questions before I go into this? Okay. Okay. So, I guess, how many of you are from computer science? Okay, most of you. And physics? Okay. Yeah, so that sort of is, I think, about 90-95% of the audience, CS plus physics. I think for the CS students, or actually for anyone who programs, it's we don't need to motivate why we need a compiler, right? Like when we write a program, we don't intend to make it in the most optimized manner. Even if you're writing a high-level circuit, which we barely do in a typical computer program, but let's say even if you're writing a quantum program in a circuit form, we care more about the functionality to be correct. We don't really care about the most optimized version of the circuit to be written, right? And that has always been the case, even if we write at this level. But of course, we also write at a high level, using a high-level programming language. So when those, it sort of is necessary for something like a compiler to convert this high-level abstract circuit or a high-level program and output an optimized circuit for that specific hardware, right? So this particular circuit that we have, right? If you think about a very naive way of executing it on a hardware, here Q5 is a qubit that's connected to 5 other qubits, right? You can potentially choose a particular qubit so that it's not really connected to the other qubits, and you might have to do tons of swap gates and result in a bad compilation. Or also there are also simple optimizations that you can do, and you can just place it properly enough so that you minimize the number of swaps. But what you can see is that there are many other optimizations that you can do, such that you get or at least get close to the most optimized version of the circuit that you want to run. Of course, this circuit equivalence checking, or I don't know, getting the optimized circuit is a typical NP-complete, I don't know if it's complete, but at least an NP-hard problem. Oh yeah, maybe it's complete because it's easy to check. So, but which essentially means that for an arbitrary circuit, you don't expect to always have the most performant algorithm that's available deterministically. But this is a problem that we have to solve. So there are many different heuristics that we can apply that has a very good trade-off between the time it takes to optimize versus the quality of the optimized circuit. Okay, so I will go into some of those in the next few slides. And okay, this just illustrates that for this specific thing, an ideal output is all zeros. Okay, I didn't realize that this is all zeros. Okay, is it? Yeah. Let's say the ideal output is all zeros. There are also like other, there are noises associated and so on, so that it's not just the time it takes to execute the resultant circuit that is important, it's also that the quality of the output also varies, right? So having a good optimized circuit, having a good compiler is necessary for both these reasons. Because you see that a perfect output is close to this, but at least a good compilation gets close to this, but a bad compilation actually really produces almost a random output that this just has also a very noisy output. Okay, so what are all the different things that we'll have to care about to optimize for a compiler? The first thing is, of course, some of the hardware characteristics. Okay, so there are different characteristics or constraints, however you want to think about it. The first thing to note is that each hardware supports a certain class of basis gates. Okay, if you remember analogous to in the classical world, there is like AND or NOT are the basis gates, is at least one possible set of basis gates. You can also have NAND, you can also have NOR, but if you just have, I think, OR and NOT or just XOR, like some of these are also not complete basis. right? So it's of course necessary for a hardware to have a complete set of basis gates. By complete, I mean any computation can be represented in some combination of these bases. But there are also, different variants of basis gates possible. And for a typical hardware, due to the underlying physics and electronics, there are certain gates that can be implemented in a reliable and a efficient manner. So each generation of hardware has a certain class of basis gates that we work with. Okay, so for example, in one of the older generations of processors called Falcon, we had the echo crosses, the ECR gate, and then the CX gate, and RZ and SX and X. So these were the basis gates that we had, and of course in addition to measure and reset. And when we had our Eagle processors, which was the generation that we had like last year, the year before, and so on, I think there are probably some more Eagle processors that are still available on our cloud, I think. So where we had ECR, RZ, SX, and X, which is still a complete set of basis gates, but it's slightly different. And then in the newer generation Heron processors, we have CZ, RZ, SX, and X. So these are the 4 gates that we have. So whatever high-level operation that we write, whatever high-level computation that we write has to eventually be compiled into these 4 basis gates, okay, eventually. The second limitation is also the qubit connectivity. It's not always the case that, each qubit is connected to every other qubit, okay? So in our like IBM's the heavy hexagonal based connectivity architecture, each qubit is connected to 2 or 3 other qubits. So since qubits also have limited connectivity, and like for example the circuit that I showed like a few slides ago, it had a particular qubit Q5 that was connected to 5 other qubits, Q0 to Q4. So there is no single qubit that's connected, but of course like we can also try to optimize the placement of a qubit, and so that we can minimize the number of swaps and so on, right? Or even otherwise we'll have to introduce additional swap gates to at least ensure the computation is correct and perform as intended, right? So with the limited connectivity is another thing that we'll have to address during the compilation process. Okay, yeah, this is what I talked about. Yeah, one thing is of course introduce swaps, and second is to minimize, introduce swaps so that it's correct, and second is to minimize the number of swaps because swap is like expensive and noisy to work with. Okay, and depending on the basis gates, there are also different ways of implementing swaps. So that's another thing a potential compiler to optimize for. If you look at it, I think, yeah, in our Eagles we had the ECR gate, so this was the way swap was implemented. Now in Herons we have just SX and CZ. Actually we have CZ and then we have SX, so we can implement a swap like this. So yeah, first is identifying the correct set of swaps, the second is minimizing the swap gates needed, number of swap gates needed, and the third is also sort of representing a swap in terms of an optimized set of gates. In addition to all these that I mentioned before, there is also a very significant characteristic of a hardware that we'll have to take care of during compilation, which is the effect of noise. Each qubit, if you leave it alone, there are certain classes of noise that that acts on the qubits, or that noise that the qubits inherit, I would say. Like there are metrics like T1 time, T2 time that characterize the decoherence noise, like with respect to energy relaxation or the dephasing. Okay. There are also errors associated with each type of gate. Okay. Of course, single qubit gates contain a bit smaller set of much smaller errors. 2-qubit gates have higher errors, but there are errors associated with each gate. So these are also things that we'll have to optimize for. And if it's a multi-qubit gate, let's say a CZ or for example, when C0 had C0 1 to 2 had a certain amount of error, C0 2 to 1 had a certain amount of error, and certainly errors varied significantly across each pair of qubits that had connectivity. So taking into account all those and optimizing a circuit with respect to those, the noise characteristics of the hardware at that point of time is also critical for a compiler. All right, so these are all the things that we'll have to optimize for. And like I briefly mentioned earlier, this particular class called the target class in backend enables a user to specify the characteristics, all the characteristics of the underlying hardware that we want to like compile our program towards. Okay, be the error rates or the duration of the gates, some optimized pulse calibration of the gates, or like whatever. Like there are different characteristics of the hardware that are present in target, which will be used during the compilation process. And of course, for the traditional IBM hardwares, there are already these classes that are pre-built and available. If you want to use Qiskit to compile your program to a different hardware architecture, you can use this. Okay. How much time can I use? 10 minutes? Okay. Or I will take more of Kalyan's time. Okay. So I will quickly go through this, the transpiler process. Okay. So this is the core set of steps that we do to convert a high-level circuit into an optimized thing. To start with, how do we represent an input circuit? We use a DAG-based representation, a directed acyclic graph representation to represent the quantum circuit. DAG circuit has, let's say, something like this, right? The nodes represent the qubits and the operations. Okay, so the input nodes, the operations that are performed. The greens are the input nodes, sort of, and then, okay, I don't think the color representation is that accurate. Yeah, so let's say there are input nodes, and then there are operations, output nodes. So these are all represented as nodes in the DAG. And then the edges track the label of the qubits that are passing through these different operations. So for example, let's say there is this particular gate which takes in, it's a 2-qubit gate, it takes in Q0 and Q1 as input. And of course, I mean, in quantum, we like retain this, right? So we have Q0 and Q1 going as output. You can just track, trace a particular qubit where it's going, right? For example, if you look at Q1, it first had a conditional RY, and then it goes through excitation preserving and then a measurement. So Q1 has conditional RY, excitation preserving. Yeah, barrier is just a no-op gate, and then you have a measurement, right? And then the output of the measurement goes into, mesh 2. Oh, by the way, okay, I think now I understand. So these greens are actually input nodes, input qubits, or input classical registers. So input quantum registers and input classical registers. And then these red like color, these are for the outputs. And then the intermediate things are all the gates. Okay, so these are the nodes, and then the edges track the qubits involved, or the classical bits involved. Okay, so we believe this DAG-based representation simplifies how we track the circuits and analyze it and so on, and it also makes it easy for us to perform different optimizations. Okay, and at a high level, our transpiler is composed of like there are different ways you can optimize a particular circuit, right? Each individual unit of optimization that you want to perform is called a pass. A pass can be let's say as simple as cancelling redundant gates. Let's say you have, I don't know, 2 or 3 consecutive gates and then you want to cancel it. That can be a single pass, right? So that way, I think there are many different kinds of simple optimizations that you can do, and a single algorithm of that is called a pass, right? I think there are 100+ passes in the Qiskit transpiler. One high-level abstraction is called the pass manager. You can have pass managers for some high-level tasks that you want to do. Okay, so let's say you can build a pass manager for layout operation. Layout means you want to map the virtual qubits in the input circuit to the physical qubits in the hardware, right? You want to see, okay, like there is Q0 to Q5 I had in that example circuit, right? And let's say we have a 156 qubit hardware. So Q0, what is the mapping you want to have for Q0 to which qubit in the hardware? So those 6 qubits, you can map to any qubit in that 156 hardware, right? So that's the layout. You can have let's say layout operations, you can have a pass managers for layout, right? All these pass managers maintain this so-called property set. It's a high-level context that you maintain throughout the transpilation process. It contains some information about the circuit, like the depth, number of qubits, some commuting sets, and also it has like where you want to end your optimization of the circuit, like where you want to end the transpilation is also where these are all in the context. So like I mentioned, the basic unit is pass, and then you can compose pass managers. Qiskit by default has a preset pass manager that has 6 stages that we'll briefly go into. But there are also, it's very easy for you to write your own pass manager that has your own pass, or you can even have a pass manager that composes the 100+ passes in any order that you want to run. And you can also you can have multiple pass managers, so you can sort of sequence between them in whatever way you want. So essentially, it's completely pluggable and extensible. You can write, there are many different unit components for you to optimize a circuit. There is a generic sort of optimized preset pass manager that we have that we believe works the best for an arbitrary circuit. But if you have a special circuit that you want to run and optimize for, you can sort of reorder this or introduce your own optimization of circuit in whatever way you want. Okay, so what do we have in our preset pass manager? It consists of 6 stages. The first stage is called the init stage. It essentially does 2 main things. First thing that init stage does, it decomposes any 3 qubit or 3+ qubit high-level gates into just 1 and 2 qubit gates. So the first step of init stage is just a decomposition of a multi-qubit gate in 3+ gate into a 1 and 2 qubit gates. After that, for example, what that might mean is, okay, you can have this so-called excitation preserving ansatz. That is one thing that you will very often see, right? And you can break that, if that is a single thing that you write, breaking that down into a single and 2 qubit gates is the first thing that we do in the init stage. And the second is some very simple set of optimization passes that you run. Okay, so example, if there is some set of gates equivalent to identity, you remove that. And then if there is a gate that's sort of 2 consecutive CXs, you cancel that, and so on. So simple optimizations you do. Okay, so that contains the init stage. The second stage is called the layout stage. Like I mentioned before, it is the stage that maps each qubit in the sort of the input circuit that we give to the particular qubit in the hardware. Okay, it is actually quite critical because of the different connectivity involved with the qubits in the hardware, different noise associated with it. This is one of the critical stages in correctly or optimally mapping a virtual circuit to a physical set of qubits. And it actually has sort of 2 high-level stages. First is called the VF2 layout pass, which essentially, if the input if the connectivity of the input circuit already ties into the connectivity required in the hardware, it's easy. This pass does some finds isomorphic subgraphs in the connectivity graph of the hardware. If there is one, it already assigns it, and especially assigns someone which has the lowest error rate. But there is also an optimized pass if there is no exact mapping that's possible. There is a particular algorithm called Saber, which also it finds the layout while also minimally introducing the swap gates required for that. Okay, so I mean, maybe we don't have time to go into that algorithm. And like I said here, okay, so next stage is called the routing stage, which essentially inserts the swap gates wherever necessary. So the particular Saber algorithm does layout and routing together. It does the qubit mapping while also optimizing for the swap gates necessary. So once you do this Saber, you can also run this VF2 layout algorithm that I mentioned to, if there are equivalent things, we can minimize the error there. Okay. So after layout, the fourth stage is called the translation stage. So in the input circuit, we can use an arbitrary set of gates, right? And like I mentioned before, each hardware has a certain set of basis gates. So this translation stage is the one that converts arbitrary set of gates into basis gates that are supported for the backend that we want to run on. Okay. After that, it also runs, in addition to that, it also runs some high-level synthesis, which anyway I will let you defer to later. And then the fifth stage is called the optimization stage, which does like various set of optimizations. I mean, here, this is where, you know, there is like a very high trade-off that you can take between the longer that you want to run the compilation process and to the most efficient circuit that you want. So it's up to you to have different levels of optimization possible. So there are different algorithms here I thought I will get into, but I think this is all publicly available content, right? So you can go to transpiler stages and see what are all the different optimization process that Qiskit runs at this fifth stage. And then the final stage is called the scheduling stage. You have the optimized circuit, and this actually goes into sort of a level of detail. So let's say this is the circuit that we want to run, and let's say if you look at this Q3, there is a lot of gap in between this particular operation and the CZ that follows here, right? So you want to minimize the idle time for a particular qubit, so you space out the operations that are on a qubit such that there is no qubit which has a very high amount of like idle time at any point of time. Okay. So if you go through all these things, with every sort of release of Qiskit, we see a very, very significant improvement in runtime and quality of Qiskit. And maybe I'll just sort of, there are, I mean, in addition to the traditional passes, algorithmic based optimization and compilers, we also have AI based compiler passes that are there in the Qiskit transpiler service. And there are these different passes for error mitigation and error suppression algorithms. Maybe this particular thing is an independent lecture in itself. And you know, this is sort of the final summary of a layout of different compiler tools that are available, right? In the core Qiskit SDK, you have the preset pass manager, or you can plug in any set of passes and like transpiler plugins that you can use. You can also bring transpiler plugins from outside that you think can easily, it can work with some of the other transpiler tools that we already have in the SDK. These are the things that you can run locally. And in addition, there are also, you know, AI-based transpiler passes or some of these error suppression passes that can be run in the cloud. Okay, and each of them have their own advantages and I mean, I wouldn't say disadvantages. There are like different advantages for different classes of circuits that you want to optimize for each of these. So that's something, yeah, I thought I will cover, but anyway, I'll skip for this. And in Qiskit SDK, there are only two main components, right? The biggest, one big part is the transpiler that we covered. And just to summarize, there is also this thing called Quantum Info that is another big component. But that's something I will let you guys explore by yourself. And of course, everything is open for you to try out. The Qiskit SDK is open source. The learning platform, it used to be like mostly internal. but a few months ago we made almost everything that to be open here. This contains everything from the foundations courses in terms of core quantum information or some algorithmic foundations, or some modules with respect to specific application libraries or some special quantum algorithms, or some, I don't know, business foundations. I don't think that's anyway, if you're curious, you can look into that. In addition to that, there is also a lot of tutorials for you guys to look into, right? You might have covered some of these throughout the Fall Fest, I believe, some of the tutorials. Okay. So essentially, if at all there is any like research paper that comes out, if we think the algorithm that is proposed in the research paper is reusable across, like if we think there is a long-term like a value in that, there is a very optimal implementation of that is made as a tutorial, and also some of those are also repurposed as add-ons for a easily plug-in. So all this is open. It sort of contains everything from foundation to the most advanced research that exists. So and there is also, you know, some level of simulator for you to get started, and 10 minutes of access per month per user for the hardware it's free. Yeah, it's up to you guys to, like, there's a lot of things for you to work with and take forward. And yeah, just an advert anyway, this is the month we have the application portal open for the next summer's internship. We typically, you know, look for the pre-final years. Yeah, whoever is interested, and yeah, I strongly encourage you to apply for this as well. Okay, thanks. Okay.
The first question is there an equivalent of an intermediate representation hierarchy in Qiskit, similar to how LLVM uses multiple IR levels?
I wouldn't say so. There is just, I don't think there are different levels of IR at this point. At least whatever is exposed is the QASM and the QPI, and they are also not hierarchical. I think they're just different IRs, I would say. So as of now, there is no hierarchy.
The second question is, does the Qiskit runtime environment perform any form of cache or JIT compilation for repeated circuits, similar to JVM's hotspot optimizations?
Okay, I don't think I know enough about JVM to answer that question. Maybe we do some of it. I'm just guessing, but I don't have a good understanding of JVM to answer this. Yeah. Do you know? No. But maybe if they can send the email, I will like explore to see and respond. Yeah. Cool. Okay. Thank you.
Thank you, Professor Dhinakaran. Now we have a small token of gratitude that we want to present from the IISc community for your time and your contribution to this event. So I would request Professor, please come on stage. A great round of applause. Thank you so much, sir. Now, the next talk is titled Diagonalization Using Data from Quantum Simulations. In this session, the quantum classical hybrid methods for diagonalization will be discussed. It will primarily deal with SQD and Krylov-based methods. We will look into the configuration recovery techniques required to correct incorrect samples and also discuss some implementation aspects. The presentation will be done by Dr. Kalyan Dasgupta, who is a research staff member at IBM Research. He did his PhD in electrical from the electrical department at IIT Bombay in the area of power systems. After his PhD, he joined IBM Research and worked on a variety of areas ranging from power systems, renewable power integration, application of geospatial data for agriculture, and many more. He has been with IBM Quantum for the last 3.5 years. He has been working in quantum computing applications and also on Qiskit development. So a great round of applause for our next speaker.
Can I use this one? Hello. Yeah. Maybe I'll just put it here. This is okay, right? Yeah. Okay. Does this work? Mm-hmm. Okay. This is work. That's not working. It's fine. Okay. It's fine. Okay. No problem. It's okay. So I'll be talking about diagonalization using quantum computers. So I guess you have already, you have speakers who talk about add-ons, and I'm guessing you have already heard about SQD, right? Sampling-based quantum diagonalization. So how many of you have heard of SQD? Okay. Okay, fine. So I'll go over the basics of SQD and some of the Krylov methods. And so you have some Qiskit implementation of these, these algorithms, and they are there as, as Qiskit add-ons. I'm sure you have heard about the terms Hamiltonian and stuff, right? So you all are kind of aware of the quantum computing terminologies, right? So you have heard about Hamiltonian and stuff. So majority of the problems in quantum computing, involves, working with Hamiltonian, finding the eigenvalues, the, the smallest or the largest eigenvalues, and chemistry or physics, problems in these areas and many body physics involves actually calculating the ground states, right, and excited states. That means essentially finding the eigenvalues of some ground state or some excited states, right. So that in turn involves diagonalization of a Hamiltonian. Diagonalization as in, like, if you have a matrix, you do some basis transformation and get it into some diagonal form, and the lowest element of that diagonal, or the magnitude wise, is the lowest eigenvalue, right. So I'm sure you have all heard about variational quantum algorithms, right. So how they work. So how many of you have heard of variational quantum algorithms? Okay, right, significant number of you. So see, in variational quantum algorithms, what we do is, so let's say you have this, Hamiltonian H, right, and you want to find the lowest eigenvalue of H, right. So what you do is, you first of all start with some, qubits in some zero state, and you have some encoding strategy. So encoding strategy could be it's a circuit essentially, some quantum circuit, some gates. So that prepares this zero state, basically takes this zero state to a state which is kind of, very close to the state that you want. The state that you want is essentially the, the state that is very highly overlaps with the lowest eigenstate, the eigenstate corresponding to the lowest eigenvalue, right. And then what you do is, you do further kind of a, operation on that reference state, and you expect that, when you take the final expectation, right, you would get the lowest eigenvalue. And what happens is, this is the part that quantum does. What the quantum does is basically prepares this state, and then you measure, and you take the expectation value and send it to a classical side. The classical side consists of an optimizer, and this optimizer, what it does is repeatedly asks the quantum side to keep sending it some more expectation values, and it kind of changes the parameters. When you by changing the parameters, we mean the the gate parameters here, and then eventually it converges to some state, and you consider that state to be the lowest eigenvalue, right? So that is how a variational quantum algorithm works, right? And you have several encoding strategies you can see here. The ansatz are also, it could be some domain inspired, in the sense that you could be, if you are solving a chemistry or physics problem, you already have known like ways to kind of create these ansatz. And also there are some hardware efficient ansatz as well. So because our quantum computers are currently do not have are not able to process, like I mean basically have noise, we cannot process a very big circuit, right? So we need some hardware efficient ansatz so that there is less noise. And also you have some optimizers that does the classical side of things, like the gradient based or non-gradient based this thing. So just interrupt me wherever possible, like wherever you have some doubts, we can have this as an interactive discussion, right? So are there any questions here, like any doubts here, like something needs some clearing? Yeah. Yeah, so the ansatz is basically, basically a quantum circuit, you can say, right? So what this quantum circuit does is basically takes you this reference state, and actually this is, I think, echoing a little bit, I guess. It's fine, right? Okay, so the ansatz, what it does is basically takes this reference state to a state very close to a desired state, right? So that's what the ansatz does. So when you have, let's say, some chemistry or physics problems, so you already have some known classical methods, and you kind of try to replicate that in the form of quantum circuits, right? And so there are some known ways. Of course, it consists of parameters, and these parameters can be updated. Similar to what you would do in a normal neural network, right? What do you do? In a neural network, you have these lots of parameters, right? And you have this back propagation, and you keep updating your parameters, right? A similar thing here, where you have a classical optimizer that keeps updating the parameters and checks which set of parameters is good enough, okay? Okay, so now this kind of methods have some limitations. I'll give you an example, like this paper, the first SQD paper had actually written about it. So for example, let's say you are trying to find the ground state of this molecule, right? So in this case, this Fe4S4, right? And here I'll show you why it becomes intractable if you are using this variational quantum kind of an algorithm. So this problem has 77 qubits with a good representation, a basis set, as in the kind of way you represent the let's say how the orbitals are expressed, right? So you have, let's say, 77 qubits that are needed for this kind of a molecule, and the number of terms in the Hamiltonian, right? So you have almost like of the order of 67 lakhs or 6.7 million, right? And for a precision of this order, right? This is the precision that is kind of expected in chemical calculations, right? So and if you need this, if you want this kind of a precision, the number of shots or the number of samples you have to take, scales as inverse, I mean basically 1 over the error squared. So that would mean some 10 to the power 20 kind of shots. Now, even if you like very optimistic kind of a calculation, like if you take 10 microseconds for a given circuit, to run this kind of a calculation would require you like 3 million years, right? So it's practically impossible to run this kind of variational quantum kind of algorithm for a realistic problem, right? So now what SQD promises is, or SQD or quantum centric supercomputing promises is basically you, instead of finding the expectation values, what you do is you kind of you work with samples instead, as I'll show, right? And it takes roughly 2 hours. Like you, of course, have a supercomputer working with the with the quantum circuit, and it would take you roughly about 2 hours. Right, and you can go through this paper, Chemistry Beyond Exact Solutions on a Quantum Centric Supercomputer, and that gives you the exact kind of parameters they have used, right. So this is the paper essentially, and you can see, so this nice results they have got using the sampling based approach. They have not gone through the variational way, but they have used a sampling based approach, and they use this the Heron processors, I think it was the Torino processor with 77 qubits, and alongside that they use the Fugaku supercomputer, which was based in the Riken University. So this was a joint work between IBM and Riken University in Japan, and they were able to kind of find the problem, solve the problem in 3 hours. So this is the layout of the sampling based approaches. So instead of the quantum side, like you calculating the expectation value, what you do is essentially you kind of generate samples, right, and these samples are then kind of used to create a subspace, right. So and the Hamiltonian, this H that we were talking about, is kind of projected onto that subspace, and then the diagonalization is carried out. So what it essentially means is, see, I mean, when you have, let's say, m qubits, right, so the number of states possible is 2 to the power m, right, and not all 2 to the power m states are are needed. So what you do is you kind of create a ansatz just like you had done for the previous one, but here the ansatz is already kind of with the optimized parameters, and then you collect the samples. Now these samples are expected to be very close to the the eigenstate that you want, and because they have a high overlap with the with the lowest eigenstate, what you do is you create a subspace, right. So using these samples, and this subspace is of the order of the number of samples. So let's say you are working with n samples, right, n, and this n is much less than 2 to the power m, like the number of states that are I mean you have when you have m qubits, right. And this Hamiltonian that you see is of the size of this matrix is 2 to the power m cross 2 to the power m, right. So if you are working with 77 qubits, right, so you can imagine how big the size is, like 2 to the power 77 cross 2 to the power 77. So that is like 10 to the power, more than 10 to the power 20, if I am not wrong, right. So now let's say you are working with, let's say, m samples, and m could be of the order of, let's say, 10 to the power 6, a million samples. So when you project your Hamiltonian from a space which is 10 to the power 24 or something to a space which is of the order of, let's say, a million, that is 10 to the power 6, and then diagonalize it, it's much easier, right. So it's easily kind of can be done by a supercomputer within an hour or two, right. So this is the process that basically a sampling based method takes, and this classical side essentially diagonalizes. So diagonalization, there are several methods. In this paper they use the Davidson method. So to kind of, it's an iterative method to kind of diagonalize, right. So any questions here so far, like, yeah. No, you are measuring all the qubits, but the samples you are limiting it to certain numbers. I'll show you. There's right, small rank approximation, exactly. Yeah, any more questions? Small rank approximation such that the lowest eigenvalues. Yes, the highest. So your answers has to be good enough so that the approximation that you are making has a high overlap with the.
Typically, when they do small rank approximation with say ML and all, the highest eigenvalues are made, but here we want the lowest eigenvalues.
Correct.
And sir, how are we creating the projection subspace?
I'll show you.
Okay.
Okay, so let's do some like basic calculations. Rayleigh-Ritz variational principle. Those who are, those who are in physics or chemistry, they would be aware of these kind of calculations. So essentially, what you do is you are trying to find the minimum eigenvalue of H, right? So that can be expressed as finding the minimum of this expression. So you have created a psi. And the psi is, let's say, parameterized with respect to some parameter. In this case, it's the gate parameters, and you want to find the minimum value of this expression such that it's normalized, the psi should be normalized, right? So this is the expression. Now if you see, psi is, can be expressed as a linear combination of my bit strings, right? So here UI are my bit strings. So bit strings as in the binary bit strings that we finally collect, right, at the end of the circuit, right? So I mean, when you measure them, it's always in the form of ones and zeros, right? So UIs are basically the bit strings in terms of ones and zeros, and the psi that you see is a linear combination of these UIs, and theta are basically the coefficients in front of those bit strings. Now my objective is to kind of minimize this Lagrangian. Okay, so you have this psi h psi, and subject to the condition that it should be normalized, right? So when you express this psi in terms of those bit strings, that is the expression that you get. Okay, and for minimization, of course, you have to kind of take the gradient of the Lagrangian with respect to your the parameter, so the coefficients theta and the lambda here, that is the the Lagrangian multiplier, let's say, right? And now if you kind of do this calculation, so what you get is basically are these equations, right? So what you have is this HP, let's say we'll call this HP as this kind of basically HP is the matrix that you get after going through these operations, right? So you have all these bit strings, right, UI and UJs, let's say, and you kind of project your Hamiltonian H onto the subspace created by all those bit strings UIs, right? I'll show you how we create that subspace, but let's say you do this calculation, right, UI, H, UJ. So basically this is HP is your projected Hamiltonian, right? And S is kind of the overlap or the kind of the inner product between the UI and UJs. Mind you, the UI are the bit strings calculated in the Z basis, that is ones and zeros. So they are all orthogonal to each other. So Sij essentially becomes an identity matrix. So what you have to solve is basically this problem here, that HP theta star is equal to lambda minimum theta star. So HP is of much lesser dimension, like size, compared to your H there, right? Because you are limited by this, HP is kind of limited by the number of bit strings you have decided to choose, right? That UI, the size of, the number of, the maximum of the index I, right? And so once you solve that, as you can see, your theta star is basically, it's solving an eigenvalue problem, right? Theta star is essentially your eigenvector. So the coefficients in front of UI are the eigenvectors, and lambda, the Lagrangian multiplier, becomes your lambda minimum, right? So essentially you have solved your eigenvalue problem. Any questions here? Like, it's a simple optimization problem. I'm sure you're all aware of Lagrangians and stuff. Okay. Okay, so yes, solving this is sufficient, let's say. Okay. So in optimization, you have this thing called Lagrangian, where you kind of you can consider that constraint, like the normalization constraint as a as a penalty bound, and the lambda as the penalty factor that that comes in front. Okay. So you can think of it in that form. Okay. So in this particular problem, see, they had the problem was very specific in that paper. The problem that they tackled was kind of very specific to a chemistry problem, where they were dealing with orbitals, right? And the orbitals were kind of segregated. So orbitals are essentially every qubit is represented by an orbital, right? Like and from our those who are not in chemistry, from our high school, from our high school chemistry lessons, you may remember, like you have these orbitals where the electrons kind of reside, right? And if a electron resides in a particular orbital, the state or the the value of that qubit, or every qubit actually there's a one-to-one mapping between the qubit and the orbital. So if a qubit has a state 1, that means an electron is residing in that orbital or in that state, let's say, right? And and as you remember, like you might remember from your high school studies, like you had like two kinds of spins, right? The top and the bottom. So we call it the alpha and beta spins, right? So here, what in this paper, they kind of, in this work rather, they kind of separated the alpha spins and the beta spins. And for example, let's say you are working with a problem or a system that has only 4 electrons, right? So if you see those bit strings, you need to have 4 ones, right? If you see the first bit string, there are 4 ones. The second one, 4. The third, and the last one also 4 bit strings. 2 on the the first set of bit strings and 2 on the the beta side, beta bit strings, right? So that has to be preserved. So you must remember whatever bit strings that you get, condition has to be met. The number of ones has to be constant, and it should be equal to the number of electrons having that particular spin. In this case, alpha and beta, right? And incorrect samples would be of this form, right? So if you have 3 ones, this would be incorrect bit strings. So there is a possibility, right? Because of noise or some gate errors or whatever, you could get all these incorrect bit strings. Okay, so finally, how do I create the subspace, right? Or create the projected Hamiltonian, right? So you have all these, the original Hamiltonian was of the size 2 to the power m cross 2 to the power m, and I am projecting it to a space which is n cross n, right? And n is much less than 2 to the power m, right? And in this, and how you create the projection matrix is basically through this method. Let's say you have u1 to un, right? u1 being the bit strings. So you do these operations, right? So the one that I showed in the earlier slide, right? So this operation here, right? So you do this operation for all the bit strings, right? And you kind of get the projected Hamiltonian, and this you can further diagonalize using some classical methods. Okay, so any questions here? Is it like, I don't know, is it being a little boring? I mean, you have to tell me, or I should skip some of the things, and it's okay, right? Okay, fine. Which these elements? Yeah. Okay, so these are calculated, like you are not inside the class, quantum computer. The quantum computer's job is to give you these samples. The calculation, this projected matrix has to be calculated outside classically. Okay. So for example, let's say your H is XIXZ or something like that, right? Some poly, right? So you have to, so you are measuring, right? Your X has to be measured in the Z basis, right?
So each term of H you will calculate using the...
Correct. For every term of the Hamiltonian is expressed as a sum of some poly strings, right? Yeah. For every term of the poly string, you have to calculate this. Correct. But remember, they have to be measured in the Z basis. Yeah.
Right. You do that on the quantum computer?
No, the quantum computer's job is to just calculate this, the bit strings. And the other calculations can be done outside. It's not so hard, right? Yeah. So it's a parity kind of a check. Okay. Okay, so I don't know, I mean, I'll talk a little bit of configuration recovery. Maybe I'll not go very deep into it. And so essentially, you see, like, as I mentioned before, you have these, so basically, you have these bit strings, and these bit strings need to have certain number of ones in the alpha side and the beta side, right? So let's say you're working with 8 qubits, let's say, for example, and the first 4 qubits are corresponds to the alpha side, and the next 4 qubits correspond to the beta side. Now these 4 qubits, let's say, need to have 2 electrons, let's say. So you need to have 2 ones here, right? The rest should be 0. Similarly, let's say you need 2 ones there, or it could be 3 or whatever, let's say. So you have certain number of ones need to be on the alpha side and certain number of ones on the beta side. The rest should be 0, right? So now how do you ensure, or whenever you get, say, some bit strings which are erroneous, that is, instead of 2 you, let's say, have 3 ones, or instead of 2 you have 1 ones, right? So you need to correct those samples, otherwise you will be wasting those samples. So you need samples which are kind of corrected. So how do you correct them? So normally, there could be several methods. In fact, it could be your work, research work also. How do we do what is the best configuration recovery process, right? How do you correct bit strings? It need not be some chemistry problem, it could be some other problem, but you need to have some condition on what the bit strings should look like, right? In this case, they have this constraint where the number of ones should be constant. So what we need to do here is, what they did in this paper on this research work is, they collected some data and based on some historical data, right, they found out what is the, basically they created this occupancy vector. So which is kind of some probability numbers. So for example, historically you would see what are the chances of this location, right, or how many times have we seen one in this location, how many times have we seen one in this location. They would do that calculation and they would have some probability numbers, and this probability number should add up to give you the number of electrons in, or electrons that should be here in this side, right, alpha side, and similarly for the beta side. So this is kind of a knowledge based thing, so where you have historical data and based on which you have created some occupancy kind of a vector. And this occupancy vector should add up to give you the number of electrons on the alpha side and number of electrons on the beta side. So n alpha, n beta are the number of electrons on the alpha and beta, or the alpha spins and the beta spins, right. So basically, you have some sample probability distribution. Let's say this is from historical data, right. This is some example that I am taking. So you would have created, some bit strings, and so this is something that you create, like, you have done enough number of experiments and from your knowledge you have created this database where you know what are the chances of, so for example, I'll tell you, let's say these are the samples that you have collected, right. So the probability of 1 here, how many times have you seen a 1 here, right? 1 is there in all of them, right? So with probability 1, I can say that, I will always find a 1 here. And the rest of them, you see, the ones are not actually consistent. Like here you have a 0 here, 1 here, 0 here, and so on, right? So out of the 5, 1, 2, 3, 4, 5, here you have a 0.2% chance or a 0.2 probability that you would have a 1 here. And similarly, you can do the calculations for the rest, right? And so based on that, you create a, kind of a occupancy kind of a vector based out of these probabilities, right? And so also you have a bit string Hamming weight. In this case, like the Hamming weight should be 2, like the example that I was taking, right? Like, so 2 electrons on this alpha side and 2 electrons on the beta side. So you have some, the alpha spin side and the beta spin side, the number of the Hamming weight has to be consistent. And you have some probabilities that you need to calculate, right? There are several methods to do it. So you can follow the paper. I have some slides here, like if time permits, maybe I can come back later, and if some of you are interested, I can come back later. Otherwise, I'll skip that portion. But so essentially, the end result is basically you kind of correct these bit strings, right, based on the historical knowledge and some probability that you calculate for a bit string to flip. For example, here I'll give you an example maybe, right? So let's say you have you have a bit string where instead of 2 you have, let's say, only 1, right? And from historical data, you know that this position has always had 1, right? So if you get a bit string where this bit string came out to be 0, there is a higher chance that this bit needs to be flipped in order to correct the bit sample. So there could be several other techniques to kind of correct all these bit strings, right? I could go on, and I mean there are some methods to do it. So maybe I'll skip this here, okay? In the interest of time, how you could do all that. Yeah, and also the occupancy vector also has to be updated. Maybe I'll just skip all this, okay? So, but I'll talk about this flow chart here, right? So how you calculate it? Sorry. So in this SQD flow chart, right? What we have done is we have so remember the answers that we have created was from an already optimized kind of set of gate parameters, right? So what that means is, unlike a variational quantum algorithm where the parameters were constantly updated, here the parameters were already kind of optimized. And so what you can do is you can directly take all the samples all at one go, right? And then what you do is you run the quantum circuit with the given ansatz, and you then sample the bit strings, right? The bit strings that you calculate in the next stage is you do the configuration recovery from some historical knowledge, right? So it requires that occupancy vector that I was talking about, that you have created using your historical kind of, or the knowledge that you have already, the knowledge based kind of thing that you have already, kind of prepared, and then create a probability distribution of all the bit strings. So now what in the work that what they have done is, out of all this bit strings that you have calculated, they created some k batches of d bit strings, right? So you have, let's say let's say for example 10,000 bit strings or 1,000,000 bit strings that you have collected, and you have created k batches, let's say some 100 batches of, let's say 1,000 samples. So you have and using this d bit strings, you would diagonalize your original Hamiltonian, right? So now the question is, every time you do this diagonalization process, you need to update your occupancy matrix, because from the knowledge of, from the the estimate that you get, right, your lambda value and the theta values that you get, you would be able to update your occupancy matrix, because you are collecting new set of samples, new set of correct samples, and that kind of informs your occupancy matrix that you create. So basically the new samples that you are kind of creating or getting updates your knowledge about the occupancy matrix. So every time in every loop you kind of update your occupancy matrix, and your correction methodology also improves over time. So when you start off, you don't have enough knowledge, your bit strings, corrected bit strings will not be of that good quality. So as you keep on iterating, you start getting more and more information about the occupancy, and your bit strings, the quality of your bit strings also improves, right? And you have better kind of subspace that you are creating, and the final projected Hamiltonian would be even better in that situation. Okay, so any questions so far? Is it a little boring? Like I need to get some feedback, like should I cover something else, or is this becoming a little, okay. Okay, so I'll talk about the ansats, okay. So I think somebody was asking about how the ansats looks, right. So remember, in this particular situation, we needed to preserve the number of ones here, right. So those kind of ansats are called excitation preserving, and I think Dina was also talking about some excitation preserving ansats. So in this kind of a situation, right, you have to keep in mind the hardware, like the layout of the qubits and all, because when you are creating these ansats, right, you have some 2 qubit gates, you have single qubit gates. Single qubit gates are not a problem, but whenever you are creating 2 qubit gates, right, so C0s or whatever, right. So in such situations, so you need connections between qubits that could be far apart, and if you arrive at such a kind of a situation, you need lots of swap gates, and that in turn increases the depth of your circuit, and that again in turn leads to lot of noise. So you cannot have that. So you need to be very clever about how you kind of how your ansats is, and how you have mapped the circuit to the the transpilation process, let's say, to the hardware. So in this case, this k alpha, k beta are single qubit gates. This j alpha alpha are essentially on the alpha side or the alpha spin side, and beta beta is also on the beta spin side. These are when you have 2 indices, like they are essentially 2 qubit gates. This is also a 2 qubit gate, but here there is an entanglement or 2 qubit gates between the alpha and the beta side. So this is the problem area. Here this is not a problem because they are single qubit gates. These are 2 qubit gates, but they are they are a limited problem because you are on the same side, right. So you can kind of cleverly kind of orient your qubits on this side and have those 2 qubit gates. But here if you have to connect this one to this one, let's say, right, if you need entanglement between this and this, so you have to see how you map your qubits to the hardware qubits, right, the logical qubits to the physical qubits. So you have to be very careful. So I'll not go into the equations and all. So essentially your excitation preserving ansats works in this way, okay. So you have this RXX gates and RYY gates, and if you kind of do the calculation, right, if you do the matrix multiplication, you will see you will get a matrix like that, okay. And let's say the thing about this kind of excitation preserving ansats is the number of ones will always be constant. So for example, let's say you do this U, multiply with 0 and 0, you'll always get a 0 and 0. If you have multiplied, like if you do the operations on a 1 and 1, you will get a 1 and 1. If you do it with 0 and 1, you will see a superposition of 0, 1 and 1, 0. So again, the number of 1s are always preserved. Here again, like if you do a operation on 1, 0, again you get a 0, 1 and a 1, 0. So the number of 1s are always preserved, right? So this kind of an ansatz is used in our chemistry kind of problems, okay? and essentially the main building blocks of this kind of an ansatz are the RxX and RYY gates, okay? Okay, so I'll also talk about how the mapping has been done in this case, right? So in this case, as you can see, like the 2 qubit gates on these red ones are the alpha side and the blue ones are on the beta side. So so whenever you had needed entanglements between on the same side, like on the alpha side, the entanglements were done on adjacent ones, like adjacent orbitals were entangled, right? So as you can see, the red were entangled with their neighbors, right? But whenever it came to entanglement between the one that I was showing from the alpha side to the beta side, you have to do it cleverly. So in this case, the mapping was done in such a way so where the alpha side and the beta side were nearby, right? So the alpha side qubits were mapped to in this way and the beta side qubits were mapped that way. So you needed just one swap here. So if you had to entangle between these two, only one swap was enough to entangle these two. Similarly, one swap is enough to entangle these two, and similarly for those two there. There could be other methods also in that case, right? So as you can see, there were no swap gates required. You can directly kind of entangle the alpha and beta side. So you have to see, based on your problem, you have to kind of cleverly map your logical qubits to the to the hardware. Of course, there are transpilation methods. You have those AI methods and AI kind of transpilation techniques that can do this for you. But this is something that one can think of on their own, and also while doing the ansatz, devising the ansatz, can think in their mind like what could be my ansatz such that I don't have too many swap gates, right? And I could position my qubits in such a way so that my circuit is not too deep. Okay. Any questions here? Like. Okay. Okay, I'll kind of omit this and I will come to the Krylov based methods. So any questions on regarding SQD, like overall, like have you understood what SQD method is? Should I start asking questions or something? Okay, somebody tell me what is the full form of SQD? Nobody? I'll give a prize. Okay. Okay, no, not to Devarthi because she already knows. I knew she already knows about it. So somebody else, what is the full form of SQD? Come on. Yeah, sampling based quantum diagonalization. Okay. But I guess you didn't say the full form, so I can't. Okay. Okay, so and so why do we project the Hamiltonian? Anybody? Yeah, that is the overall objective. So what is the purpose of sampling? Okay, let's forget the, projection. Why do we sample instead of going the VQE way? Yeah, anybody? Yeah. Yes. So the dimensionality is a big problem here, right? So the original Hamiltonian is very big. And as you saw, like VQE method, like if you go by the traditional VQE method, you could run into millions of years to solve them, right? So that's why you need to kind of kind of project it into a smaller subspace. I mean, smaller dimensional space. Okay. So I'll talk about the Krylov subspace based methods. You see, another way, like classically, how we kind of, diagonalize is or find these lowest or, the dominant eigenspace or the lowest dominant eigenspace, least dominant eigenspaces by a method called power method, okay. So where what we do is, you kind of multiply the Hamiltonian or the matrix we are trying to diagonalize repeatedly over on a given vector. So you choose a good vector, a vector that is supposed to have a high overlap, with the eigenvector that you desire, and you kind of repeatedly multiply this H, right? HV, H square V, H cube V, and you go on for a certain number of times, HR minus 1, and you create a basis with these vectors, right? V, HV, H square V, H cube V up till HR1 minus V, right? So now remember when we were doing the, in the SQD, we were doing the subspace kind of generating the subspace using bit strings, right? Which were all orthogonal in nature because they were zeros and ones collected in the Z basis, which is like an orthogonal basis. So all the, the bit strings were orthogonal, and when you do the inner product of Ui, Uj, you'll always get a delta Ij, right? And so the Krylov subspace is created by this method, right? And as you can see, this basis that you see need not be, an orthogonal basis, right? So V, HV, H square V need not be orthogonal to each other, right? But what it will give you is like, it normally converges to the dominant eigenspace. So I mean, and the reason is quite simple. Like if you express V as a linear combination of your eigenvectors, right? And if you keep repeatedly multiplying your H, what will happen is if you express this V in terms of your eigenvectors, so there's this lambda will come in front. So you'll keep repeatedly multiply lambda to the power, lambda square, lambda cube, lambda to the power r minus 1. And if a particular value of lambda is very high compared to the other lambdas, as in the eigenvalues, or a particular eigenvalue is very high compared to the other eigenvalues, this lambda to the power r minus 1 would be very, very high. So basically you would have created a space or created a set of vectors that are very high, with very high overlap with the dominant eigenvector, right? So I mean this is very common in power methods, like if you have come across power methods. So this kind of subspace that you create kind of converges to the dominant eigenspace, right? And you can write that in the form of like bracket kind of a notation in this fashion, right? And this need not be orthogonal, unlike in the bit string that we calculate. So if you are to calculate the non-dominant eigenspace, so for example, if you are to calculate the lowest eigenvalue, so you have to do the same thing, but instead of H, you have to do the H inverse square, like H inverse or H inverse square and H inverse cube and so on, right? Okay. So for this is a note, like for ground state related problems, our objective is to find this kind of a eigenspace with the inverse one, right? So now, yeah. So given that this set of vectors that you have created, or this subspace that we have created, they are not necessarily an orthogonal basis. We have to kind of convert them to an orthogonal basis by using something called Gram-Schmidt orthogonalization. So I mean this is a very popular method of orthogonalizing if you are not aware of. So the Gram-Schmidt, like basically you keep on iterating and you kind of take a vector and then see what is the overlap with the other vectors and take away their component, so that each of the vectors are totally independent of the other vectors, right? So and you create a orthogonal basis, right? So and once you have created the orthogonal basis, then you use something called Arnoldi or Langsos kind of methods, which kind of does the same thing that we did in SQD, right? You have this subspace and then you project your Hamiltonian into this projected onto a subspace which is of much lesser dimension, and then you can kind of diagonalize, right? So as you can see, H could be of the order of 2 to the power m cross 2 to the power m, and V is 2 to the power m cross r. So essentially, this is what it does is basically your projected Hamiltonian is then of the size r cross r, and r is the Krylov order, like how many times you have done this H multiplied H, right? So based on that, you can create a reduced kind of a, project your Hamiltonian onto a subspace which is of much lesser dimension and then diagonalize, right? So the benefit of using this method is, when you diagonalize using this, using this process, what happens is, for general matrices, there's a method that is called Arnoldi, like where if you do this kind of a projection, the matrix comes out of this type, right? This is called an upper Hessenberg kind of a matrix, where you have this principal diagonal, and there's one diagonal below the principal diagonal which is populated, and all the others are zeros. So this kind of Hamiltonians are kind of very easy to diagonalize. And now if your Hamiltonian is Hermitian, in our case all Hamiltonians are Hermitian, what happens is if you do this kind of a projection, your the projected Hamiltonian becomes tridiagonal, and this is even easier to kind of diagonalize. So Krylov subspace methods are very kind of handy if if you are to kind of diagonalize this Hermitian kind of matrices, because all you have to do is kind of keep repeatedly multiply this H, and H, as normally this is also done for very sparse matrices. H has to be kind of sparse, so the matrix multiplications that you see is not actually of the order of n cube, it is much less, right? So these operations are not very expensive, right? And you can easily do it, like provided your matrix is sparse enough, and then you can create those bases, which is using the Gram-Schmidt method, and then you kind of project your matrix to a reduced subspace, and you eventually kind of get a tridiagonal kind of a matrix, which is very easy to kind of diagonalize, right? So any questions here, like okay. Okay, eigendecomposition of this kind of matrices are much easier. Okay, so so now what do we do? So let's say we have already used this Arnoldi and this kind of methods to kind of do this, right? So you have these this vectors, and you have kind of used a Gram-Schmidt method to orthogonalize it, create a orthogonal basis, right? But the other way to do is, just stick to the original Krylov basis, right? And and not worry and not orthogonalize it, right? And so do the same thing that we did with SQD, right? And use those vectors, right? Vi and Vj. Like the Vi and Vj are basically the Krylov vectors, right? If V1 is your V, V2 could be HV, V3 could be H square V, and so on, right? So these are not orthogonal. So Vi Vj is not the inner product of Vi Vj is not necessarily equal to delta Ij, right? And so once you do that kind of a operation that we did, the Lagrangian, and minimize it, right? So what you get is essentially the same problem that we solved for SQD, but in this case your S is not identity, right? So what was in the SQD was solving a normal eigenvalue problem. Here you have to solve a generalized eigenvalue problem. That is, you have this extra matrix S here. So this is a much more difficult problem to solve than a normal eigenvalue problem. So the generalized eigenvalue problem, this is much harder. So people, it's not very kind of easy way to kind of do. If you without going the if you decide to not go via the Gram-Schmidt kind of orthogonalization process, this process can be very expensive, because first of all you have to do all this calculation, and then you have to kind of solve the generalized eigenvalue problem. Okay. So now coming to how we connect this to quantum, right? So in quantum, unfortunately, we cannot have, you cannot use H for multiplication. We have to have a unitary matrix if you had to kind of use it, right? So what we do is, instead of multiplying H, we kind of multiply e to the power minus IHT. So this becomes a kind of a unitary matrix, which can be then expressed in the form of a gate, right? And then it can be multiplied. So instead of multiplying H square, H cube, what you do is you kind of multiply, psi, U square psi, U cube psi, and go up till r minus 1, the order of Krylov. And then, your UK can be written in this form, e to the power I k h t. And this can be generated using time evolution techniques in a quantum computer. So basically, there is a way you can write this in the form of gates, like they are very well known methods. So normally this H, as we were discussing some time back, H could be made up of several poly strings, right? Let's call them H1, H2, H3 up till Hn. Now these poly strings need not commute, right? So when they do not commute, right, you cannot directly write them as a product of e to the power ik h1, h2, you know, till hnt, right? So then what you have to do is something called trotterization. So when you trotter, there is some error associated with it, but this is, I mean, with some error, you approximate this thing in this form, right? What you do is essentially you divide this, you know, t by p and then take it to the power of p. So when you say take it to the power of p, what this means is, let's say you have created a circuit of this type, you repeat this circuit p times, right? And that's when it becomes to the power p. So you have a quantum circuit which you repeat p times, okay? So normally in most of the problems, the trotter order that is mostly taken is either of the order of 1 or 2. So you kind of either keep it one time or you repeat twice, okay? So Krylov works this way. So you have a initial state psi, so and use some Hadamard test. I'll show the circuit how you do the Hadamard test, right? And then you kind of create your HP kj. So kj is essentially it's shown here. So what you do is you kind of using Hadamard test, like you can find the expectation of h with respect to, you know, your e to the power ik psi, ik psi and e to the power ij psi, let's say. So, and you kind of create the overlap, kind of the projected Hamiltonian. And remember, because you are solving the generalized eigenvalue problem, you also need to find the overlap matrix. So you also need to find this S, which is essentially the inner product of psi k and psi j. And that also can be created using the you know, the Hadamard test. So I'll show you the Hadamard test, how it is done. So let's say again, if you remember, we have to start from a good position. So you have these 0 states, and you kind of create the starting position using this UST unitary, let's say. So this is a very good good vector, let's say, right? So which has a high overlap. And then you have these e to the power I j h t. So essentially you are trying to calculate h j k, okay? So when you are trying to calculate h j k, so you have this which is controlled, like, you know, you have a controlled kind of a gate operation based on 1 and you have a controlled operation based on 0, right? If you are aware of the, you know, the terminal, like, you know, the notation terminologies, right? And anyway, at the end you kind of measure in the z basis. So so how do you calculate this, you know, the overlap? Let's say, so first we'll try to calculate the overlap basis. So overlap matrix. So overlap matrix is essentially this matrix. Okay, we want to calculate this matrix. Okay, so let's see how we can do it. So initially we create the initial state, let's say UST, which is a very good state. We have created psi, and then, you know, you have taken 0 through the Hadamard gate, which gives you 0 and 1. Like, I'm sure you all are aware of this thing, and this is controlled over 1, right? So this operation is controlled over 1. So this 1 gets associated with psi j. You have e to the power I j h t. So e to the power I j h t operating on psi becomes, we call it psi j. Okay, and this is again controlled over 0. So what happens is, if you do this operation, so you get this. Okay, 0 you have with 0 with psi k and 1 with psi j. So 0 with psi k and 1 with psi j, right? And then you do another Hadamard gate, right? So you do another Hadamard gate, and when you do this Hadamard gate, this is the end result, right? So you have with 0 you have psi j plus psi k, and you have psi k minus psi j. Okay, and what is the, now if you do take the expectation in the z basis, so what will happen is, you have to take the probability of 0 multiplied by +1 and probability of 1 multiplied by -1. Why? Because your you know, the eigenvalue of 0 is 1 in the z basis, and the eigenvalue of get 1 is -1 in the z basis. So you have to, if you are to calculate the expectation of z, that is what will happen, right? And when you finally do the calculation, take the expectation, what you get is essentially the real part of psi k and psi j. And if you want the imaginary part of psi k, psi j, you have to just add a rz minus pi by gate here, right here. Okay, and you can get the imaginary part, and you can add them, and you can get this, you know, psi k, psi j, the overlap matrix S. And this has to be done for all k and j's. Okay, and if you are to calculate HPK, the projection matrix, there's nothing more to be done here except for this HL here, which is again controlled over, you know, the ancilla qubit, but on the state 1. Okay, and then you will get your projection matrix HPKG. Now, so this is a lot of operation, as you can see, right? So the KQD, or the Krylov quantum diagonalization, is very hard, because all these circuits, e to the power IJHT, e to the power IKHT is a lot of work. So, and the circuits are very, very deep, right? And on top of that, if you have to trotter, like you have to repeat that same circuit again and again, like it becomes very, very long, and it's impossible for today's quantum computers. So what we do is we take another method, use another method called sample based quantum, Krylov quantum diagonalization, that is called SKQD. Okay, and there what you do is you say that, okay, I don't want to create my, I don't want to use my non-orthogonal basis. I would like to turn them into my orthogonal basis. Instead of doing some Schmidt decomposition, I would say that my non-orthogonal basis can be expressed as a linear combination of my bit strings, which are the the UJs here. The psi j that you have is essentially, it can be expressed as a summation linear combination of your bit strings, which is an orthogonal basis, right? And then you go to do the same thing, where you collect enough samples over all the psi j's and for all the j's, j ranging from 0 to r minus 1, this is the Krylov order, and you create the projected Hamiltonian, and you essentially you have reduced it to a very lower dimensional space, and you kind of again diagonalize using some classical methods. Okay, so that's it. So you kind of you are able to diagonalize. That is it about sample based Krylov quantum diagonalization. And these are the references. I won't give you any more pain. And if you have any questions, kindly ask. Yeah.
Good afternoon, sir.
Yeah.
Might be a very basic question, but I'm so sorry for that. Actually, I just want to know that. At the very first slide, you just mentioned about the strategy encoding, okay? And there are multiple encoding techniques like angle, amplitude, matrix, MPS, and like much more. So if I'm having a data set, how can I be very sure that this would be going to this encoding? Very first question. And the following up, that how encoding is going to be helped in the future, like for that particular data set in the quantums?
Yeah, that's a good question, and there is no easy answer to that.
Okay.
So for problems which have domain inspired ansatz, right? For example, problems in physics and chemistry, so you already have some ready-made ansatz. So for example, in chemistry, you have the unitary coupled cluster, or in this case the SQD, if you remember, you use the the excitation preserving what you call the LUCJ kind of ansatz, if you have read that paper, right? So for domain inspired ansatz, it's kind of easy to kind of have a one-to-one kind of a mapping, right? But remember, it has to be unitary, because the classical alternative need not be unitary, the operations, right? The answer, they also have the concept called ansatz, right? So but in that case, it's not unitary. So you have to always have a unitary variant of that, right? So that's the one-to-one mapping that you can do for domain inspired ansatz. But for for other problems, like some quantum machine learning problem or some optimization problem, see the mapping, the encoding strategy is kind of based on the problem. So it is something that you have to do, like you have to think by yourself. Okay, so for example, if you want to have the maximum use of your states, right? You want all states to be represented by something, right? So you could go for something like a amplitude encoding, right, or a phase encoding. And if you say that I have all these qubits, but not all of I don't want to totally exhaust all my qubits for some states, right? So then you could go for some not so optimal kind of a strategy. So when I say not so optimal strategy, I mean you are not able to use all the states for a given to encode something, right? So you could have so ideally, like if you have n qubits, right, you will have 2 to the power n states. So you don't need all 2 to the power n states to encode your problem, right? If you have some problem that does not require 2 to the power n states, you could go for something less, and you could use the qubit for some others kind of.
Then it's more like a sampling, I guess. Like, then it's not sampling.
No, it's not sampling. It's kind of problem specific, but you have to think carefully, like what you want, right? So for example, phase encoding. So if you have a problem, right, which you can kind of directly map, right, related to some, let's say, some orientation, right? And then you can kind of have a intuitive idea, maybe my encoding can be done in this way, so that there is a one-to-one mapping between my the visualization that I am seeing in a classical world to how I can encode in a quantum world, right? So that is something that you have to think through. Like, there is no easy answer. But if you are like if you want to go for like a very optimal one, amplitude encoding is always there, where you are making full use of all your states. Okay.
Thank you so much, sir.
Yeah. Maybe Dina, you have a better answer, like. Yeah.
So there's a question by Rehan Khan.
Yeah.
And how can Krylov-based quantum algorithms ensure stable convergence toward the non-dominant eigenspace when the generated subspace is non-orthogonal and subject to hardware noise?
Yeah, so that's why, so if you look at it, like, in the KQD method, the quantum Krylov diagonalization method that I was talking about, so it's not easy, simply because you have to, first of all calculate the, the overlap matrix as well as the projected Hamiltonian, all those things. They are first of all, it's a lot of circuit depth, right? And then it's kind of the results could be noisy, and it is, if you're talking about convergence, right, Krylov has some known convergence properties, right? But whether it is converging in a quantum computer given the noise that we are having, that is something that we have to see. So the paper they have given some error bounds, right? But those are theoretical error bounds. But in a practical quantum computer, KQD cannot be implemented as of now, purely because of the sheer size of the circuit. So that's why people have started using SKQD, the sampling based quantum Krylov diagonalization, where you are using the bit strings as the orthogonal basis directly, instead of kind of solving a generalized eigenvalue problem, right? So that is much more, I think, doable with present day quantum hardware, right? And yeah, with some known error bounds. Yeah. Any more question? Okay, thank you. Yeah.
Thank you, sir, for the enlightening presentation.
What happened when India lost the match, or like what happened? To go back? Oh, sorry.
Thank you, sir, for the enlightening presentation. And now we would want to present a token of thanks. Now we would want to present a token of thanks from the IISc community for the presentation to sir. A big round of applause for him. Thank you, sir, for the presentation. And the next talk is titled AI for Quantum. And this talk... So now we have a tea break for 15 minutes. After the break, we would be joining for the next talk by Dr. Anupama Rai. So we'll meet in 15 minutes. Thank you so much. Welcome back everyone after the snacks. The next talk is titled AI for Quantum, which will explore the intersection of artificial intelligence and quantum computing, highlighting how AI is driving advancements across the quantum software stack. We'll discuss the Qiskit Code Assistant and other AI-powered tools to simplify quantum programming and circuit design. The session will delve into AI-driven approaches for circuit transpilation, resource optimization, and error mitigation. Together, these innovations will pave the way for more efficient and accessible quantum computing workflows. The session will be conducted by Dr. Anupama Rai, who is a senior research scientist at IBM Research. She is also an adjunct professor at IIT Jodhpur. Prior to joining IBM Research, she completed her doctoral studies from IIT Delhi. Her current research focuses on developing quantum machine learning algorithms and intersection of AI for quantum. She has served as a principal investigator for several grants in the area of QML for healthcare, life sciences, and worked with several hospitals and medical research centers worldwide. Let's welcome ma'am for this with a great round of applause.
Thanks to the organizers of the Fall Fest, Debarti, for inviting me over. I hope I can create some interest. So in the morning you heard Chiru talk about quantum machine learning. There are two aspects around it, right? So one side of the story is that how can we use quantum principles, principles that are not available in classical computing, and how can we improve machine learning, right? So that side of the story you have heard in the morning. I will give you the other side of the spectrum, right? How can I use AI to boost quantum tools, quantum architectures? What are the possibilities if I am an AI expert? How can I get into the field of quantum? What are the different things that we can do? So some of the things that I will be talking about today are things that we have done, are out in the open source. And there are a lot more, so yeah, at any point in time if you have questions, feel free to ask. So there's a vision that we have been seeing, following, trying really hard, I would say, which we call the quantum centric supercomputing. So if quantum has to see its advantages, it's not going to be alone. We'll work in a system where we have the HPC infrastructure, we have the quantum infrastructure. So all together with in fact the AI enabled chips, right. So the AI infrastructure, HPC, quantum, everything together, and the algorithms should be modular in a way they are structured to be able to leverage the advantages of say HPC or classical and quantum, right. So what is the vision here? What are we trying to do? How can we reach there? There are a bunch of algorithms that today exist that is already leveraging this kind of a system, and they are showing such improvements, right. So in the previous talk you heard about diagonalization, and you would have heard about SQD, right, and Kalyan would have told you that okay, how it, so it takes 12 minutes of your quantum processor and then 2 hours, less than 2 hours of your classical processor, and which is a supercomputer, in this case a Fugaku machine, and how these things are seamlessly integrated, right. How are you orchestrating these workflows? And there is a lot of things that AI can do here, right. So this is a typical infrastructure architecture that we do when we talk about workflow or resource management or resource optimization. You have your CPUs or your GPUs or your AI infrastructure, and you will have your QPUs right there. I'll just remove latency off the window for now, but I mean we are not yet there to talk about that, oh the latency is high and so on. I mean our algorithms are not that fast yet that we those milliseconds, those really count. But yes, that would be also something that would be quite pertinent in a couple of years. So what are we saying when we talk about quantum plus AI? What are the different things that exist, right? So you have some, say your data or your problem today is classical, and you have been using that kind of data or those tools and methods that you have from your classical computing already. You want to be able to port them to quantum states, run something in the quantum device which you know that there is a clear path to advantage. There is a need for running this in quantum. Not everything we want to run in quantum, but there are certain things that are hard for classical, we want to run them on quantum. We want to get back things and then run them in classical. This is the typical hybrid quantum classical that everyone talks about, right. But there is more, right, and that is what we are going to talk in this particular talk. So, I am going to give you just say 4 things here, not a lot of things, and hopefully I can go into details of all of them and explain. So, at least you should have 4 takeaways from this talk. So, the first thing, right, a simple thing that all of you today, I mean hardly I do not see students today coding everything from scratch like we used to do. So, they use Claude and all these LLMs, and you must, right, that is how the developer ecosystem is moving. I mean there is no point in reinventing the wheel. So, there are these code assistant existing for you in different extensions that you use. Now, generating codes for generating classical AI codes or classical codes was not easy, right. Now, generating quantum codes, they should be even more difficult, right. So, that was the first thing that we started from. Can we create something like a Qiskit code assistant, right. So, we want to create an assistant, we want to teach our LLMs that okay, can you generate Qiskit codes. Now, instead of they being able to generate very good codes, because you do not have a lot of data to train with, you do not have a plethora of Qiskit codes existing, then the Qiskit library is constantly changing, because in a new field like quantum, there is a lot of things that you keep coming, right. There are new algorithms that are coming, new implementations, not everything still that yet implemented in say Qiskit or in any other of the quantum languages. So, you have papers, and doing paper to code in quantum, believe me, it is way difficult than it is for other paper to code projects. The second thing that you see here, because it is a Qiskit Fall Fest, and I am hoping that in the first few lectures you have learnt enough of quantum computing that you know that there are these huge quantum circuits that we are trying to run. Can we do better optimization on these quantum circuits before we run them at different levels? When we say that okay, I have a 50 qubit circuit that I want to run on this hardware, which is a 156 qubit hardware, right. So, which are those particular qubits? I want to select those 50 qubits which have less noise, which maintain the same connectivity that I have in my user defined circuits, and I do not know the noise profile immediately. Last noise profile that I know is when the device has been calibrated, right. So, can I still go ahead and pick the best layout? One problem, right. Then when I transpile it for the quantum compiler, can I use the best transpiler passes, right. What would be the best transpiler algorithms? Think of them as set of graph algorithms in your mind, and those are the kind of things that you see in this pillar 2. Can I optimize this circuit? It could be for transpilation, the end users, there are several end users here, but broadly what you are doing here is you are trying to optimize these circuits to be able to better run them on the quantum hardware. The third one, now when I am talking about quantum centric supercomputing, so I am saying that okay, I have so many devices, right. I have these HPCs, I have a classical resources, I have a quantum resource, and these resources are pretty expensive. So, how do I optimize the usage of each of them? While my quantum device is running with certain things, my classical systems should not remain idle. So, how can I do better resource management? How can I do better workflow orchestration? So, there is a bunch of work that you can do in this third pillar. And the fourth pillar is more about okay, I get some results from my quantum device, right. Now, so say look at the sampling based algorithms. I get a lot of bit strings that I am constantly sampling. Can I do some sort of a distillation approach here? Can I get the best bit strings, right. So, this is something, I mean Scott Aronson called it peak circuits, and that is from that time we call it peak circuit identification, or there are a bunch of problems around peak circuits. And these are some things that we are trying to do with AI, and we have some excellent results in this. This is a very recent work, but we are seeing a lot of encouraging results. Now, just deep diving into each of those 4 pillars that I showed, right. First one, creating a Qiskit code assistant or a code assistant. Many of you would have done a code assistant for say different languages or even for Qiskit, right. So, I mean because Qiskit is art and the Fall Fest is Qiskit themed. So, we'll concentrate on say Qiskit code assistant. So, different things different components that we already need. For example, you need a data set, you need to choose some model, fine tune that particular model, expose that as a service, integrate that with whatever people are actually using, say Visual Studio or whatever, wherever you have to build these extensions for. Exact same pipeline we are following here, right. Now, what are these data sets and what exactly are we doing? So, these are some of these data sets that you see here, and I have just put in terms of the million tokens that you see for each of them. This is slightly dated, we have a bunch of models. So, we have been creating these newer models and putting them back on Hugging Face for everyone to use. For the Qiskit service, yes, there is a set of restrictions that we have, but for open source Hugging Face you have a lot more that you see here. And then we have to work on something called a Qiskit human eval. So, being able to have them test them is a more important step, right. So, we want to be able to see whether the code compiles correctly, the code functions exactly the way you want it to function, and there are a lot of these quantum nuances that you want to capture. So, for all of that we had to create something called a Qiskit human eval and write a bunch of tests for that. I've just linked the paper which was an outcome of that particular work. This is a detailed slide. I do not know how much, I hope it's visible and readable, but yeah, so this is, I mean you can just go down to the SW bench data set and see all about the work that we have been doing, what were the different data sets that we used for training and so on. This is an ongoing work. So, there are some papers that are already published in IEEE Quantum Week for the last couple of years, but there is a lot more work that is going on because we need to keep these systems improving. There is a lot of work in terms of Qiskit code migration, right. For example, where you had a Qiskit code which was in say some older version and a user just now wants to have it migrated to a newer version. So, that could be one of the things where we are using a graph frag kind of a thing, and there are several such features within Qiskit code assistant that we are working on. So, yeah, I mean these are some of these models. I mean so if you see Quen works significantly better than the other models, and these are these are some of the test results that you see, the 150 test cases that I mentioned. So, these are some of the test results that you see here. There are a bunch of other models that we have, but I mean there are legal bindings. We cannot if you have a service, you cannot put a lot of these models. For example, you cannot train or you cannot fine tune Claude and so on, but there are a bunch of models that we have been training, and these are some of these models. Okay. So, I think this is a video of it. So typically how it works is you give it a prompt very similar to what you have in several other code assistants. So if you look at the VS Code extension, then something similar, maybe many of you guys would have used Copilot and other things, right. So something similar, but we also have a full blown portal for it where you can go ahead, and there are two different things. So you might want to understand more about the concepts. So you use a RAG for that, and it will explain you the concepts, give you the codes which you can generate, run on a device. So if you have your IQP token there, it directly will run on the hardware. If you do not have your token, it will run on a simulator, or if you are asking for somewhere around 50-60 qubits which the simulator is unable to provision, it will give you that error as a message. But here what you are trying to generate is, okay, I will give something and it should generate some of these Qiskit codes and give me some of these results. There are more agentic approaches. So, as I do not know if you guys have used IBM Quantum Composer, where it was a UI kind of thing where you can drag and drop gates and do some initial things, which is very good for a starter person. You cannot really do a lot beyond a starting kind of thing. But now what we are realizing is there are a lot of these people who are not coders or coming from backgrounds like biology or chemistry or physics people roughly code, but other people who are not very coding savvy, but they tend to be able to be more comfortable learning or implementing if there is something like a drag and drop. So, something that we call internally as a Qiskit studio is where you have such a flow, it is built on Landgraph and it uses that kind of a UI. So, you have different things. So, you can just, so here is the assistant which is more like the chatbot. So, you can just directly ask that, okay, show me how to run say sampling based quantum diagonalization, and it is going to start generating, and you can then say, okay, I want it to run on nitrogen. It is going to find out what is the Hamiltonian of nitrogen, what would be the number of polyterms, what are the different things to have. It is going to do all of that, and it is going to run it. Now, you can go ahead and change different parameters and different things. So, it is still something which is more accessible. So, it is not only a learning kind of a platform, but a lot of people typically prefer this. So, these are things that you can quickly spin it up. So, all the Qiskit functions that you see today or some of the Qiskit add-ons, they can be converted into something like this, and you can have an agentic app which runs. So, I mean there's a demo. I'll not go into the demos. I mean, I have just put in the link, and if whoever is interested, you can go find and see more about it. Qiskit Studio, I don't know. Will release, will not release, but yeah, that is a separate discussion. But what basically it has is, as I showed you, you have that visual circuit builder and you have this AI powered code generation. So, as soon as you change something in the visual blocks that you had in the last slide, the code automatically corrects itself. So, if you say that, okay, here I want resilience level of this, that you drag drop in the UI, the code will automatically reflect the same changes. You have along with that, you have real execution, and you have more explanations as well at every step. So, this was when we were building it, because this was coming from a lot of our client request and all the education that we keep doing. So, that is why education was a key focus for building Qiskit Studio, but yes, there are a number of other applications for that. I just put in a QR code if people are interested to go and check Qiskit Code Assistant, and or just try the models yourself from Hugging Face. That you can anyways do, the models are up there. So, the second pillar that we were talking about, right. So, can I actually do better circuit optimization? So, there are different parts, right. For example, as I mentioned, right, how can I choose the best layout, best qubits for running the circuit? What are the different mechanisms for say a routing pass to do? Can I actually have a better or a more optimized circuit? So, the user has created one circuit. Did I switch something off? Okay. Okay, it's working? Yeah. Yeah, even if it doesn't, yeah. So, I don't think it is. Okay, no problem. Am I audible? Okay. Quite loud. Yeah, it's okay. It's okay. Yeah. I'm audible, right? Okay. So, yeah, so in this AI routing pass, basically what we do is, so suppose user has a circuit and that is using a lot of these gates which are not there in the particular chip that you want your circuits to finally run. So, you do a step of decomposing it into the sort of base or the native gates of that particular hardware. So, those are different steps of optimization, and in that process you do not want to be increasing the number of swap gates or increasing the number of total gates or the depth of the circuit, right. So, what are the different mechanisms by which you can optimize these circuits better? That so there is a lot of work there, and but I have just linked the paper which we have. This is an old paper where we are using some reinforcement learning techniques to be able to do better transpilation passes. So, within transpilation there are several stages, and each stage has to be taken care differently. There are different optimizations that we do. And this particular paper covers most of the ways that you can do here. Now, there's another work which is more on what should be the circuits that will help us get some advantage, right. There's a lot of discussion. There was a paper early this year which is called the framework of quantum advantage, wherein people tried to coin out what would be the type of circuits to use, what can I do in terms of like verification, reliability and so on.
So for that we created something called bench press, where we have a bunch of quantum circuits that we typically do benchmarking against, right? So what we did in this case also, we ran the same Qiskit AI transpiler. So we have our traditional transpiler passes or transpiler routines, and we do a comparison with that and the AI transpiler passes. Okay, so there are a lot of next steps here, as you see, transpiling to gross code, dynamic circuit generation, how will this scale in a fault tolerant kind of setting, and what are different alternates when we talk about the routing problem, because it's a very vast problem. There's a lot of scope for new work there, right? But one key thing that I wanted to convey here is, what are we talking about here? What are the different AI methods, or what are the places in quantum where I can use my AI knowledge. So just treat them as some of these places, or okay, transpilation is one big process, or routing is one big process, or within transpilation there are so many problems where I can use my AI skills and still contribute to the field of quantum. So that's what I want you guys to take home from this particular part. Again, I've just put in a QR code for transpiler service. This is runs the transpiler on cloud. You can locally run it also. You can have your custom transpiler workflow. For example, you are running some particular algorithm and you want to experiment with different types of transpiler algorithms. You can run it locally for all of them, and then execute and see, okay, what works best for me. There are different steps, so you can create your own flow. That I want to be able to use, say, AI based routing, but the other thing, maybe I will use some other algorithm. So you can have a mix and match, whatever works best for you. So the point here is, how can we give more control to a quantum researcher who wants to have all these knobs with themselves, but they don't have to work on these knobs. So the AI researchers can come in and build these knobs for them. The third one, right? Now this one, again, a very important, a critical piece here, where we are talking about resource management, right? So we have a collection of tools. How can we do resource management better? As I mentioned, right? How can we reduce, say, idling time? How can I ensure that I am using my resources optimally, right? Can I do better job estimation time prediction? So for example, because we have a lot of these logs for each job, so we have some understanding over the period of years that this kind of a job, this kind of a program, how many jobs it's going to spin, how many qubits it needs, and what is the queue time, and considering all of that, we can give you some accurate prediction of job time. Now, to whom this is very important? So if there are faculties, and I know there are some faculties in this mix, so for example, you have submitted for an NQM proposal, right? And you have asked for some quantum resources. Now you want to exactly understand that, okay, this would be my quantum experiments, how much time should I allocate, or how much of these quantum resources will I need, right? So if you can do this job, you can do the prediction of this time required for each job accurately, you save a lot, right? So you know exactly this much time I'll need for each of these types of jobs. And if you look at the admin for each of these quantum infrastructure, then for these admins, it's like a very hard job. It's like a nightmare to them when we talk to them. But if you can give them these things as a service, then they exactly know that, okay, I have, say, for an institution like IISc, so IISc has this access and they have to run it, and they have so many students who are wanting access. Some particular students will have some research papers, so they are going to increase their usage, versus someone is not actually using their resources much. How can I optimize that? It's a nightmare for a data engineer or a resource engineer to do that, and there could be a bunch of tooling that you can provide to them. So this service was primarily thought and built for that kind of a purpose. There are a lot of other things, for example, job validation, right? So often this happens is you run something, and because you run it over cloud and you get an error, right? So we at, say whoever is the hardware provider, we need to ensure that, okay, the job that you are submitting, we want to be able to do a very first cut, right? As soon as we get a job, is this job valid? Will this job not throw an error? Because you're going to sit and say in queue for next 40 minutes or 1 hour, 2 hours, who knows, right? So after that queue
queue time, you realize that this job is invalid and it's going to throw you an error. That's a waste of the time for both the researcher as well as the queue logs, right? So you are not actually, so we are not using our devices very well. So we need to ensure that the devices are used well. So for that, a job validation and job prediction services are very important. Then there is a bunch of work which, for example, under circuit classification or circuit manipulation techniques, as we call them. For example, I know Debarti has been working on circuit cutting and several other things. So circuit knitting as a toolkit, that we thought that, okay, there are multiple advantages of having circuit knitting. And going back to our initial vision of quantum-centric supercomputing, you want to be able to fragment your circuit, right, to be able to run them on different nodes. So you can use circuit cutting as a manipulation technique to do that. And we have been publishing a bunch of papers around how can we do that better, right? So circuit cutting is one such thing. There are several other tools. Some of them are available as Qiskit add-ons also. You can look at operator backpropagation and so on. Right? So there are a bunch of these things where you can actually, given the circuit, can I classify or can I use an AI model which helps me classify what could be the different tools to use. There are a bunch of tools out there. I don't know what tools or what combination of tools or what is the series of operations that I should run. Can an AI model just run them all for me and give me as a, say, a dashboard where I know that, okay, given this is the circuit that I want to run, or say this is the budget I have. When I say budget, this is the amount of time or amount of resources I have, and I want to be able to go down to, say, this accuracy spectrum, right? So so it can tell me that, okay, you can run, say, X, Y, and Z operators, and that is going to take you to this, which fits in your budget. However, if you run, say, X, Y, Z, and alpha, it is slightly exceeding your budget, but it can get you to say holy grail, right? The chemical accuracy level, right? So something like that, can I as a user, it would be very, very good for me to, I can only build quantum algorithms. Can I actually find out that how do I run this quantum algorithm better, right? What are the kind of toolings that I can leverage for this work? So this is somewhere around that particular area. And the fourth thread, right? So this is another one which is very new, right? So last, I would say, maybe a year, right? So there's a lot of interest in something which was called as peak circuits. So there is a way that in quantum you can actually identify that these are the circuits, or these are there are these bit strings which stand out, right? So there could be interference ways, or there could be different ways to be able to figure out what are my what are the most important samples that or what are the most important bit strings, right? And quantum circuits exhibit these clearly. So that's what they are calling as peak circuits. Can I actually identify these peaks better, right? When I'm say from the last talk, you guys heard about all these sampling based algorithms, right? When you're sampling at such a large scale, and then again you don't want to make it a very computationally hard problem for the classical device. You're just throwing all these things to the classical device and asking them to diagonalize. So can I actually have a more distilled approach here and then pass it to the classical device, so that overall time I'm just reducing, and not just the overall time, right? For example, there are a bunch of say in DFT, if you were able to do in classical in DFT, where you can run say 100,000 kind of atoms interacting with each other, and you're not just looking at the ground state, but you're also looking at the excited states there. Now if you think of something like that, or a counterpart of that here in quantum, you have multiple limitations, right? So how can we reach that? These are some of these. So there are multiple tools that would be needed to fit into this larger picture, but one of these tools is the identification or distillation of peak circuits. So that's one way. The other ways is, can I actually use, say, AI-based decoders to be able to do better error mitigation? So there are a bunch of these algorithms which we call error mitigation. What are they? They are some post-processing routines. So for example, I don't know if that has been covered. So you have, say, some twirling-based approaches. You have zero-noise extrapolation kind of approaches. So there are different approaches where you run a quantum circuit, you extract something, and then you extrapolate, or then you find out with some mitigation or post-processing routine that how can I minimize the effect of noise and get the best result out, right? So can I actually work on, say, some AI models to improve or to generate better error mitigation strategies, right? Then there is a lot of work that is happening in terms of error correction algorithms also. For example, I've just mentioned LDPC codes, but there are for other codes as well. There's a lot of work that is happening for gross codes and other things, but there's a lot of so it's in the similar spectrum. So can I look at how can these AI models help me do better error correction, right? In calibration, there's a bunch of work that, in fact, I am also involved in a lot of these calibration kind of work, where the goal is, so we typically calibrate, and I can only talk about the devices that we built. So we calibrate each devices once in 24 hours. And then we have to, whenever we spin a new model, so or a new device. So for example, say right now we are doing it for Cleveland Clinic. They're upgrading their device from a quantum system 1 to quantum system 2. We take a couple of months to put in a new device, right? For each of these routines, we do a lot of calibration for each qubit gate, for the gate operations and so on, right? So there's a long calibration process. There are a lot of log analysis to be done, and there is a lot of need for automation here, right? So those are some kind of tasks that AI is very amenable to do, right? And they are very efficient doing. Now, if those things can be plugged in here, we can overall increase the efficiency of the quantum devices, right? That's our final goal, right? So how can we increase, say, something like machine efficiency, or how can we do faster auto calibration, or how can we figure out that, say, a calibration on one particular qubit failed, so this algorithm failed on this qubit, what is the best algorithm to run in this situation so that I can recalibrate this particular qubit, right? So these are some very, very hard questions, and the device engineers, with their huge amount of the research that they have been doing, so some of them know in the tip of their hands, right? Some of them do it manually, but for the rest, it's a hard learning process. So can we encode all that knowledge and use AI there? Now, yeah, this is more on peak circuits. So this is something that has been grabbing a lot of attention, in this sense that people have been claiming that if you want to have quantum advantage, you need to be able to do this process better. So how can we do this process better is what I was explaining, that okay, if I can distill these peak circuits better, then there's a reason why we say that okay, the sample dimension is going to drastically decrease, then your total time, the total efficiency, and if you can just come to that realm of what is important and what is unimportant, then your space decreases, which overall impacts the rest of the things, right? So there's a lot of sample distillation work that we are doing here, as well as a lot of classical benchmarking, and there was this hackathon from I forgot the name of the company, where there was this open source hackathon done, where we worked on some of these reinforcement learning based strategies and doing peak circuit distillation, where we can see that okay, the AI based methods significantly outperform, and within a matter of 8 minutes of the launch of that hackathon, so David got some excellent result and won the hackathon. So okay, so now we'll just come back to where we started from. So what are these synergies, right? So we see a lot of synergies, a lot of places where these two fields interact. So there was a time when people were very interested in quantum machine learning, because quantum is very buzz and machine learning has all the buzz, and people were just wanting to club these two and find something very important. While the field is very, very important, the basic problem of quantum machine learning algorithms as of today is the scalability, right? So they are really struggling to scale. Now, there are a bunch of algorithms which are fault tolerant in nature, that have mathematical proofs with these fault tolerant assumptions, right? Now, once you start to relax these fault tolerant assumptions, the math is all gone, right? So you have to rework on the math to say that okay, can I still prove that there will be a mathematical convergence? So that's the place where all of us, all the QML people are really struggling. While you are struggling at that part, the other part, there's a bunch of work, and that's why I thought that maybe I'll focus here. There's a lot of space where all the existing AI and ML knowledge that all of us have can be used to make the entire system better. So you cannot have quantum advantage in a day, right? You need to be able to plug all the open holes. And a lot of these open holes can be plugged with AI, not all. right? There are some holes that you can plug with AI, so why not we do them and then create that overall infrastructure. So this is some of the works that I have put in where, you know, foundational models along with quantum can typically help expanding the current landscape the way we are seeing. For example, dynamical systems, so if you want to solve differential equations for dynamical systems, or there's a bunch of linear algebra and eigenvalue problems, for example, all the problems that we talk about in quantum chemistry, so and several others. There's a bunch of optimization, combinatorial optimization problems that, you know, typically we are seeing that, okay, don't take a quantum ML approach, rather there are a bunch of different approaches that can actually, there's a potential benefit that's already there and that can happen, right? So why not you look at your application from that lens? And of course, in terms of probability and stochastic processes, there's a lot that we can possibly do. So if you just look at the landscape, and that's why I thought that I'll just put in some of the works here. So how have traditional solvers been looking at these problems? How are foundational models looking at it? How are we using these large language models or foundational models in that sense? And what are the kind of quantum algorithms? What are the kind of things that we are using? Right? So for example, in differential equation, if you see that there are these classical numerical solvers that we have been using, there are a bunch of foundational algorithms. There's a lot of work in FM for math in this spectrum, and of course there are some quantum algorithms. There are actually a lot of these quantum algorithms in not only these two buckets but in several other buckets, and they have these fault tolerant expectation if you look at them. But there are some of them, and that's the open research problem to, you know, a lot of you who might be PhD students or postdocs. Those are the kind of open research problems which we should look at, right? So this is a fault tolerant algorithm. If I relax the fault tolerant assumptions, how will the math look? How can I make this a pre-fault tolerant algorithm? What is to be done there? So those are the kind of important research problems that you can look at. I categorize them with application areas so that, you know, that is more relevant. There are a lot of application researchers who are looking at, say, combinatorial optimizations, and these could be some of the algorithms that you are looking at, right? So for example, QA, okay, it should be QAOA, and several others that you are using. So yeah, I mean, I would, yeah, so I have 15 minutes. So broadly, there's a lot of work and there's a lot of intersection, but we see a very promising future in, so I'm not saying that stop the work that you have been doing in terms of quantum machine learning, but while you are exploring things in quantum machine learning at an algorithmic level, which is needed as of today, it's not yet there to be able to, I cannot run reliably a quantum algorithm on, say, the quantum kernel methods. I cannot run it reliably on a very large number of qubits on a very large data set. It doesn't work, it doesn't scale. Versus, so there's a lot of work in the algorithm space. Versus this side of the story where you're using AI for solving quantum, there's a lot of work that you can immediately do. Right? So there's a very good intersection, and I want to, you know, leave you guys with that thought that there's a lot of possible ways that you can contribute. Open to questions.
Ma'am, so the first doubt that I had was, what exactly do you mean by fault-tolerant assumptions? I didn't get that part.
It's working? Yeah. Okay. So fault-tolerant assumptions is a very good question. So for example, if you are having a quantum phase estimation in the block, so there is a, so you are designing a quantum algorithm and there are multiple components of that, and one of those components, so I was in a discussion just before this where we were working on a mathematical algorithm there, but it has a bunch, and there is a very good convergence proof that we have come, so mathematically it is great, but there are two assumptions. One is quantum phase estimation that we are using, then there is some amount of amplitude estimation, there are a bunch of things there. Now how can you relax it? So instead of quantum phase estimation, which you know that is going to work in the fault tolerant era, what is something that in a pre-fault tolerant era you can plug in that place without losing the benefits of the other sides. Right? So, that is something that we need to think about. Right? So, there are some places where to get that added precision or to maintain the advantage that you are getting in quantum, you are losing that precision. So, then you will not get an advantage, right. So, keeping that in mind, we need to restructure these algorithms which have that fault tolerant assumptions or QRAM, right. So, multiple such examples. Yeah.
Okay, and my other question was, like as we spoke in a previous paper also today in the morning, that number of iterations that we run our quantum algorithm for, that is not known. We don't know what is the exact value there. Somebody who has say a better quantum computer can run it for 5,000 qubits, but if I do not have those resources, I can maybe only run it to 12 qubits. That's something that would maybe even scale to the calibration side. So do you think AI could be able to come up with such an answer to like how many number of iterations would be perfect for a quantum algorithm, and like how would it be able to do so, considering we have a lot of limited data and the cost is also an issue?
Okay. So, number of iterations and number of qubits, let us think them as two different things. Okay. So, what is number of iterations is typically in classical machine learning, you run this algorithm for till it converges, right. So, till it converges, say let us say you took 400 iterations. So, similar to that we do in quantum also, we might have multiple iterations that is required till it reaches some convergence, right. Now, the use case will govern what is their convergence criteria and so on. That is iteration side of the story. The other side of the story, what is the number of qubits, right. Now, that is a mapping that you predefine and do. Can AI help in there? Good question, I have to think, I do not know. But sometimes for some it is very application driven. So, I want to be able to encode these Hamiltonian terms in this way, right. So, there is probably not much to do, right. I am governed by something, right, I am governed by the equation, right, versus say for a classical machine learning kind of a thing where you have features like height and weight of all of us in the room, right. So, you have two features and then you want to do better feature learning, and then you are saying that okay, I do not want to use 2 qubits, I want to be able to decipher and figure out something like that. So, you have something governing your number of qubits, right. So, there okay, I do not know, in the top of my mind I do not see the value there. Now, the other thing that you mentioned, that someone has more resources, so they are able to run it better versus us. Where can that happen? So, for example, I think say MNIST, I think I saw fashion MNIST is what you were talking about? Okay. Okay. So, let us say you are talking about 700, 800 features and you are saying that oh, I did not have 700 qubits. So, I had to do PCA or I had to do some feature dimensionality and I run it on smaller qubits, and that is the reason why I am probably not getting great results, right. Although that is not, you do not actually have a way to quantify or pinpoint that okay, that was the exact problem, but yes, there is a loss of information that you did classically versus if you did not do a classical loss of information and assuming you have 700 qubits. Will that be better? Of course, that will be better. Now, can an AI algorithm help us figure that? At this point, because we do not have that many qubits, right. So, we are not thinking ahead of 1000 qubits. There are a bunch of problems that we should think about that are in the realm of say 100 qubits, right. Do we see a lot of papers which are ranging in 100 to 150 qubits? We do not. Right. Those many qubits we already have, why are we not going there? So, it is not an easy problem, that is why we are not going there, but that is something that should be our focus. So, whoever is working on the quantum algorithm side of things, can I actually do something in the space of say, I am not saying 100, you have to go to 100, but in the space of say 60 to 120 qubits, that entire range. What is the best way that I can leverage, because that is going to give me a much larger Hilbert space which I am not tapping into when I am working on 10, 12, 20 qubits, right. So, if we could do that, we know mathematically that we have an advantage, right. So, that is something that we can do today.
Thank you so much, ma'am.
Hello. What do we mean by here?
Sorry.
What do we mean by recalibrating the qubit?
Okay. So these devices have lot of noise, as you know, right? So what we typically do is we want to be able to calibrate them to their their ground states. They have been exposed to a lot of noise. There are a bunch of calibration algorithms that we run for that entire device. So for that entire chip, across all connections we run this, right? So we want to be able to recalibrate them. The reason why we are doing it every 24 hours is because we cannot do it like every hour, because people are running their codes and so on. We do not want to come in the way of people running their codes. Typically every 24 hours we will run it, and so that you are still getting to that least noise place. So if you say run something immediately after a calibration, maybe your noise levels is lowest, versus you run something 23 hours post calibration, of course your noise levels will go up. So yeah, so that is the need to calibrate these devices.
Ma'am, the thing was like, if you see the ultimate standpoint or the ultimate point we want to reach for AI, they speak about AGI or whatever definitions they
Sorry, is it become?
They speak about AGI, like the ultimate point they want to reach in AI, right? Whatever definitions they may have of it. But my thing was like, is there a similar point for quantum? Like, of course, I know this quantum advantage, quantum supremacy, but is there something even more profound we are targeting through quantum? And also, can AI add up to it?
All I know that, what we are targeting is, can I do something useful in quantum? Can I do something which I was unable to do classically so far? While I say that can I do that? I want to be able to do that in terms of, say, not just speed and accuracy, but also I have to keep in mind the cost that I involve, how much of quantum resources, how much of classical resources I will need to be able to achieve that, versus the best classical algorithm, right. So that is the battle that we are doing. If my classical algorithm can do something reasonably well, I do not need quantum for that problem. So I need quantum for those particular problems where classically I am not being able to do. Now, not just I want to be able to do it better in terms of accuracy and time, I want to be able to have a verification, right. I need to know that my algorithm is verifiable. If I run it on this device versus on that device at different times of the day, so it still performs the same way, right. Best way is if I have a mathematical proof, that is how we start, right. We have the math first and then we do the experiment, and then we want to conform back to the math that yes, it exists, right. Experimentally, what do? We want to run it at different times of the day, because we know the noise has been changing. We want to run it across different layouts, different partitions of the data, and so on, right. That is how we verify that, okay, whatever I got in the math, I still get back from an experiment side. So I think that is where I would say I am in terms of the quantum aspirations that I want to do. Apurva sir is here, so he has a lot more aspirations in quantum, but we are there, right. I would say that is advantage, that is quantum advantage to me, if I can run a circuit reliably with a lower cost, more accurate, something that I was not able to run in my classical resources. That would be great.
Thank you. That works.
So there are some questions from live stream YouTube. There's a question from Kapil S. He says that how does the data feedback loop in the AI driven quantum systems differ from traditional machine learning pipelines, particularly in the context of quantum measurement collapse?
Okay, quantum measurement collapse, not tried. Now, say something simpler like the first example I showed, code assistant, right. Very similar to what you do in traditional AI, right. You plug in the data, you run these models, these are the same LLM models that you are running the same like classical code for, you run it for Qiskit code, right. There are no such quantum nuances there in that particular problem. Now, where there are quantum nuances, possibly in the calibration side of things there are quantum nuances. There are nuances in the peak circuit distillation, right. But yeah, I mean there are ways of thinking about this. So one is, so there are places where I want to fine tune my LLM models. There we are not actually leveraging the quantum nuances, right. It is more like, okay, there is some data which and the data is also not quantum, like this is Qiskit code. So it is not quantum, it is a classical data at the end of the day, right? Versus there are some places where I have this information which and we have not been able to do it on quantum data. So, I will not say that okay, we have done anything on quantum data. So, we do not have this problem envisioned yet.
One more question is, in quantum synthesis, how does the non-cloning theorem and entanglement alter AI's optimization space compared to classical logic synthesis?
So there's circuit synthesis, that's a good question. So, circuit synthesis, routing and those kind of problems where we are primarily looking at say transpiler kind of phrases, right. So, there you are not actually, so entanglement is what you have desired in your circuit, right. Versus what I am looking is the same circuit composition that you are wanting, can I actually give you the same circuit composition from the layout I have, or can I generate an optimized synthesized circuit, so say a Clifford circuit I synthesize for you, or say some other circuit, optimized version of some other circuit that I generate, which has a say basic things like minimize the number of swaps that I have, can I reduce the circuit depth significantly so that it runs more efficiently, so things like that, right. So, that's how you.
One last question. How can reinforcement learning be applied to optimize qubit routing on noisy intermediate scale quantum hardware?
So, there are a couple of papers, I think 2-3 papers from David Kremer and team. So, David and Ayushi have been, I mean there are a bunch of people and there are a lot of other people outside of IBM Quantum also who are looking at reinforcement learning for this, for similar kind of problems, I will say. So, yeah, you can go into the details, I mean there are big problems. However, I will not say that reinforcement learning is the best way to do that. So, the current known machine learning literature, that is the best way. It does not mean that that's I mean we do not know more than reinforcement learning, honestly. So, a recent example that I heard which I liked a lot was, so reinforcement learning takes a path, right. So, you do a mistake, you give a penalty, you do something good, you give a reward, and when you at the end of the game say you win it, right. So, what happens is this entire path is given the highest weight. Do humans learn like that? No, we do not, right. We do not say that okay, if you have to climb from this floor to the 5th floor, you have to fall at these many places, but that is still the best path, no, right. So, so reinforcement learning is not the best approach for this, but current best approach is reinforcement learning. We are being able to learn these things in terms of the transpiler passes significantly better than say the existing algorithm on Qiskit is called Sabre. Okay. So, there is a version of Light Sabre that is currently implemented. So, if you do not run it with AI transpiler, if you just directly transpile your circuit, you will run Light Sabre, right. And when you run say in AI transpiler, there are a bunch of steps like synthesis, routing and so on, right. So, you can have each of these steps separately. So, when you run each of them, you see that okay, there is a significant improvement that you are being able to get. The reason why you are getting that, it is a graph optimization problem at the end, right. So, it is basically the number of qubits, the number of connections in this device versus the number of qubits and the type of connections which you have in your circuit. So, you are trying to do this smaller graph on this larger graph and say that what is the best subspace subgraph that I can get, subgraph isomorphism with some extra additional constraints, that is it. Right. So, then reinforcement learning plays quite well. Any other questions? Okay, then thank you all for your attention.
Thank you, ma'am, for the presentation. And now we have a token of thanks from the IISc community being presented for a contribution to today's event and making this a success. So please, ma'am, please come on stage. A big round of applause, please. And a round of applause for all the speakers today. This is the last talk of the day, so a huge round of applause for all of them. Thank you so much for making today's day such a success. Please join in tomorrow as well. Tomorrow's event will be at A.V. Ramarao Auditorium in the Chemical Sciences Building, IISc. So please join in there as well. We have an interesting set of talks tomorrow as well. Thank you so much.